Good morning.
Yes, good morning.
Good morning, everybody.
Yeah. So can I ask you one question? At what time my talk is today?
Excuse me. Your talk is about 9:30.
About 9:30.
Yeah.
Okay. Yeah. The reason I'm asking is I'm in another meeting, so I just want to come out at 9:30. Okay. Thank you.
To get licensing from Ministry of Health. This is
I think we start.
Okay. Good morning, ladies and gentlemen.
Wait. We open
invitation for the members of the advisory board to join us on Thursday in this.
Okay. Good morning, everybody. It's a real pleasure and honor for me to welcome you.
1 minute, please.
Okay.
Waiting for. We just opened the webinar to attend this.
Okay.
Yeah. 121. Why we should wait?
See, Yusuf, can you hear me clearly?
Yes.
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 Good. Thank you. See Mohammed صباح الخير.
صباح الخير. أهلا وسهلا. حلو السيشن.
الله يطول عمرك.
Okay, ma'am.
Okay. So, good morning, good afternoon, good evening. It's a real pleasure and honor for me to welcome you to the official opening ceremony of the 9th edition of the International Renewable and Sustainable Energy Conference, IRSEC'21. We have an amazing panelists in this opening ceremony. I have the honor and pleasure to introduce first Her Excellency Dr. Laila Ben Ali, who is Minister of Energy Transition and Sustainable Development in Morocco. So we have a recording from her. Unfortunately, she could not attend live. You can just
Good morning,
play the recording.
good afternoon. I'm really pleased to participate in this 9th edition of the International Conference on Renewable and Sustainable Energies. Special thanks to the organizers, MSTI, Mazen, Mohammed V, and Abdel Malik Saadi universities, and the other national and international organizations as well. The event is really timely. It's a great opportunity to highlight our actions, particularly those related to SDG 7, to ensure affordable, reliable, sustainable, and modern access to energy services. The event is also very timely. It comes just after COP26, where Morocco revised upwards its commitments in terms of greenhouse gas emissions reductions in a context of economic recovery with more than 300 post-COVID recovery measures. But let me get back to the Paris Agreement. Achieving the goals of Paris means rapid and profound transitions in energy, industry ecosystems, urban infrastructure, and all these at the same time. It cannot be done without real technology breakthrough, particularly in the area of energy storage, especially if you want to increase renewable energy to more than 70% of electricity production with almost zero coal by 2050. Solar PV modules and battery storage costs decreased by almost 90% and 87% respectively during the last decade. This was also only possible through R&D, through demonstration and deployment at scale, in addition to supportive regulations and international cooperation in trade. That's on the supply side. But the good news is demand-side management technologies usually facilitate the deployment of low-carbon options on the supply side. Morocco's commitment to energy transition is a voluntarist political choice made by His Majesty the King Mohammed VI, God assist him, more than a decade ago, through an ambitious energy strategy. This energy strategy is based on three key pillars, as you know. One, renewable energies. Two, energy efficiency. And number three, regional integration. This strategy is supported by openness to the private sector and an industrial integration. One key priority is really to improve and streamline the regulatory and institutional framework to be in phase with the rapid evolution of the energy sector and to increase our attractiveness to private investments, both national and international. Accelerating a national ecosystem of renewable energy technologies will not be possible without strengthening transparency, particularly on transaction and system costs, without access to information on investment opportunities, and without facilitating decentralized production as much as possible. Morocco decided to exceed the objective announced at COP21 by increasing the share of renewable energies to more than 52% in the electricity mix by 2030. We have 50 renewable projects today with a total installed capacity of around 4 gigawatts that are already in operation. We have more than 40 international companies from 13 countries that are active in the renewable power generation market. Since 2009, that's more than $12 billion invested in renewable energy. These projects have contributed to improve our energy independence by more than 8% since 2009. For the 60 other projects that are being developed or under construction, and the multiple others which will be financed over the next decade, my message is the return on the capital employed needs to improve. Again, through strengthening transparency, improving access to information on investment opportunities, but also through improving our integrated development approach. In line with the new development model, we want to maximize the impact on employment, to maximize the impact on education, on health, agriculture, and infrastructures to guarantee a sustainable development for the kingdom. In line with the new development model, new initiatives are being launched to accelerate our energy transition and sustainable development. For example, Morocco just adopted a roadmap for the development of low-carbon hydrogen. It has significant assets to become a key player due to its energy and logistics infrastructure and its industrial and R&D ecosystems. This roadmap targets industry, ammonia, mobility, and energy storage in the local market and for exports. Morocco also adopted a roadmap for energy recovery from biomass, targeting household, agriculture, and forestry waste, as well as wastewater. The energy potential is estimated at more than 20 terawatt hours per year. That's around half of our national electricity production today, or the consumption of a country like Azerbaijan. Morocco, with its 3,500 kilometers of sea coast, has a huge offshore wind potential that exceeds 250 gigawatts, in addition to the energy of marine currents. The country also adopted an integrated program mandating all water desalination plants to be equipped with renewable energy production units. The first integrated project is authorized this year. And also we have all industrial zones will have access to renewable energy with a total estimated electricity demand of more than 800 gigawatt hours per year. The midway review of our energy strategy also focuses on the promotion of energy efficiency in energy-intensive sectors and transport, as well as agriculture and public lighting. We are targeting an energy saving potential of at least 20% by 2030. With more renewables, more decentralized production, more efficiency, smart grids are now unavoidable, and they have to be included in our transmission and distribution investment plans. They help improve the quality of electricity supply, and they help improve the quality of targeted services. Obviously, research, development, innovation, and industrializations are essential pillars. Let me give you some numbers illustrating the expansion of R&D structures and platforms and their synergy with national and international companies, as well as our universities' ecosystem. The Green Energy Park and the Green and Smart Building Parks, two innovative platforms with $20 to $25 million each, dedicated to research and development and training in renewables, green buildings, energy efficiency, and smart grids. We also have other platforms that are being developed related to green hydrogen, to agro-energy, focusing on biomass and energy agriculture nexus, or the water energy nexus focused on desalination and water treatment, and they're all endowed by $50 million. In terms of industrial integration, a wind turbine blade plant with an annual capacity of 1,000 megawatt, as well as 3 PV module plants with 300 megawatt per year, have been set up for the local market and for exports. A thorough watching of evolving technologies, as well as win-win national and international partnerships, are necessary for successful energy transition. Morocco is an active member of all alliances and coalitions aimed at energy transition. And in this regard, I would like to cite in particular the Coalition for Sustainable Access to Energy that is co-chaired by the Kingdom of Morocco and Ethiopia to generalize access to sustainable energy, particularly in Africa. Morocco has developed an important arsenal of strategic cooperation agreements in this regard. So win-win partnerships are necessary, but they are not sufficient. They should constantly be accompanied by capacity building, by technology transfer, but also by access to the growing carbon market and ESG-related funding mechanisms and opportunities. So to conclude, I would like to underline the importance of innovation and digitalization to bring in real investment opportunities. We are on the verge of potential technology breakthroughs, particularly in the area of energy storage, which we are watching carefully. Your discussions and the intellectual property you will exchange over the next 4 days, particularly on electrochemical storage, on lithium-ion batteries, on vanadium redox flow technologies, might totally change trade balances and international cooperation down the road. They might totally change the way we plan, the way we build, and the way we finance our energy systems. That's why I'm particularly proud of the innovative space that this 9th edition of the International Conference on Renewable and Sustainable Energies offer, and I wish you all success. Thank you very much.
Thank you so much, Excellency, for the very insightful remarks. Let's move now to our next speaker, who is Professor Saifur Rahman. Professor Saifur Rahman is the IEEE President-elect for 2022. He's also the past President of IEEE Power Energy Society and an IEEE Fellow. At the same time, he's also the Director of Virginia Tech Advanced Research Institute, USA. We have a recording from Saifur Rahman because, owing to the time difference, you could not make it this morning.
Good day. This is Professor Saifur Rahman from Virginia Tech and the IEEE President-elect 2022. I will be the President of IEEE in 2023. As you may know, I was the president of the IEEE Power and Energy Society in 2018 and honored to be invited by the organizers to give my welcome message for the 9th International Renewable and Sustainable Energy Conference, IRSEC 2021. Since I am now in the US and the COVID-19 pandemic still ongoing, I'm not able to come before you in person and attend this conference with you. I would like to welcome all of you to this conference and like to emphasize that this conference is very timely as policymakers all over the world, industry leaders, academics, and ordinary citizens are engrossed in the discussion on climate change and issues on adaptability. IEEE Power and Energy Society provides a platform for discussion of such issues through our conferences, journals, and chapter-level discussion forums. PS has a dedicated conference in this field called the IEEE Sustainable Power and Energy Conference, ISPEC, which I helped to launch in China in 2019. It is now moving around other Asian cities. I hope our volunteers here will show interest to bring this conference to North Africa in the future. PS has a journal named IEEE Transactions on Sustainable Energy, where scholarly articles on sustainable energy are published. I hope some of the authors presenting the papers here at this IRSEC conference will consider publishing their work in the IEEE Transactions on Sustainable Energy in the future. The other area of focus is for PES, volunteer engagement at the local level. PES has over 260 local chapters all over the world, including one here in Morocco. I would encourage local PES chapter leaders in Morocco to consider organizing local events to bring awareness about issues of public interest among the tech community in this country. This is one way how we can give life to our motto, advancing technology for humanity. Thank you very much for giving me the opportunity to come before you and speak at this conference. Have an informative and enjoyable conference. Thank you very much.
Thank you so much, Professor Saifur Rahman. Now let's move to our next panelist in this opening ceremony. So I leave the floor to Dr. Hisham Bouskri, who is the R&D Director at Mazen here in Morocco. Mazen is a Moroccan Agency for Sustainable Energy. So Dr. Hisham, the floor is yours.
Thank you, Mr. Saidi and Ruzal. So after Dr. Laila Ben Ali, the Minister, and Professor Saifur Rahman, it is my pleasure to welcome all of you to the 9th edition of the International Renewable and Sustainable Energy Conference, IRSEC 2021, held for the second time virtually this year. So despite the digital format imposed by the COVID restrictions, the conference successfully attracted participations from over 35 countries. So this interest attests to the growing international reputation of the conference and further strengthens its position as the leading regional conference on renewable energy research. Further, there's a virtual expo, which is a proof of the bridge that is being built between academia and industry, and the IRSEC conference is a platform that serves to bring together these two ecosystems. So Morocco's leading role in promoting renewable energy sources into a significant part of its electricity generation capacity is actually operationalized by Mazen innovative approach to develop world-leading energy plants, such as the Norway solar plants. So this investment creates a positive dynamic in creating an important traction for the regional ecosystem, and this is pushing research and innovation further down the road of excellence. Undoubtedly, IRSEC is today one of the largest renewable energy conferences in the MENA region and possibly also in Africa. So it is an honor for Morocco to be behind this initiative, which constitutes an exchange platform for innovation, research, and development in renewable and sustainable energy. Every year, despite COVID, despite the restrictions, IRSEC brings together a network of researchers and experts from Morocco and beyond, and helps create these synergies that are particularly beneficial to the young researchers, which are the future of the sector. Mazen's continuous active implication in IRSEC is yet another testament to its ongoing support for scientific research in renewable energy area in Morocco. Mazen is committed to supporting market-aligned R&D initiative that accelerate time to market of relevant technologies. And I think storage has been extensively cited by our minister. Renewable energies, and in particular storage, is a fast-paced innovative sector that creates many opportunities to improve existing technologies in terms of performance, reliability, and competitiveness. And let's make no mistake about it, storage is what will make renewable energy an alternative to fossil fuels. So these opportunities can only be materialized into a large-scale technology demonstrator, such as the one that Mazen is hosting in its R&D platform in Ouarzazate. Mazen is satisfied to see that its unwavering support for the conference has allowed IRSEC to soar into new horizons. We wish the conference organizers, panelists, and all the participants a productive and fruitful virtual conference. And I would like to thank also the organizers for the opportunity to participate in this opening ceremony. Thank you very much.
Thank you so much, Dr. Razaki, for the thoughtful remarks. So let's move now to our next speaker. So apparently Professor Abdelatif Mokrim, the Dean of the Faculty of Science, could not make it this morning. So I moved to the next speaker in this panel, Professor Shahzada Ahmed, who is the Shahzada Ahmed, who is the BC Materials Basque Center for Materials, Applications and Nanostructures in Spain. So Professor Shahzada, the floor is yours.
Good morning, ladies and gentlemen. Good evening, in which time zone you are. It's my great pleasure to welcome you all in the 9th edition of the IRSEC'21. It is one of the largest renewable energy conferences in the MENA region, as Dr. Hassim has just commented about. The conference chair, I want to thank conference chair Mohammad Isadi, Professor Yusuf Jaz, dear colleagues, dear researchers, young fellows, ladies and gentlemen. I'm deeply delighted to welcome you in the 9th edition of the IRSEC'21. And we have more than 35 countries in the participations in the conferences here today. Due to ongoing sanitary restrictions, since last year it is being organized in the virtual mode. And I hope and I believe that by next edition, we will do in a 3-dimensional in-person mode. Today, the organizers have assembled a very diverse program to address the world's most pressing challenges, that is renewable. And as the minister says, the time cannot be better as the COP26 has just finished. So it's a follow-up conference we are following up. And the minister commented that Morocco is setting his ambitions higher by betting 26% more on the renewable energy. I look forward to working with ministers, because we are also ministers and Her Excellency, and we are a member at World Economic Forum. So I look forward to interacting her with more. This is to find a solution to the climate crisis. Sustainable energy conversion is the most important. And our society needs technological advances, and technological advances in terms of energy storage, in terms of energy conversion, and energy connecting to the grid. If you can see my if you can see my presentations, you will say that this is how the CO2 emissions is increasing rapidly. Last year was a little bit better due to the COVID. It was 411 ppm, but now it's back to 439 ppm. Today, we are facing one of the biggest challenges our humanity has faces in the current decades, but we don't want to repeat it. So if vaccine is important, renewable is equally important. On the right-hand side, you will see the pictures from I stole from the Time magazine. It's a very good. Renewables is very important, and renewables need all of the renewables infrastructures conversion and storage. Otherwise, energy with catastrophe will eat the fabric of our society. Most of the countries, most of the European countries has set a target to be carbon neutral by 2050. How this will happen? So how this will happen? You will see that we signed a Paris Agreement in 2016. We are still not fulfilling the Paris Agreement, and to make it fast acceleration to the carbon neutral, 1/3 of the electricity will come from the PV. 1/3 of the electricity will come from the PV. Then we have the wind, and the hydrogen as a new vector will contribute. And in the future, you will see most of the long distance trucks, vehicles will run on hydrogen. So by doing so, we will be only able to make a smooth transition. Some country will do 2050, some will be do later on, but by 2060, across the globe, we hope that we will achieve to be a carbon neutral. It's the sail sky scenario here. And for this, the European Union and many they have marked some mandates, the materials which we go that how to achieve this. To achieve these things, we need new materials, and new materials for energy harvesting like photovoltaic, CSP, wind power, energy storage. Minister just commented that vanadium battery. I'm very pleased that Minister has a very great technical details he knows about it. Lithium-ion batteries, we have to look beyond lithium-ion batteries, supercaps, fuel cells, energy storage, and make our energy buildings more efficient, because in most of the countries, heating, in some countries heating, and some countries cooling requires a lot of energy consumption. So our societal mindset is such that we care how much we earn, but nobody asks you how much we burn. So it will be our responsibility to change our mindset, and charity begins at home. So we have to be very careful how much our carbon footprint is, and we should minimize our carbon footprint in day-by-day basis. Let me finish by saying that none of us can achieve what we want alone. It is time to intensify our efforts and let not anything stand in the way for what we can achieve together. So just to give you an example, we need efficient solar cells. And when we have an efficient solar cells, we need an efficient battery to store the energy. And finally, we need a power converter for the network. So all these topics will be discussed today in IRSEC. I'd like to thank you for your active participation and allowing me to speak before you, and enjoy the conferences, enjoy the technical details and the know-how it generated. So I finish also saying that emission anywhere are a threat to humanity everywhere. It doesn't let underdeveloped countries need to be punished. Emission anywhere is a threat to humanity everywhere. Thank you all, and please enjoy the conference.
Thank you so much, Professor Shahzada, for all the thoughts you shared and the remarks. Now I'm going to present some remarks also in this opening ceremony. So good morning, Excellency, ladies and gentlemen. May I first of all express to you my warmest welcome to the 9th edition of the IEEE International Renewable and Sustainable Energy Conference, IRSEC'21, which is organized as a virtual event owing to the ongoing COVID-19 pandemic for the second time. According to the World Energy Outlook 2021 published, sorry. So according to the outlook published recently by the International Energy Agency in 2020, even while economies were strongly impacted by COVID-19, renewable sources of energy such as wind and solar PV continue to grow rapidly, and electric vehicles set new sales records. The new energy economy will be more electrified, as it was mentioned several times in the former talks, interconnected and clean. Its emergence is the product of a virtuous circle of policy, action and technology innovation, and its momentum is now sustained by lower costs. In most markets, solar PV or wind now represents the cheapest available source of new electricity generation. Clean energy technology is becoming a major new area for investment and employment, and a dynamic arena for international collaboration and competition. During the last 2 decades, Morocco, the country virtually hosting this international conference, has embraced a very ambitious strategy, as it was outlined by the former speakers, Her Excellency the Minister, Dr. Hisham. So Morocco has embraced a very ambitious strategy to tap into the amazing renewable energy potential. It has both for wind and solar power, which has already started to pay off. Excellency, ladies and gentlemen, IRSEC'21 conference has, IRSEC in general, conference has been organized on a yearly basis during the last 8 years, and has been contributing to the dissemination of key research and development research work in a wide range of areas, disciplines, and both cutting edge and emerging technologies related to renewable energies and sustainable development, coming from many countries from around the world, such as technologies such as green hydrogen, smart grids, and smart cities, to name a few. It's also an outstanding forum providing renewable energies and sustainable development and many other related fields. Experts, engineers, researchers, PhD students, and policymakers, unique opportunities for networking, discussion, and exchange. Excellencies, ladies and gentlemen, I'm very glad to highlight the fact that IRSEC'21 is held under the auspices of the Ministry of Energy, Transition, and Sustainable Development. I seize this occasion to extend Her Excellency Minister Laila Ben Ali, on behalf of IRSEC'21, our organizing committee, our most sincere thanks and gratitude for their invaluable support that has certainly a very important share of the unprecedented success of this very edition under this very special conditions of the pandemic, which this success is already incarnated by an unprecedented number of research papers, submissions from the 5 continents, and many inspiring and insightful keynotes, invited talks, and tutorials. Indeed, this success is also the result of the amazing job and hard work of the IRSEC'21 different committees, namely steering committee, organizing and technical program committees, also the keynotes and invited speakers, the technical sponsors, and all the participants. It's my real pleasure to address also special thanks to our strategic partner, Mazen, who was with us in the journey, in the long journey we have started 9 years ago, and in establishing and sustaining also this conference throughout the years, despite the difficulties and the challenges of this pandemic. It's my real pleasure to address all of them, and in particular to the General Co-Chair, Professor Zaz, and also to Professor Hibawi, to all the TPC members and all the members of the organizing committee. My most sincere thanks and gratitude for the great job they have been doing during several months of preparation of this very edition. I also wish all the participants and the guests a very fruitful and enjoyable IRSEC'21 virtual experience. Thanks you for your attention. Now I move the floor to the General Co-Chair, Professor Yusuf Zaz, so the floor is yours.
Thank you very much, Professor Saidi. Distinguished guests, keynote and invited speakers, technical program committee members, colleagues, and participants. It gives me pleasure to extend to you all a very warm welcome on behalf of the organizing committee of the 9th edition of the International Renewable and Sustainable Energy Conference, IRSEC'21. Placed under the auspices of the Ministry of Energy Transitions and Sustainable Development, the IRSEC'21 is organized by the Mediterranean Space of Technology and Innovation, MSTI, in a strategic partnership of the Moroccan Agency for Sustainable Energy, Mazen, and technical support of IEEE Power Energy Society. IRSEC is also supported by Mohammed V University in Rabat, Abdelmalik Saadi University in Tétouan, and many other organizations. As a previous edition, due to the COVID-19 pandemic, this edition is organized virtually and broadcast from Tétouan, Morocco. All participation is free of charge for attendees without paper. This year, IRSEC attracts about 220 submissions from about 35 countries. More than 40 keynote and invite speakers will present the latest advances in renewable energy and energy efficiency, organized in 6 important workshops, 4 special sessions, and 4 tutorials. The program is extended in 3 days before the opening of today and 5 days of the conference. The first workshop is lithium battery science and technology, chaired and proposed by Professor Dr. Amir Khalil from INL USA. The second workshop is emerging semiconductors for photovoltaics, proposed and chaired by Professor Shahzad Ahmed, is also the deputy chair of this conference. And with the presence of the high scores Professor Khaja Nazruddin. The third workshop is the advances in renewable resources forecasting and their economic prospects, proposed by team of Mazen. Many keynote speakers such as Andreas Kazantidis from University of Petras, Greece. The fourth workshop, sustainable energy for building and urban environment, proposed by Professor Zaid Rumani, Professor Najma Arousi, and so on. And shared by the Professor Helico Orlon from Brazil. Workshop 5, digital technologies in solar energy, proposed by Professor Saad Mutahar from INSAFEZ. We have the presence of high-level keynotes. Professor Saad Mukhlif from University of Malaysia. Workshop 6, perspectives of green hydrogen development, also proposed by Mazen team. We have many keynote and advice speakers such as Professor Jamal Shawqi from Polytechnic Montreal and Professor Tariq Shafiq. Special session on smart technology, smart grid technologies and applications, proposed by Dr. Mohammed Barara, and with the high-level presence, Professor Safur Rahman and Professor John MacDonald and Hassan Barabani from Iran. Special session to magnetic materials and devices for energy, proposed by Professor Mohammed Bali from Morocco. And special session 3, biomass and biogas energy, proposed by Professor Hassan El-Bari, and special session on wind energy, chaired by Professor Ahmed Zahid from Australia. Thanks for all organizing committee of IRSEC, namely Professor Lihibawi, Professor Hadil Benahdesh, and all team of Mazen, Muad, and so on. Thank you very much, ladies and gentlemen. You carry with you the best wishes of IRSEC organizing committee for productive and successful conference. Thank you.
Okay, thank you so much, Professor Zaz, for your remarks. Now we'll move to the workshop on emerging semiconductors for photovoltaics applications. The workshop will be moderated by Professor Shahzada Ahmed. So the floor is yours, Ahmed.
Thank you, Professor Isadi. Thank you very much. Thank you for organizing the conference. I think Professor Nazruddin will join us at 9:30. So we have a couple of minutes to wait for him because he was in another meeting.
Okay, thank you.
I think Professor Shahzad is with us.
Yes.
Okay.
We are waiting for Professor Nazruddin. I think he will join us at.
Good morning, Ahmed.
Good morning.
Okay, are you available now, or we just give you 5 more minutes?
Can we just check my screen, my computer?
Absolutely, perfect. I can see your screen.
Perfect. Okay, so I go out of my screen, and you can.
Yeah. We will wait for 5 minutes because at 9:30 we have announced your talk.
That's fine.
Thank you. So it's a great success. It's 9 o'clock, 9:30 in the morning, and I can see almost 300 participations, and many more on YouTube. So I think online is also being live. So it's a great success. So it looked like the coming generation is more enthusiastic to learn the wisdom of the people who are going to speak today.
It's you. Okay.
Okay, so we start. Good morning, everybody. It's my great, and good evening in which time zone you are. Sorry for that. Good morning, because we have many participants from China and Malaysia, also many other countries. It's my great pleasure to welcome the first speaker of this conference, and he needs no introduction. Mazen, Professor Khaja Nazaruddin, is a professor at EPFL, and his research is focusing on perovskite solar cells and light-emitting diodes. He has published more than 650 papers, which has been cited over 1,100 times with an H-index of 150. And regularly he cites among the top 10 researchers in the world who made significant contribution in the field of perovskite solar cells and dye-sensitized solar cells. His name is synonymous with perovskite solar cells and dye-sensitized solar cells, and his energy is unmatchable. I myself tried many times, but I failed, let me confess you, to match his energy and passion for science, but let me confess you, I failed many times. But I hope somebody will succeed him to working of 18 hours, contributing to the field of thin film photovoltaics or emerging photovoltaics. As a fellow of European Academy of Science, as a fellow of Royal Society of Chemistry, and recently, this year, he has been awarded Khawarazmi Award. And just this month, just to give you a short side note, just this month he published 2 papers, one in Nature Nanotech and Nature Communication. So you can imagine in 1 month he has 2 big papers coming. So his research is no boundaries. And with this, I think if you understand Arabic, so I call him Nazir, is Benazir. So if you know the meaning of Benazir, you know what it does. So he's unmatchable in his energy and his passion. With this, I think I'd like to hand over the floor to you, Professor Khaja Naziruddin. And we look forward to listening and learning from your wisdom.
Good morning and good afternoon, ladies and gentlemen. First of all, I would like to thank the organizers, particularly the chairman of this session, Professor Ahmed Shahzada, for inviting me to present or to share some of our recent progress on perovskite solar cells. I take this opportunity to thank all the organizers who has put so much efforts to bring all the scientists, top-level scientists on this floor. With this short introduction, I would like to start my presentation. My name is Naziruddin, as Professor Ahmed has introduced. This is my email address. Let me just take my laser pointer. So my email address is given in below. So if you have any questions regarding my presentation, please feel free to send an email query. I will try to answer you as soon as possible. And the title of my presentation is given here. So the tuning of 3-dimensional and 2-dimensional interface by various cations to afford efficient and stable perovskite solar cells and modules. In my today's presentation, what you will see is how you can stabilize the perovskite solar cells, how you can improve the efficiency of the modules to close the gap between the small cells and the modules, as the title is shown here. So I'm working at EPFL, and I would like to start my presentation. I also have an affiliation at Korea University, King Abdulaziz University. So this is our campus, which is very nice, beautiful on the sides of lake. And this is the whole campus. And here what you see is our library, learning center. And this is our big Congress center. Unfortunately, it is not active now because of the COVID. Now I come back to my presentation. I would like to bring you a perspective between the perovskite solar cells and silicon solar cells. So on the right side, what you see is our perovskite solar cells, where we are having three main components. One is an electron transport layer on which we deposit three-dimensional perovskite, and followed by two-dimensional perovskite and whole transporting material. So these perovskite three layers, they are efficient and they give you very close to 25.5% efficiency, similar to silicon solar cell efficiency, which is 26.5. However, the processing of perovskite solar cells are a solution process, very easy to fabricate. On the contrary, if you look at the silicon solar cells, it's energy intensive and it needs a huge amount of heating, 1400 degrees temperature, where we bring the metallic silica and then we have to melt it and make it ingots and slices. So this is a highly energy intensive process. On the contrary, perovskite solar cells we can fabricate at 120 degrees temperature, and they are as good as silicon solar cells. And these materials are highly absorbing. At the same time, they are highly emitting. As you can see from here, when we apply voltage, and you can see the light coming out because of the perovskite solar cells are highly emitting material. So these are the dual application materials in one material. So what is the perovskite material actually? This is a very old material, discovered 100 years back. It has a common formula of ABX3. A is an organic cation or inorganic cation. Cesium, methylammonium, formidinium. We are developing new cations with other substituents. And the B is a lead and tin. Tin is a very interesting candidate, but unfortunately, it's not very stable. So all our focus is based on lead 2+. And X is a halide. It starts from chloride, bromide, iodide. Mostly we are using iodide because it absorbs all the visible light. So this simple formula consists of very interesting properties which are highlighted here. They absorb strongly in the whole visible region. The tunable band gap, you can see in the next slide. The band gap can be tuned by changing the cation or by halide. And when you shine the light on these materials, you form the exciton, and this exciton binding energy is extremely small. So these are very interesting properties of this material. Because of that, we are getting such a high efficiencies. And the absorption spectra, as I mentioned, it has a huge absorption in the whole visible region, spanning from 400 nanometers to up to 820 nanometers. And correspondingly, you can see the emission coming from this material, which is around 780 nanometers. Another interesting property of this material is the sharp onset. Because of this sharp onset, we can use these materials in combination with the tandem silicon or CIGS perovskite tandem configurations, where very recent data coming from Berlin group is 29.8. So there is a possibility that one can reach 30% efficiency using silicon perovskite solar cell, tandem solar cells. But in this talk, I will be presenting only the perovskite solar cells and their stability, improvement of their stability. So the solar cells, perovskite solar cells has a different configuration. So this is the crystal structure of the perovskite materials. On the B, this is the configuration, which is typically called NIP, NIP mesoporous structure, where we are depositing compact layer of TiO2, followed by the mesoporous layer of TiO2, infiltrate perovskite on the top, and then whole transporting material. So the light is coming from the transparent conducting glass side. So this is called NIP configuration. And this NIP configuration can also be without mesoporous layer. Then it's called planar NIP perovskite solar cell. So what we are having is a compact layer of TiO2. Then we have a absorber layer and spirometad. On the contrary, if we deposit first whole transporting material on the transparent glass side, followed by the perovskite and the electron transport material, this is called PIN configuration. In my talk, I will be focusing only on NIP configuration. on the left side, what you see is a cartoon of various layers which we are depositing. On the right side, a cross-sectional image of our perovskite solar cell. So we are having a conducting glass, that's FTO. We deposit a very thin layer of compact TiO2 oxide layer. Then we deposit mesoporous TiO2, it's a very thin layer, followed by a tin oxide. You will see towards end of my presentation, the purpose of depositing tin oxide on top of TiO2. Then we deposit a triple cation or double cation perovskite absorber layer between 600 to 700 nanometers thickness. Then if you can see that there is a very thin layer of a overlayer, which is deposited by phenyl ethyl ammonium iodide 2-dimensional perovskite. Followed by we have a whole transporting material, which is typically 160 to 200 nanometers thickness, and then contact gold. So this is a NIP configuration. And this configuration, very recently, we got a 24.3% efficiency, which is certified at Newport. This work will appear hopefully Nature Energy. So that this is a certified efficiency from Newport. And when we have these mini modules based on this configuration, we obtained 21.7% efficiency. Now we have a very recent data which goes up to 23%. You will see in my presentation. Once if we have these small mini modules, which we integrated into a mini panel, having a A4 size paper, that's a 23 by 30 square centimeter, 30 centimeters. And this is a working mini module in our lab. So it's everything is fine, but what are the problems? So if I highlighted perovskite solar cell efficiency reaching 25% efficiency, silicon solar cell efficiency I'm comparing here, and tandem efficiency, as I mentioned, is 29.8. And the energy payback time, this we can, if somebody is interested, I can provide you all the information. It's less than 2 months for the perovskite solar cells. What is missing in perovskite solar cells? It's a stability. Now, how can we improve the stability of the perovskite solar cells? That's a topic of my presentation. So here I have highlighted the possible approaches of increasing the stability by interface engineering. You will see in my presentation how we are attempting this one. Phase engineering of perovskite layer. Now, perovskite is even though it's a very simple composition, but it has a different phases, alpha, beta, gamma. And all these phases, alpha is the one which we are very much interested, which absorbs all the visible light from 400 to 820 nanometers. How can we stabilize alpha phase with additives? That's what we will see in my presentation. And the development of charge transport materials here. Today, I will be presenting on the electron transport material. In fact, we have a very big research topic on organic whole transporting materials, particularly dopant-free, which I will not be presenting. But if somebody is interested, you can contact me. I can discuss later. Now, I come back to the interface engineering. The one of the way we have attacking this problem is we deposit 2-dimensional perovskite on top of 3-dimensional perovskite. How do we do that one? When we are depositing the 3-dimensional perovskite, invariably, try to remember, invariably, we have a 10% excess of lead iodide. When we have this 10% excess of lead iodide, when we spin coat a larger cation, is shown here. These are the possible cations. But in this case, I'm taking only one example, phenylethylamine, which is shown here, phenylethylamine cation. When we deposit this phenylethylamine cation on top of 3-dimensional perovskite, the leftover lead iodide reacts with this cation and forms a thin layer of the 2D perovskite. Now, what are the properties of the 2D and 3D perovskites? And as I mentioned before, 3D perovskites, they absorb the whole visible region up to 820 nanometers. On the contrary, if you look at the 2-dimensional perovskite absorption spectra, they absorb only a small portion of the visible light from 400 to 500 nanometers. However, the difference between the 3-dimensional perovskite and 2-dimensional perovskite is the 2-dimensional perovskites are extremely stable, but the efficiencies are very low. On the contrary, 3-dimensional perovskites power conversion efficiency using these materials are extremely high, but the stability is relatively low. So why don't we combine 3-dimensional perovskite and the 2-dimensional perovskite and get the benefit of high efficiency and high stability? That's what you will see. But if you look at the 2-dimensional perovskite, because of this cation, and the three-dimensional perovskite structure is shown here, the unit structure. When we increase the size of the cation is going into the cavity of these spaces. When we increase the cation size, we splice this three-dimensional perovskite into layered perovskite. Now you have an opportunity to tune your two-dimensional perovskite layers. If you required n equals to 1, that's a 1 layer. And if you look at required n equals to 2-layered perovskites. So you can control the morphology, film thickness of these perovskites by controlling the ratio between the larger cation and the smaller cation. And the other interesting property of this two-dimensional perovskites, they have a characteristic XRD pattern, which is in the range of around 6 to theta. And these are the, so if you look at the green line, this is a pure two-dimensional perovskite. Corresponding absorption spectra is shown here. Now, if you look at the black line, that this is absorption spectral properties of the three-dimensional perovskite, and the three-dimensional perovskite has a characteristic XRD peak around 14.7. Now, if by combining three-dimensional perovskite on the then two-dimensional perovskite, the absorption spectral features are shown. This is the red line. Now, you can see that the characteristic XRD peak of a two-dimensional perovskite, which is around 5, and then followed by 14.7 is intact. So that shows the presence of three-dimensional and two-dimensional perovskites on one each on the top. Now, the other way of characterizing these materials is, since the two-dimensional perovskite has a characteristic high luminescence in the visible region around 520 nanometers, if you excite from the top side 450 nanometers, so this is our typical configuration, exciting from the top side, it gives you the emission related to the two-dimensional perovskite. So here the formula is cesium, formidinium, methylammonium, lead iodide, and bromide. So triple cation, double anion perovskite structure. So if we have a two-dimensional perovskite on the top, you see clearly the presence of the two-dimensional perovskite peak. And if we don't put the two-dimensional perovskite, then you don't see any two-dimensional perovskite emission, but only you see the three-dimensional perovskite emission. On the contrary, on the two-dimensional perovskite, layered perovskite, you see a dominant peak coming from the two-dimensional perovskite, very small peak coming from the three-dimensional perovskite, demonstrating that the thickness of the two-dimensional perovskite is in the range of 50 nanometers. However, if you illuminate these two structures, one is a reference without two-dimensional perovskite, with the two-dimensional perovskite, from the bottom side, you see that the two emission spectra are overlapping, also demonstrating that the two-dimensional perovskite layer is remain on the top of the three-dimensional perovskite without penetrating into the bulk of the perovskite layer. So what does it gives you the power conversion efficiency and advantages? And if you look at the XPS data, based on the XPS data, the binding energy, the energy level scheme is shown here, the Phi panel, the central panel, where the perovskite HOMO and then the two-dimensional perovskite HOMO is well aligned compared to the spirometad, which is slightly above the energy. So when you excite the perovskite, so the positive charges are tunneling through the two-dimensional perovskite into spiro. However, the electrons, because of the LUMO level of the two-dimensional perovskite, which are significantly high in energy, so the electrons are not tunneling and the electrons are driven towards the electron transport layer. So in other words, we are reducing the recombination at this interface between the perovskite and then the whole transporting material. And if you look at the data based on the VOC, it's a VOC of 1.09, that's the reference sample, and 1.14 with the two-dimensional perovskite. So the power conversion efficiency of two-dimensional perovskite containing cell gives us 20% efficiency. The optimized perovskite solar cell with the 3D and 2D 20.75. This is at the time of 2018. Now today we have further modified this cation, that's a phenylethylamine. To before I go to the new cations, let me just show you the stability data of this new cations deposited on the perovskite solar cell, three-dimensional perovskites. So here we see the red line, that's based on two-dimensional perovskite deposited on top of three-dimensional perovskite, and the black line demonstrates without any two-dimensional perovskite stability over the period of 800 hours. within the red lines, we have two categories, that's a blank and filled. The blank one is under argon atmosphere, and the filled one are encapsulated with a sealing and measured under outside conditions. So you can see one is under pure argon atmosphere, another is encapsulated. In both the cases, you can see clearly the enhanced stability compared to the reference sample. So now coming back to the new cations, so instead of just phenylethylamine, we removed one proton and then incorporated fluoro group on the phenyl, and in another cation we have replaced all the protons and inserted fluoride groups. So it's called fluorophenylethylamine, pentafluorophenylethylamine. So these are the two cations, and these two cations we developed two-dimensional perovskites. Their absorption spectral properties are shown here. The green one is the fluorophenylethylamine two-dimensional perovskite absorption spectra, and the purple one is the pentafluorophenylethylamine two-dimensional perovskite spectra, absorption spectra. Now, when we deposited these two cations on top of three-dimensional perovskite, the black line is a pure absorption spectra of the three-dimensional perovskites. The blue is with the fluorophenylethylamine, and the red is a pentafluorophenylethylamine two-dimensional perovskite deposited on top of three-dimensional perovskite. So this work is published in 2020 Advanced Science. You can see the more details there. Now, if you look at the data, the black one is the reference sample without any two-dimensional perovskite deposited on top of three-dimensional perovskite. So if you focus the VOC, it's a 1.09, and the power conversion efficiency is around 20%. Now, when we deposited fluorophenylethylamine as a cation, two-dimensional perovskite cation, the efficiency increased from 20.2 to 21.3. And if you look at the VOC, it increases from 1.09 to 1.13. Further, if we added pentafluoro on top of three-dimensional perovskite, that's the efficiency increased from 20, that's a blank reference sample, to 21.65, and the VOC from 1.09, the reference sample, to 1.15. And in addition, if you look at the stability data of the reference sample, which is decreasing significantly over the 1000 hours, when we deposited fluorophenylethylamine cation, that's the blue line, and the red line is pentafluorophenylethylamine. So the stability is significantly enhanced over the 1000 hours of period. Now, if I go back to these two-dimensional perovskites, now you can imagine they are deposited on top of three-dimensional perovskite in plane with the three-dimensional perovskite. Since these organic cations are non-conducting, so we suspect that there may be issues of charge extraction. So what we have developed is a pure organic cations. This is totally accidental discovery. So here are the two other types of cations. That's a para ethylamine substituted on the benzene, and the ethylamine substituted on the meta positions, ethylamine substituted on the ortho positions. Now we want to see the formation of the two-dimensional perovskite using these two cations in these cations. Now this is the reference sample. That's a phenylethylamine iodide, and this gives you a two-dimensional perovskite. This is corresponding luminescence peak. And now if you take the para, that's this cation, we do form a two-dimensional perovskite. On the contrary, when we use meta or ortho cations, we don't form a two-dimensional perovskite on top of three-dimensional perovskite, as shown here, based on the luminescence properties and XRD peaks. So this is quite interesting. As I showed before, when we illuminate from the two-dimensional perovskite side, we clearly see the emission. And that's only possible with the para. Meta and ortho are not providing. So what happens is, when we have these organic cations, they are also passivating the three-dimensional perovskite, and the defects on the surface and even the deep defects also getting passivated by these two cations. And this work is just appeared in Nature Communications. So here we have the power conversion efficiency measurements using a control sample, that's the blue line, IV characteristics. The ortho is the best one, which is the red the curve. and the meta is the orange one, the para one is the gray color. And the IPC spectra of the control and ortho, the cation is almost identical. Now, the power conversion efficiency using this ortho diethylamine phenyl cation, just cation, there is no two-dimensional perovskite here. It gives us very close to 24% efficiency. In the reverse scanning and forward scanning, it's a 23.27% efficiency. So these are the IV characteristics of using this orthophenyl diethylamine cation. So here is the tabular form of the data, which compares between the blank, ortho, the para, meta, and ortho. Now, using these cations and the same composition, we developed modules. So these are the typical our module size, which is 7 by 7 centimeters. So we have 9 cells together with P1, P2, P3 scribes in order to get the current flowing in one direction. So here is the power conversion efficiency 21.36 using this type of cation as an interface modifier. And the stability when compared to the blank is shown here for 1100 hours. That's a red is with the ortho cation deposited on top of three-dimensional perovskite. The blue line is the control. Now, phase engineering, as I mentioned before, is quite interesting to improve the stability of these materials. So here what we have done is, so how do we stabilize? So the way we have approached here is doping with ionic liquids. The ionic liquid name is given here, highlighted with yellow. 1,3-bis cyanomethyl imidazolium chloride. This is a chloride salt of imidazolium cation. With the cyanomethyl groups are functional groups. So the purpose of this adding these functional groups is to coordinate Lead2+ so that you form a initial nucleus using these ionic liquids. And in addition, we have also used methylammonium chloride as an additive. So using these two components in the perovskite composition, we can reach very high efficiencies, 24 with a smaller cell area, with 21.1 square centimeters, 23.4. So this efficiency for such a small area, that's a 21 square centimeters, is one of the highest in the literature. So this work will appear very soon. And what happens when we use, this is a control, that's a surface images of the control film on the left side. As we increase the ionic liquid concentration from 0.2 to 0.6 to 0.1, 1.4, you can see clearly the enlargement of the crystals formation and crystal growth. And on the bottom, you can see the cross-sectional image of these cells. So the certified efficiency at 24, the certified efficiency was 23.4. That's a module efficiency using 21.18 square centimeters area. So this on the left side, you see the cartoon, and this is a cross-sectional image of our perovskite solar cells. And this is a maximum power point tracking. And the power conversion efficiencies are shown here, which is certified at Newport. Now I come to the charge transport, the materials, development of charge transport materials. As I mentioned, we have three important layers. One is the electron transport layer, absorber layer, and hole transporting materials. Hole transporting material I'm not discussing. Absorber layer, we have showed the phase engineering. For the electron transport materials, most of the people, they are using TiO2 nanoparticles. If you look at the figure A, so we are comparing the two types of electron transport materials. Nanoparticles of TiO2, this is a commercial sample from various source suppliers. Now we have synthesized in our lab the single crystalline TiO2 nanocrystals. This is having a typical size of 4 to 8 nanometers. So single crystal TiO2 nano materials compared to colloidal TiO2 nanoparticles. So by using this single crystalline TiO2, the purpose here is to enhance the conductivity of the electron transport layers. Thereby, we increase the fill factor. So this is a typical perovskite which we have used by using this phase engineering. Spirometad is still our material, and the power conversion efficiency, again, we reach 24% efficiency using this new electron transport material. But the beauty of here is, if you look at the fill factor compared to nanoparticles, which is 81%, and here we are having a 85% fill factor against measured in Newport. So the purpose of here increasing the fill factor is by using nanocrystalline TiO2 material. So the power conversion efficiencies are shown here, and here is the sun intensity versus VOC. Again, we made a modules efficiency, and these modules are shown here. Again, we have used the P1, P2, P3 scribing to increase the voltage. These are the mini modules which I have shown you before. So the active area is today, now it's at 24.63 centimeters square. Now I come back to the another approach we have taken, electron transport layer TiO2 and the perovskite. We have issues where the delamination is one of the problem with the TiO2 as an electron transport layer. So by incorporating a tin oxide on top of TiO2, we can diminish this effect and increase the stability of the perovskite interface. So if you look at the stability of one of the perovskite solar cell with pure TiO2 as the electron transport layer, and then followed by when we use a pure tin oxide, that's the stability is the red lines, which is overlapping with the blue dots, and the blue dots are the TiO2 followed by tin oxide ETL layer. So this gives us an enhanced stability by improving the interface between the perovskite and ETL layer. So with that, I come to the conclusions. So the 2-dimensional and 3-dimensional perovskite composition delivers exceptionally and gradually organized multi-dimensional structures at they are very stable. The ionic liquid which we have developed, cyanomethyl, this is a coordinating ligand with imidazolium, that's called functionalized ionic liquid, binds to the lead-2+ and forms a very nice crystals in presence of methylammonium chloride. And the purpose of using methylammonium chloride and chloride salts are to slow down the crystallization process so that the crystal growth is significantly improved. So we have developed single crystalline TiO2 nanoparticles for narrowing the scalability gap towards the stable and efficient perovskite modules. With that one, I would like to thank all my PhD students, postdocs, and the collaborators who are helping us with this. I would like to go to the financial the contributions, the Swiss SNF, Solaronics, and Swiss Luxembourg project, and US Army project, Toyota Japan, Panasonic, and Avengova and European projects, QNNF projects, Kiri project. And I would like to thank my group members and thank you all for your for listening me, and I will be happy to answer your questions.
Thank you very much, Professor Naziruddin, and especially thank from my side for being perfectly on time. Now the talk is open for the questions. We have some of them. Is it being asked in the Q&A section, or we will take the question at the end of all the talks today? Yusuf.
Yes, I think after the next two keynotes,
okay,
we will be at some discussion.
Thank you very much. Thank you very much. Thank you again, Professor Khader Naziruddin, for your very illuminating talk. And now it's time to move to the second talk of the day. It's Professor Sanjay Mathur. And Professor Sanjay Mathur is a professor at University of Cologne. Professor Mathur's expertise is building bridges between organic and inorganic chemistry and making new materials for energy applications. And he's also a visiting professor at Japan, a Spark faculty, IIT Madras. He has authored over 500 SCI publications, fellow of the European Academy of Science, academician of World Academy of Ceramics, chair of Material Research Committee. Last year, he was awarded R.C. Mehrotra Lifetime Achievement Awards, and he runs a very diverse group on inorganic chemistry, organic chemistry, materials, and devices, and his incoming president elected of American Ceramic Society. Professor Mathur will speak today, efficient photon harvesting technology for energy application. Since his diverse research area is very diverse, so I requested him to touch the topic of both photovoltaic as well as photoelectrochemistry. So he is going to be a speaker on both this topic today. Professor Mathur, the floor is yours. With this, we are looking forward to listening.
Thank you very much, Professor Ahmed. And also, I would like to thank the organizer of IRSEC and especially you for inviting me. I mean, we just heard this fantastic presentation by Professor Nazaruddin, who's a good friend. And it's very difficult to speak after him. I think people will agree to this. As it was mentioned, that I will be talking about something which is a little bit of different, but obviously here also photons are involved. We have seen what photons can do in terms of reactivity, stability. You can have all kinds of reactions going on when you have photon being absorbed. And this is what we have seen in the stability issue of the perovskite, which is still a kind of unsolved problem, which we'll be discussing definitely in the discussion afterward, because I think we can learn a lot from the EPFL group. But then there are obvious fundamental challenges, and I was very impressed to see that at the core of this science is chemistry, materials chemistry, which is actually helping to pave the solution. And I think this is a very big message. I was impressed how many people are attending this conference, because this is the message we have to communicate, that chemistry and material science are also going to provide the solution for bigger problems like climate change and environmental pollution and all those things, that the engineers, material scientists and chemists are not only polluting, but they will also be the people who will be providing solution. So with this, I would like to briefly talk about what we are doing in Cologne. I think it was already mentioned, we have a group of materials chemists, and that's why I would like to briefly show you what we are doing. Our interest is not only in a particular class of material. We do in general ceramic science and engineering. That means we take ceramic powders, functionalize them. They can be used for 3D printing. We shape them as fibers by electrospinning, multi-nozzle electrospinning. I will be showing a few examples. We do sensors, batteries, and one of the interests is on catalytic converters, because by using 3D preforms, which can be, for example, fabricated by additive manufacturing, 3D printing, they can be functionalized for all kinds of catalytic application, whether it's the conversion of CO2, or whether it is just the decomposition of soot particles which are coming out of an inefficient combustion process. And also we have interest in very simple reaction of water splitting that we all know for several years. And I think in every introductory class at university, this is one of the experiments that we see, that water can be split into its counterparts or in complementary parts, hydrogen and oxygen. And if we can do it more efficiently. And I mentioned we also have activity in the lithium-ion batteries, and then meanwhile we have also been working on magnesium sulfur batteries. So it's a little bit of diverse portfolio, but the core is always the chemically processed materials. So we always try to tune the processing. We are always interested in making materials compatible with the process. So that is where we, for example, for all the applications that we have seen also in photovoltaics, when it comes to perovskite, we know that there are several components. It's the electron transfer material, it's the hole transfer material, it's the absorber and the electrode, but they all have to have a compatibility, because we are looking at multi-materials junction. And as it was shown by Nazir, that it's ultimately the surface chemistry, interfacial chemistry, that you can tune by having a nanocrystal with a single crystal, for example. So the same can be done by adding interadhesive groups, interadhesive layers, by gradient films, by changing the interfacial dipoles. And this can be done by combining, for example, a molecule to a ceramic particle. And these functional particles, they allow you to make dispersions also with high solid fractions that can be used as functional inks. And they can be used for a number of applications. This is a European project on energy harvesting from mechanical energy. So in every car, we have several sensors, and the mechanical vibrations, not only in an automobile, but in any machine which is working, you have mechanical vibration when things are operating. And this energy can be converted by the piezoelectric materials. And if you can make them, the project here is on lead-free piezoelectric materials. And this has led to also a new kind of catalysis, like you can combine photo and piezo. So you can, in fact, make materials which are going to activate the photocatalysis, because you can now create in the material, like piezoelectric, you can have transient dipoles, which will then allow you or enhance the capability of that material for charge separation. So these are fundamentally new areas where we need a lot of new materials chemistry, and this is where we are working. Now, just to give one example, and then I will move to the talk, is that we have just seen how important is the chemistry of the precursors. Like in hybrid perovskite, by changing the size of the group, you can go from three-dimensional structure to two-dimensional structure. Same as I want to show you with this simple example. We have a large cluster here on quantum matter and materials, and one of the material for quantum technology is bismuth selenide or bismuth sulfide. And just by changing, you see here there are two precursors. One is a bismuth sulfur compound with isopropyl group, and the other is tertiary butyl group. So basically, not big change. Bismuth is 3+ in both cases, and you have 3 anions. Now, if these thiolates are changed just in the organic periphery, where you move from 3 carbon to 2 carbon, you have an entirely different chemistry. Because by doing so, you are changing the dipole in the molecule. That means the electron density between bismuth, sulfur, and carbon is now differentially distributed. So in one case, in the case of tertiary butyl compound, you get what is needed, bismuth sulfide. But in the case of, because of this polum, you have in the bismuth sulfur isopropyl compound, you get bismuth zero. So this fundamental difference in the molecular chemistry changes the complete properties of the material. That is something that's a driving force in our group. And we do this by making libraries of precursors that can be used for all kind of applications, sol-gel, CVD, or we do a lot on atomic layer deposition, which is also used for perovskite. We do work on perovskite as well. I will be talking towards the end. And this is supported by a startup company that we have started in 2018. So many of these companies are using the precursors or getting some kind of R&D joint project with us. With this, I come to the announced topic that this simple reaction, and a lot of people have worked on it, and it is still an ongoing topic because the focus in Germany is in a big way on hydrogen technology. And since Siemens has started seawater electrolysis, there is a renewed interest in also bundling the resources on what has been done in hydrogen. So we have the national priority programs on this, and we have coordinated also a European project on that. Simple reaction of, and then this is the vision that can we take seawater, which is having a lot of electrolytes, and use it as the source for hydrogen. Can we use electrons or photons coming from sun as the source to drive this reaction, which is thermodynamically it has to face an activation barrier of 1.23 volt. Now, it's well known. I'm just quickly going through because I see there are a lot of students and younger people also. So hydrogen is an energy source. It is very abundant. The only thing is it is very reactive, and that's why it's not appearing free in nature. So that means if you have a source of hydrogen, you have to store it. Otherwise, it will react with something. And there is a complementarity in the hydrogen can be converted into electricity, and you can use electricity to produce hydrogen by electrolysis, for example. So this is making the production of hydrogen from naturally abundant sources, a catalyst which is abundant, not one of the critical material, and a source like seawater, which is abundant as well. We do need desalinization technique for making drinking water available to the whole world, but seawater is still more than 95% on the planet. So we still have a huge source of. Now there is a trend. The market of hydrogen is over $150 billion. And this has been a challenge for many years, that you are facing the problem of competing costs, like the electrolysis, which is done commercially, mostly with the sweet water, gives you hydrogen in $3 to $4 range per kilogram. That includes the production, storage, and saving. That means on dispensing. And this is where people have come up with new ideas like the microgrid techniques. or using one of these is the solar hydrogen production, where you can use solar light in combination with electrolysis to have a electrochemistry involved there. So you can have a photo absorber which is giving you a certain amount of photo voltage, and the rest can be supplied by, for example, a photovoltaic module, so that you have an efficient production of hydrogen by splitting water. And this hydrogen economy is obviously requiring energy loop. So there was a discussion because this topic was there for almost 20 years. And then people thought that, oh, the dream of hydrogen is still over, but I think it's no longer a dream, because if you see, as I mentioned in the beginning, that seawater electrolysis for large-scale hydrogen production is, you go on the website of Siemens, you will find that they are now into this. You look at the Bosch, which is again a German company, they are producing fuel cells. And fuel cells, they are actually just the reverse of the photoelectrochemical cells. So this technology is so complementary to hydrogen production. And I think the value chain has to be extended. How can we use this hydrogen, which is coming out of an electrolyzer, for a value-added product? Can we add to the calorific value of hydrogen? And this is where the whole energy discussion is going. Now, in terms of chemistry, it's a very simple reaction. I'm not going into the fundamentals, but you have two reactions. One is the reduction of the protons and the oxidation of the hydroxyl radicals that you are producing. And for this, in any material, in any photocatalyst that's absorbing photons, you want to absorb entire range of the electromagnetic spectrum. Not only looking at, for example, the prototype catalyst titanium oxide, which is obviously having a large band gap and suitable for UV absorption, but you want to harvest something between 400 to 800 nanometer, the visible range, like chlorophyll is doing. So you need material which have an absorption maxima in this range. And for this, there are certain factors. One is the maximum achievable photodensity. So this is something which is that how many photons are then absorbed and converted into electrons. Second thing, which is very important, that material should have an efficient charge separation and transport properties. Because if the charges are reduced, and if the exciton diffusion length is too short, and they are combining or recombining at the grain boundaries, then you don't have an efficient chemical reaction on the surface. And then obviously the catalytic efficiency, which depends on how your chemical topography of the surface is, how the surface is designed. And this is where I will show you a few new examples of how to do that. Now, in terms of cost and stability and efficiency consideration, that's a huge experimental space. It's a three-dimensional space, as you see in this diagram. You are talking about highly efficient. Then you have to see the applicability, which is the maturity level of the material. At what level you can get it? Can you source it from industry? And what is the stability? So there have been different areas people have worked. This was the work that John Turner and others have done at NREL in the US, where people have looked at 3-5. And then there was also activity in Canada on this. 3-5 semiconductors are very good for splitting water, but they are obviously expensive. So a large substrate will cost you several thousands of dollars. Then there was an interest in oxynitrides, mostly by Domains Group in Japan, because people realized that if you substitute nitrogen in oxide lattice, you obviously increase the overlap of the orbitals. So you are changing the electronic structure and also the electron mobility. So you have a higher conductivity, but here the problem is of the long-term stability, because the oxynitrides are in between the nitrides and oxide, but they slowly tend to move towards the more stable oxide. Metal chalcogenides are obviously interesting because of their high electrical conductivity, and a large number of these have been tested as good absorber and good catalyst, but once again, we have the stability issue. So the area which is now of interest is the metal oxide. For obvious reasons, metal oxides are stable, but they are not free of limitations. I mean, they have the problem of low electrical conductivity, which is intrinsic. And then also for a lot of these oxides, the diffusion length for the charge carrier is too small. So if you make a thicker film for having a good absorption cross-section, then you will have a lot of recombination. So the overall efficiency is very low. Now, one compound and one material which we have been working for a long time and is on iron oxide. And this is for simple reason, it has the right band gap of around 2 electron volt, depending upon what kind of phase you have and what whether it's a combination of two. You sometimes have an amorphous iron oxide as well, which is helpful in also absorbing water molecule. But as I mentioned, it has the limitation of short lifetime. It's only in picosecond. Diffusion length is also not very big, 2 to 4 nanometer. So overall, the lifetime of photo-generated charge carrier is low. And that's why it's important to structure this. I'm just showing it because this is where we started. We have done this by CVD. You can make them large scale. This was done with Siemens, so they have tested it. And here you have the first compromise. If you make it, there's the typical thick color, thick film, which shows the color of hematite, this reddish brown color. This film is too thick. I mean, it is not giving you a good photo conversion efficiency. So the optimal is somewhere around 300 to 500 nanometers. And this film is almost transparent. So you lose a lot of photons because you have a good transmission here. So that compromise has to be, but I'm just summing it up at this point that this has been done. We have now made iron oxide and we need a top layer so that there is no back channeling. I mean, the electrons or the holes which are on the surface, they don't migrate backwards into the substrate, which will again lead to recombination. So for that, we need a blocking layer, and this is a thin titanium oxide layer. And this has been done by a combination of CVD and ALD to make these laminates of 2 oxides, like we've seen also in the previous talk on tin oxide and titanium oxide. And this gives a quite good efficiency. Obviously, what we cannot forget, and this is something that is also intrinsic to every material like the perovskite we have seen, the boundaries or phase boundaries are living materials. So they do interact because of the defects, because of the differences in chemical potential. You do have migration. And we have done intensive work here on looking at the DFT calculations of these phase boundaries of titanium oxide and iron oxide. And if you deposit it on a substrate like FTO or ITO, which is generally used as conductive substrate, you do see the penetration of tin into your absorber layer and from absorber layer on the blocking layer. So you, at the end, have an electronically coupled junction of titanium doped iron oxide as the middle layer, and a tin doped iron oxide. And this has to be kept in mind because this is also important for the long-term stability, because over the time it changes. So we have looked at in detail. Siemens has done this. They have done also cost calculation. We have seen that actually the cell efficiency is the key. So we looked at 10 by 10 square centimeter cells, and by doing a calculation on a farm which will have maybe 100 by 100 meter area, we come to almost €7 kilogram per kilogram cost for hydrogen, provided we can have a photocurrent of 10 milliampere per square centimeter. And this is doable, this is possible, this has been shown. And the issue here is that because of the seawater that we are using, you do have production of chlorine and you do have corrosion of this. So we realized that our PEC demonstrator was slowly corroding because we had to, if we are using a metal as a substrate. I'm not telling you all the details of the story. We had to go from the FTO and ITO to a metallic substrate because these are more economic compared to the other substrate which are used for publication. They cannot be afforded for industrial production. So we went to thin metallic films, and they had to be drilled because otherwise the gases will not diffuse into chambers. So we had to, and you will have a lot of hydrogen and oxygen in one chamber, which will lead to then oxy-fuel. So all these problems have been, and they are still going on. We have scaled it up because CVD and ALD, thin film processing, is not the way to go. You need something, and we made this, and you can see here bucket-wise, large amount of catalyst was made, and this can only be sprayed. You need something which can be used as a solution, and here again you need chemistry to make a suspension of the ceramic materials, which then can be applied on large area surface, as you see here, 1 by 1 meter. Now, the bias-free solar hydrogen dream is not realistic, because right now there is no material which will give you the amount of photovoltaic which is needed. So you need a combination, and people have come up with these. This has been shown. 2 years ago, there was also an open call of the European Commission and saying that if you can show a bias-free hydrogen oxygen, this was a call for 5 million euros just to, but they wanted that it should be purely solar driven. There is no external bias. But it is not possible that we know because of the materials that are at hand. And I showed you in the beginning that this is either the cost, but if you want to have a device which will run for hundreds of hours and in a self-sustained mode, you need new materials. So this transition of going from left, what you see of this electrolysis or electrolyzer that you can procure, which gives you a permanent or continuous supply of hydrogen, to something which is totally bias-free, just taking a semiconductor, immersing it in a simulated seawater, it's a saline water, 0.1 molar of sodium chloride, and then applying photoelectrolysis to have hydrogen. So this is a way to go, but it needs new materials. And I just mentioned that this processing of old materials is an important, because they are effective, they are abundant. The only thing is the efficiency is low. And that's what I would like to show in the next few minutes. So first thing that we have done here is that how can we create new phase boundaries to have both a high absorption of water molecule and at the same time having high transport. So for this, we have come up with this concept of crystalline amorphous junction, similar to something which I will not compare it, but I'm saying the analogy is to PN junction in semiconductor material. Now, having a junction where you have a compositionally homogeneous material, so it's the same chemical composition, but you have a structurally different material. It's amorphous, it's disordered. So by doing so, you change the work function of these two materials. And this is driving, for example, charge separation. And this has been done by DFT studies by Dr. Choi, who is a group leader in our group, doing this computational chemistry work. And he has shown in several of his publications that by having these amorphous crystalline junction, you have a higher activity of the surface. So how to realize it in a real device? So what we did is, we have taken these amorphous films, which can be deposited by plasma-enhanced CVD, and used femtosecond laser. So by using this laser, you can structure these surfaces, as you see here. Now you have domains of crystalline iron oxide close to or adjacent to the amorphous iron oxide. And these kind of structure are good both for light absorption and catalysis. So this tandem property is very helpful, and now this can be embedded. So it is an embedded functionality. It's a buried functionality. You can cover it with the top layer, a hermetically sealing layer of titanium oxide. So this is one way, and we have shown that if you use higher laser power, you can convert iron oxide, which is well known for transition metal oxide, that if you heat them locally, they tend to eliminate oxygen. So you can convert hematite into magnetite, and by doing so, you again create these kind of interfacial dipoles. And these dipoles are also sustaining the cycle of reduction and oxidation of iron 2+ and iron 3+ center, which are essential for splitting water or hydrogen reduction, proton reduction on the surface. Second thing that was, and I think this was a publication by Michael Gretzel on that, if you have anisotropic, this was of Lionel Vazier, showing that if you have anisotropic grains and they have a certain facet which is more prominent, means you have a texture, you have a higher photocurrent in the sample. Now, for this, obviously you can make by hydrothermal techniques using surfactant, but this is not helping because you get very small amount of material. If you want to do it on a large scale, you need a method which is compatible. So what we have come up with is also something which has not been reported so far, is to do CVD or film growth in magnetic field. There is a lot of work on electrical field, so people do spark plasma sintering and material synthesis in electrical field. But in magnetic field, this is something which has not been reported for thin films, especially for metal oxide. So by doing this, we realize that since iron is a transition metal, you can change the flux in the gas phase to orient in a certain way. And this is something that we have shown that by applying field during the film growth, you change the optical density, you change the grain orientation, and you can control the phase. And this, you see here on this slide, that without field, that means under zero field condition, you have an isotropic growth. That means the grains are randomized, you have everywhere, you have a dense film, but the grains do not show any specific orientation. By applying the field, and depending upon whether the field is perpendicular or parallel to the substrate, you can induce an anisotropic growth. That means the grains are now growing perpendicular to the substrate. And this obviously helps in the charge transport, because now these pillars or nano rods, they are acting as highways for the charge transport on the surface, where you have the oxidation taking place. So this phase and morphology control by CVD is an important area, and this has now been shown for a lot of other compounds also. And what I wanted to point out here is that through this highly faceted and textured structure, which can be controlled, you can also control that certain facets are preferred, they can be exposed. So like you can see that already at, this is just 0.5 Tesla. Now in the meanwhile, we can go very high, and we can make material, we can even change the composition of the material by applying field. But for this purpose, it was important to have highly crystalline iron oxide, which is dense, which is stable, and has the right facet on the surface. And this has been shown that on a small sample here, that you do have a clear jump in the photocurrent, which is generated in the field deposited iron oxide sample when compared to the amorphous one or non-zero field condition. Now the third thing is that we can obviously take the catalyst and do a co-catalyst immobilization. Because of the time, I'm not going to go into the detail. I think Shahzada has appreciated finishing on time. I will just say that the path forward is to combine the solar and PV. I mean, we know that the perovskite, they have done excellently well in competing with silicon technology, but they do have the stability issue. We have been working for a long time. One of the startup of Solar from Poland is in Cologne, and 3 of my PhD students are working in this company, Solaveni. So we have discussed this very often. How can we combine these moderate stability of the perovskite solar cells with the photoelectrolyzer, and then come up something which is more sustainable in terms of the added value, and obviously if it can lead to decarbonization of the economy, which is a big area. And obviously once we give hydrogen value by producing, for example, other hydrocarbons or fuels like methanol, or even using it for reduction of carbon dioxide, it is a totally different value chain than just by producing hydrogen where you have issues with the storage. So here I would like to, just because Shahzada has mentioned, we have been working on the planar perovskite films, and I think it has come to a saturation with Newport now certifying regularly efficiency more than 25%, and I think Professor Naziruddin's group has been pioneer in this. But we are following a completely different approach. We are now making flexible perovskite. So this is published work. We are trying to put all the 4 components in a single fiber, so that it can be used for integrating it in devices, integrating it into fabrics, in other things. And this is the area where we see a lot of potential also, that a poorly functioning photovoltaic cell, because by using the photocatalyst, you can easily harvest a photovoltaic of 0.8 volt. And then you need, obviously, if you look at the overall potential and the real experimental value you need something around 1.5 volt. So you need a photovoltaic cell which can give you the rest. So this combination is something where we are looking at. And with this, I would like to summarize. I think I would like to point out that there is a comprehensive photocatalyst database available. JCAP at Caltech, the Joint Center for Artificial Photosynthesis, they have screened 10,000 photocatalysts. And they came up with few transition metal-based spinels and other oxide, because these are the transition metals, they have multiple oxidation states, and this is what is needed for surface chemistry. There is a lot of work on the reaction mechanism, but what we need for a cost competitive solution is how to integrate. And I think this is where the challenge is. We have to now stop thinking in this square centimeter sample and talk about system and integration. Because every time you work with industry, they are more interested in technology integration and not looking in a beaker where you can produce, or in a glass vessel where you can have a good hydrogen production and you can show them bubbles evolving when you shine light. Second thing is that there is a need to take the materials which are abundant, stable, and have shown to be active and structure them in a way which is industrially compatible, like this laser-based patterning, or looking at field-assisted synthesis of these materials so that you can have new functionalities with old known materials. Right, and I think this is the final thought. Energy transition is ultimately a materials challenge. I mean, if we are looking at the batteries, photovoltaics, everything boils down to the eco-design principle that we can apply on a material. And I think we all know that with the perovskite, the issue of lead is a permanent one. And this is an ongoing discussion for a long time. There are ways to substitute, but this is one thing, it is a material challenge. Same is with all kind of catalysts, that you are looking at something which is stable, recyclable, and abundant in our earthly resources. Right, and there are other, so I think right now I would also like, because there are a lot of people here in the group, you can look at other small molecules activation. Nitrogen is one good example. Like you can activate nitrogen to create ammonia, which can be used as a fuel, and it can also become a storage for hydrogen. And that is again a very, very important area, because if you see the production of ammonia, which is taking a large amount of the global energy production, 1 to 2%. I think this is where if we can come up with an efficient technique to overcome the limitation of Haber wash process, we can make here a big impact. With this, I would like to thank my group members for doing most of the work, our funding agencies, and I obviously would like to thank everyone who is right now joining us in this online session. I would like to thank Professor Shahzada Ahmed once again, and I thank you all for your kind attention. Thank you.
Thank you very much, Professor Mathur, for your fantastic overview and taking us through the journey of the materials design and discovery for energy applications. And you have very nicely touched all the three cutting edge topics: energy generation, hydrogen production, and energy conversion, of course, photovoltaics. And I second your opinion that the materials are very important. And this reminds me of the famous song of Madonna, I am a materials girl. So we need materials, doesn't matter which type of application we go for, hydrogen, storage, and conversion. Thank you very much. We have received a couple of questions for you, but this we will take after finishing Professor Dario Bassani talk. Sure. Once again, thank you very much for your fantastic talk. The next speaker is Professor Dario Bassini. He is Director of Research CNRS at the University of Bordeaux. Professor Bassini received his PhD at the Northwestern University, and then he worked with Jean-Marie Lehan, a Nobel laureate at Strasbourg. And since 1997, he's at Bordeaux. I don't know why. Maybe the wine is more important for him, apart from science. And he lead a research group focused on the use of supramolecular interaction and to control the photochemical and photophysical behavior. And he has been receiving many honors and awards. To name a few is Grammatisch-Newman Prize of the Swiss Chemical Society. He's an editor-in-chief of photochemical and photobiology. And today he's much more interested in providing mechanistic inside view of the photoelectrochemical systems and photophysics. And today we are looking forward to hearing from Professor Bassini. Professor Bassini, the floor is yours, and we look forward to listening to you.
Thank you very much, Professor Ahmed, and good morning and good afternoon, good evening to everyone. It is a great pleasure to be able to share with you our recent results on understanding proton migration in perovskite materials. Before that, though, I would like to express my gratitude to the previous speakers for giving us such fantastic talks and great introduction on perovskite materials and also the challenges that our society is facing in general. As you can see from this picture, Bordeaux is actually a great place to be. So there's really no question as why one would like to move here eventually. The topic that's really of interest here today is the use of hybrid perovskites to replace silicon devices. And something that perhaps wasn't mentioned by the previous speakers is why this is actually interesting to us. So if we just take a quick look at some key numbers, like from the International Energy Outlook just this October, in 2050, we expect that about 1/3 of the electricity in the world, or about 10 trillion kilowatts, will be coming from solar. Now, to prepare or to obtain 10 trillion kilowatts, we need something like around 70,000 square meters of solar panels at the current efficiency. So this is enormous. This is about twice the size of Belgium. And if you compare this to a 4-lane highway, we would have to build about 400 kilometers of solar panel highway every single day from today until 2050. To be able to achieve that type of production. So of course, perhaps we could do this with silicon, but that would require a lot of energy and a lot of infrastructures. On the other hand, if we were able to do this with hybrid perovskites or other printable solar cells, and we heard mention of flexible perovskites just in a previous talk, then this would be fantastic because we could use roll-to-roll printing technologies. And then of course, it would be possible to print 400 square kilometers of solar cells between now and 2050. As was also mentioned previously, we have a couple of problems with perovskites that we still need to address. Apart from the presence of lead, which could be a problem, but not necessarily so if suitable containment strategies can be implemented. We're also really dealing with that of operational stability, which Professor Nazaruddin tackled very nicely in his initial talk. And there's two real problems here. One is that of moisture. So moisture degrades perovskites, especially under operational conditions, that is under the presence of light. The other problem is that of ion mobility. So we can do something about moisture by encapsulating the perovskite. This is possible, but there's not much that we can do about ion mobility because this is a problem that is intrinsic to the perovskite structures, which is composed of ions. And to solve this, we really need to understand a little bit better how ions migrate and why they migrate. So there are different ions in methyl ammonium perovskite, for example, one of them being methyl ammonium, the other being lead, and then of course there's iodine or other add elements that you have made added. Now, lead thus is very heavy, so that one hopefully doesn't migrate too much. However, numerous groups have shown that methyl ammonium and iodine, both of which are rather large, bulky ions, actually do migrate. So under operational conditions, you'll see that you will have slow migration of these ions through the perovskite cell, and this eventually leads to degraded performance because, of course, you don't have the perovskite structure anymore throughout your material. So if you're going to try and solve a problem, you, of course, need to understand it. And obviously, there's been a lot of work that went into understanding methyl ammonium and ion migration. However, there's another ion that has been, at least until recently, overlooked in these perovskite solar cells, and that is protons. Now, protons are there because we have methyl ammonium, and ammonium is, of course, a protonated amine, and amines can undergo protonation and deprotonation very quickly, so we expect that there are going to be protons in the material that are going to be able to move around. The reason why this has not been studied very much, at least in our point of view, is probably because it is very difficult to study the movement of protons. Protons are very light elements. They have no electrons, of course, because they're a proton. They're never free. They're always associated to something else because it's a nuclei, and they move very quickly. So whereas for methyl ammonium, you can actually use, for example, techniques like TOF-SIMS or mass spec to be able to map out the concentration density through your device, and the same can be used for iodine. Well, you can't do that for protons, can you? Because you're going to have protons everywhere, and you're not going to be able to detect a small difference in concentration of a proton between the top of the device and the bottom. Apart from that, mass spec, of course, is not sensitive to protons because you're using primary ions, which are much heavier than protons. So you can't detect anything that is lighter than your primary ion, like, for example, bismuth in this case, or in often cases. So we thought about this, and we proposed the new techniques that we thought could be useful for doing this. And it's a spectroscopic technique that we developed in collaboration with a colleague here in Bordeaux, Thierry Boufteau, who's a specialist of polarization modulated infrared reflection absorption spectroscopy. Now, this is a technique that's been fairly widely used by spectroscopists working on surfaces. And it combines the advantages of having an enhancement of the electric field by a metal substrate, along with the surface selection rules. So this is actually extremely sensitive infrared technique. So it's like doing IR absorption, except that it's very sensitive, and it's so sensitive that it can even detect a single molecular layer on top of a metal object. So very, very sensitive technique. And it's also sensitive to the orientation of the individual bonds. So if you have a molecule that is oriented on the surface, you can actually tell the way that it's oriented, whether it's oriented vertically or oriented, for example, horizontally with respect to the surface. So we can get a lot of information with this technique. So how can we apply this to perovskite materials? Well, the idea that I had was that, or that we had was that we could use the difference in mass between protons and deuterium to be able to watch the substitution of hydrogen or deuterium by the light, by the other isotope, during the migration of protons in the material. Now, this has two effects. One of them is that it gives us a change in the vibrational energy, as you can see by the difference in vibrational frequencies between hydrogen and deuterium. But it also has another interesting effect, that it actually changes the activation energy for proton or deuterium migration due to the difference in 0-point energy between the vibrational minimum for the proton with respect to deuterium. So we expect a higher activation energy for deuterium with respect to protons. And as we'll see, this is actually the source of one of the surprises that we had. So in essence, the experiment that we based on the following results is the following. We begin with a deuterated methyl ammonium precursor, and then we prepare a perovskite with this per deuterated methyl ammonium, and then we watch as in the presence of moisture, the deuterium is sequentially substituted by protons to obtain your standard methyl ammonium. And as you can see here from the actual raw data that we collect, we can see very clearly the stretching frequencies for deuterium here at around 1190 centimeters to the -1. And with time, they go away and they're replaced by the growing of the signal of the ammonium. And we can actually follow the different intermediate species by looking at the relative concentration, of course, ponderated by the isotopic presence of the different elements, concentration of different elements. And as we follow the material, so a single device, as we follow it over time, we'll see the disappearance of the peaks due to the deuterium, and then the growing and the disappearance of the intermediate NH2D species, and eventually, with the short induction period, the growing of the fully protonated species. Now, this is the technique that I wanted to present here today, and now I'll show you how we can use this to understand and analyze the device behavior. So the first thing that we looked, of course, is the effect of light. Is proton migration affected by light? And the answer is yes. Absolutely, it is, very much so. As you can see, proton diffusion or the substitution rate is slow in the dark, and it dramatically accelerates when you irradiate the substrate, slows down again when you turn off the light, and once again accelerates as you increase the light. So we have an on-off effect of light onto the proton migration and the diffusion. So clearly, as many people have seen before, perovskites degrade much quicker when the cell is in operation than when you store them in the dark, for example, in a drawer. This is, of course, important because we're interested in having stability under operational condition, and obviously proton migration is very active during irradiation. So we expect that there is a correlation between light irradiation and proton migration, the next question will be, is there a correlation between proton migration and degradation? The actual diffusion rate is not just sensitive to light, it is also sensitive to the presence of moisture. Again, this was seen before. We can actually now quantify this, and we see now that we can measure the rate of proton diffusion with low concentration of moisture, intermediate and higher. And if we plot this, we see that we have a relatively linear relationship, which is in agreement with a first order rate reaction. So not only is proton migration and hydrogen substitution sensitive to light, it is also sensitive to moisture. And this means that perhaps we can use this technique to measure the efficiency of protective layers towards moisture. As Professor Nasruddin mentioned, we need to protect the perovskite device from moisture, so we can put different layers on top. This was already done many years ago, so already 7 years ago now. This is an example from the SNAITH group using iodoperfluorobenzene. What they propose is that you have the formation of a halogen bond, and then the presence of these fluorine atoms, which are very hydrophobic, protects the perovskite from attack by moisture. More recent results have elaborated on this concept, for example, using olein ammonium polysulfides, which also work very nicely, even better. This is a little bit more complicated, so we can go back and look at this and compare this to different other fluorinated precursors that we can use, for example, fluoroimidazolium iodide, or perfluorooctane, or even perfluorothiodecane. And what we find is that if we prepare different perovskite devices and then coat them with a monolayer of these different compounds, we can then measure the proton diffusion rate and use this to assess the efficiency that these additives have to protect the perovskite device from degradation by moisture. And this is something that we can do very quickly, so it's can be done in about half a day of experiments. If you compare, for example, methyl ammonium iodide, so your regular MAPI device that is unprotected, you have a baseline. If you put simply in the presence of perfluorooctane, you see that this results in a decrease in the proton diffusion rate, which means that there is some protection by perfluorooctane. This same perfluorooctane, but now with a thiol group that can be used to bind any vacant sites on the lead, has a considerably improved efficiency with respect to perfluorooctane. The best efficiency that, towards the protection to the degradation we found was afforded by the iodoperfluorobenzene reported by SNAITH, and even better by the fluoroimidazolium compound shown here, which had the lowest proton diffusion ratio. Now, the reason why we think that this is particularly interesting is that if you want to make efficient protective layers, you need to measure their efficiency, and for that you need to do degradation studies. Now, unfortunately, the degradation studies are going to be even longer if your protective layer is very efficient. So to be able to measure the protective efficiency of this compound, for example, you might need several weeks of exposing the perovskite device to moisture to be able to see an effect. And this will take a long time, of course, so you're not going to be able to screen protective layers very quickly. In this example, we can screen all of these protective layers in a couple of days. So we can go to much faster screening of possible protective layers just by measuring the rate of proton diffusion rather than actually having to look at the degradation rate of solar cells. And this actually revealed some very interesting surprises. So for example, to go back to the perfluorodecane thiol and the perfluorooctane, what we found is that the perfluorodecane thiol, which we expected would lie perpendicular to the perovskite, just like thiols stand up on gold surfaces, actually preferred to lie flat. Now this we could see through the different relative intensities of the vibrations. I'm not going to get into the details because I think it would take a little bit too long, but we can see that this molecule actually lies flat on the perovskite surface, whereas it lies perpendicular to the surface on gold monolayers. And we asked ourselves why this would be. Because there's really no reason for the fluorine atoms to want to lie flat on the perovskite, which is relatively polar surface. And so that's why we investigated the orientation of perfluorooctane, and much to our surprise, perfluorooctane spontaneously binds to the surface of the perovskite to form eventually a single monolayer that lies flat on the surface. Now this is extremely surprising because perfluorooctane is a little bit like Teflon. This is, and you can expect that perovskites are more like polar molecules. So this is a little bit like water sticking to your Teflon pan. We never expected perfluorooctane to stick to perovskites, but yet it does. We find that there are specific interactions between the carbon-fluorine bonds and the surface of the perovskite, most likely through a specific fluorine perovskite interaction that we tentatively attribute to hydrogen bonding, not fluorine halogen bonding, but hydrogen bonding, which actually allows this perfluorooctane to stick relatively well to the perovskite surface. And that's why you saw the protection offered by perfluorooctane, which is otherwise a very volatile compound and should just evaporate away. How can we use this? Well, we can actually make compounds that are fluorinated and expect them to stick to the perovskite. And this is exactly what we did. We prepared different porphyrins that we could use as a shuttle to bring metal ions in contact with the perovskite surface. The easiest ones to prepare are these tetrakis perfluorophenyl porphyrins. Unfortunately, we quickly realized that these mesophenyl groups prevent the face-to-face binding of the porphyrin to the perovskite, and so they tend to lie perpendicular to the perovskites. And once again, this is actually the power of the PMRS studies that allowed us to actually see that these porphyrins do not lie flat, but they lie perpendicular to the perovskite surface. So we went back, it was a little bit more work, but we prepared the same porphyrins, but without the phenyl groups, and these ones actually lie flat on the surface. And now we can put in different metal ions inside the porphyrins and use the porphyrins as a sort of shuttle, like this nice little truck, to bring the metal ions in close proximity to the perovskite surface and use this to change the surface potential or the work function of the perovskite. And you can see that by simply changing the metal ions inside the porphyrin, we can vary the work function of the perovskite material over a range of about 0.15 volts, so 150 millivolts, which is actually quite considerable when you think that this is actually due to a single molecular layer. Now, it turns out that the proton migration is actually much, much more complicated than what we initially anticipated and what I have just shown you. Just this year, there was this very beautiful paper published by David Kain's group in Advanced Materials, in which they reported a diffusion coefficient of around 3 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ untrue. We ourselves measured the diffusion coefficient by IR spectroscopy and found it to be about 100,000 times slower. It is 1.5 times 10 to the minus 15. Here is their data that they reported in their manuscript, and they measured this on single crystals of perovskites. Now, you could think that single crystals are better than microcrystals on a surface or nanocrystals on a surface, but this is not the case. As you can see, there is a considerable scatter in their data, and in fact, you can fit their data either to their diffusion coefficient or to our diffusion coefficient with really no change in the residual chi-square. So their data has so much scatter that you really can't tell what the diffusion coefficient is. But this led us nonetheless to wondering, why should they be able to get such a high diffusion coefficient in these crystals? And to answer that, we actually reproduced their experiment and compared the diffusion in a single crystal with the diffusion in the same crystal but this time crushed to a powder. And what we find is that there is no difference or very little difference in the diffusion in the large crystals and the powder samples. So according to their model, we would expect about 15% exchange in the crystal and complete exchange in the powder, whereas experimentally what we found is about 12% in the crystal, which is very close to the 15%, but only 44% in the powder, which is obviously not the quantitative exchange that you would expect. And of course, we were able to do this using IR spectroscopy, which actually allowed us to count how many protons were exchanged, which is of course much more precise than the NMR technique that they use. The explanation that we eventually found to the discrepancy between ours and their data is actually due to the presence of grain boundaries and dislocation in the single crystals. So when people measure diffusion in single crystals, it's important that they take into account the fact that the diffusion can occur not just through the surface, but also along these high diffusivity pathways, which are due to dislocations and grains in the nanocrystals or in the single crystals. And if you take those into account, then of course, all the data fits very nicely. So let's go back now to the diffusion and the effect of light on proton migration. So we looked at the effect of light on proton migration as a function of the light intensity and found that it increases, but then decreases. So if you look at the proton diffusion in the dark, it's actually relatively slow. However, as soon as you start to irradiate, it's light activated, and so it becomes very, very quick. And then if you increase the intensity of light, it starts to slow down again. So this means that there is a competing process with proton diffusion that actually slows the proton exchange. And what could this be? Well, we think that this is related to the nature of the migrating species. And if you look at some of the theoretical work that was published by Rappe in 2015 in this very nice theoretical paper, it seems that the most likely migrating species is actually hydrogen dot. So the hydrogen radical migrates, and it is formed by capture of an electron by a proton to form this hydrogen radical. It migrates, and then eventually you could imagine that when you have a large concentration of these radicals, they may recombine to form hydrogen, or they may recombine with an iodine radical to form hydrogen iodide. Both of these species have actually been detected by mass spec as gases coming out of perovskite devices during operation. So we think that this is perhaps a plausible termination pathway that could account for this slow decrease of the proton exchange rate as you increase the radiation intensity. So with this, we're really still in the quest for trying to understand how the diffusion actually occurs. So we, of course, published a rebuttal of Kahin's work in Advanced Materials that appeared just a couple of months ago in the same journal. And we started looking in a little bit more detail how the proton diffusions in the dark. So we found a new setup that I don't have time to explain here, but allows us to get much greater density of data points to be able to fit these curves to precise diffusion models. And again, I can't go into much detail, but this is of course governed by Fick's law of diffusion in solids. We can approximate it with this rather complex function, but as you can see, this function fits beautifully the experimental data that we obtained for the total hydrogen or proton diffusion. And from this, we can actually extract relatively precise or quite precise values, I should say, for the diffusion rate. And what we find are values that are very close to the ones that we previously reported. So the diffusion of proton is 1.4 times 10 to the minus 16 centimeters squared per second. And we also measure the diffusion of deuterium, which is interesting because it's a little bit slower. It's 5.1 times 10 to the minus 17. And this gives us a kinetic isotope effect of around just short of 3. This gives us a fairly complete idea of the proton diffusion steps. We know that we need to absorb water. We have dissociation, migration, and return migration of the deuterium. And we think that the rate limiting step may be the absorption of water onto the perovskite material, but we're still trying to confirm that. With that, I'm going to conclude because I see that our chairman has appeared, and I think it's time for us to go to the discussion section. So proton diffusion is a very complex process, but we think that understanding it is key to improving device performance. We have evidence for specific fluorine perovskite interactions that we think can be used to improve the perovskite monolayers. And then we also showed that proton diffusion is activated but slow in the dark. The people that have been doing the work are mostly this graduate student that has now a postdoc, Yangfan Chen, another postdoc, Dr. Subasadu, and this is Susanna Molenda, which is working with us right now. I'm happy to acknowledge the collaboration with Dr. Lionel Hirsch for the perovskite devices and Thierry Bouvetot for the perovskite, the PMRS measurements. And with that, I'll pass the floor back to our chair and thank him once again for the invitation and organizing such a wonderful session. Thank you very much for your attention.
Thank you very much, Professor Bassani, for providing us the mechanistic overview. This is paramount to optimize the system, to develop new material and make them more efficient. Quantifying of underlying mechanism is of significant interest for the renaissance of material. That's only we can learn, and very nicely you have done it. And thank you again for your time and very great overview for this one. Now I will pick a couple of questions, and all the three our keynote speakers are here. I once again like to thank for their time and their amazing talks today morning. So I will choose from, if you go. There is one question from Dieter Meissner. Thank you very much for your excellent talk. It's for Naziruddin. Is not phase stability a thermodynamic property, while stability deals with kinetics? Do you have a data on the thermodynamic stability of the different phases? Professor Naziruddin.
Very nice question. Unfortunately, we are in a process of working on these materials and the stability of various phases. We don't have any data. But on the contrary, if you allow me to ask one question about this, the last talk given by Dario Bassani. So he said, yeah, please. I really appreciated your talk, and it's a brilliant talk. I really like your talk regarding the stability of these perovskites. I have two questions. One is, can you just give us a hint why the fluorinated ionic liquid stabilizes the perovskite? This is my first question. Why did you select methyl ammonium cation, which is known in the literature that's unstable? Then can we go to the formidinium or even cesium just to identify, is it a proton-induced instability or is it due to some other factors?
Yeah. So thank you very much for your comments and very interesting questions. So for the first question concerning the ionic liquids, so many of the ionic liquids have fluorine in them. Because they need to undergo phase separation and be relatively heavy and not evaporate. And we think that this fluorine perovskite interactions contributes to the improving the stability. So you can see or imagine how the ionic liquid will fill up the interstitial space between either the grain boundaries or the dislocations and prevent moisture from penetrating or other exterior events from penetrating into the material. Concerning the second question, why we chose methyl ammonium iodide, well, we begin because this was the one that has been the most studied and for which there is the most data in the literature to compare. The answer to the second question is yes, of course, we can study this also in FAPI materials, and we have. I can already tell you that the diffusion of protons is considerably slower, so actually much slower in FAPI than it is in MAPI. So this goes very well in line with the additional stability of ferromedium cation with respect to the methyl ammonium. If you include cesium, it actually slows down even more. So this is work that we were very happy to do in collaboration with our chair. So we saw that the incorporation of a small amount of cesium into FAPI actually slows down even more the penetration of moisture. So clearly there is a very strong relationship between the protective ability of different cations and the penetration of moisture. So we think that this is a key aspect.
Okay, one final question, just a quick question. You use a perfluorinated the surfactants, and then you are favoring the fluorine to hydrogen bond. Why don't you call maybe fluorine to iodide interhalogen bonds? They're also very active and they form very quickly.
That is true. That is true. That is an excellent question. That is actually the first thing that we thought of as well. And we looked into the literature. There's quite a little bit of theoretical background on halogen bonds. And what we find is that the methyl ammonium iodide halogen bond is not going to be very strong because you don't have sufficient sigma hole on the methyl ammonium to be able to form a halogen bond. So it could be, but we think that this is weaker than the hydrogen bond formed by methyl ammonium and iodide. Iodide is not very good hydrogen bond acceptor. However, methyl ammonium is an excellent hydrogen bond donor, very, very strong. And so we think that this compensates for the poor hydrogen bond accepting ability of the iodide. We actually, as a side note, we actually see a difference in the stretching vibration of the CF bond, which is in agreement with the interaction of the fluorine with the surface. So we can actually see this looking at the CF bond, that the fluorine is actually stabilized by the surface.
Okay, thank you. Thank you.
Very good point.
Yeah.
Professor Mathur has also some curious questions.
Yeah. I just, connecting on this, first of all, Dario, thanks for this wonderful presentation, and I could follow it very well as a chemist. I was just wondering where your observation and the work of Kahin, you've shown that the larger grain boundary function or volume leads to higher mobility of protons. So is it a proton hopping on the surface that we know? There is a well-known mechanism for proton hopping on the surface of hydrophilic crystal, or is more like a bulk process? Because when you were talking about the mechanistic model, I was thinking you are looking at how a proton in the lattice of perovskite can move around, right? So how do you compare these two things?
So that's also a great point that I neglected to go into much detail. Thank you for bringing it up. So we believe that the proton migration is interstitial in the bulk, and probably by hopping on the surface. The hopping on the surface is something typical for protonated materials. So this is probably, we can expect that in the presence of moisture, there's going to be a layer of water on top of the perovskite, or a very small layer, very thin layer of water. And so proton diffusion is going to be very, very fast on the surface. Inside the perovskite, though there is no water, we never found any evidence for water that penetrates inside the perovskites. And so for this reason, we think that it is interstitial. And this of course is in agreement with the fact that it's a very small ion. So there's no need for a vacancy to be able to hop from one side to the other for the proton.
All right. Can I have one more?
Please.
Thank you. Because there is a discussion, or there are reports on that if you bombard single crystals of these perovskite with protons and electrons, so these elementary particles, then you have a stability effect. That means you stabilize in one or the other way. So you were talking towards the end that if there is a link between the proton migration and the degradation. So what is your stand on that? Is it really initiating? Because then it is contradicting all the reports where you see a stabilization. You have a high stability. People justify it with new electronic states being generated. So yeah, it would be nice to hear your comments on that.
Yeah, unfortunately, I'm not aware of the study that you're mentioning. I can add just as a comment that the proton migration by itself may not be necessarily a problem, provided that the protons stay inside the material. So that as long as we don't lose protons, it's probably okay, because eventually they can make it back to their initial location. Unfortunately, what seems to happen is that when you have free electrons or free charges that are moving around the perovskites, either by bombardment or during operation, the protons are going to be reduced to hydrogen radicals. And the hydrogen radicals either recombine together when they meet and form hydrogen molecule, and the hydrogen molecule then evaporates from the perovskite. And this, of course, now you've lost two methylammoniums because you lost two protons. Now you have two methylamines. The methylamine acts as a trap because it is an electron donating compound, so it's going to degrade your material. And the same happens if the protons react with iodide radical. They form hydrogen iodide, and this can escape the material. So this is probably the reason why eventually you have degradation of the material. So the actual migration per se may not be a problem, but because of the free protons and the free ions that are moving around and the free charges that are present, this eventually leads to the degradation.
Thank you. By the way, the group is actually from France. Catherine Corbel from Synchrotron in Paris. They have done this work.
Okay, thanks. Thanks very much. Yeah, I'll have to look into it. I must have missed it.
Yeah,
that's great.
Thank you very much. Yeah, thank you very much. Now I have a question for Professor Mathur. Is Abdul Haq. Sir, what do you think about wind energy generators based on piezoelectric strings? How efficient they are?
Yeah, thanks. This is an interesting question. I think it's a matter of scale. I don't think that people have been able to make these large piezoelectric crystals so far. So I think this will depend when you are able to demonstrate it. What I know from that small devices, they have been combined for like piezo photovoltaic effect. This is piezocatalysis. So there has been a lot of work on piezotronics. So people have seen a combination of this. And I think the fundamental principle of creating these transient dipoles or a piezo potential in the crystal is something which can be very nicely related to any physical model of charge separation. Because if you are polarizing the surface for a very short time, then you will either repel the molecule or you will attract the molecule. So I think that I can understand, but for using it for wind generator, I must say that this is something which is not within my own expertise. So I don't want to give any unqualified answer, but knowing the ceramic processing, I know that we don't have those large crystals. That might be important to have energy harvesting that can compete at that scale.
Thank you. I have another one for you, and that is more relevant as Professor Sanjay. I want to ask you about the advantage and disadvantages of a spinel cobalt oxide as a water oxidation catalyst. It's from Arwa.
Right. So cobalt oxides have been identified. I mean, you know the famous catalyst from Nocera on COPE. That was a cobalt phosphorus complex. And the reason is that cobalt 2 and cobalt 3 plus is also thermodynamically very stable. So you have a stable redox shuttle there. And people have shown, the group of Dunwai 1, that you can take cobalt spinel CO3O4, where you have both cobalt 2 plus and 3 plus. And if you replace some of the cobalt 2 plus with iron to have a doped spinel, it's a very good catalyst. I think the challenge there is that how is your trivalent cation distributed in octahedral and tetrahedral holes? Because I think the distribution, what is the degree of inversion in the spinel, is important for the ions or for the sites which are exposed to water. And that actually controls because if you have a stable state and it is not willing to get reduced, then obviously the catalytic efficiency will be low. So people have published on that how the inversion or the degree of inversion in spinel relates to the catalytic efficiency. But coming to the short answer is yes, cobalt-based oxides have been identified in these 20 champion materials by the JCAP people who have done machine learning and other things. So, and this is well known that transition metal oxides are very good catalysts for water split.
Thank you very much. I have the last one due to short of time, I will take the last one for Professor Nazaruddin. is from the Tariq. Maybe the question is not rightly phrased. Can you comment about the new technology in PV system?
Maybe
new technology in the PV system.
Yeah, maybe he is interested to know the cost analysis of the perovskite solar cells. Maybe just give the silicon solar cells. You have the peak kilowatt hour price, which is in the range of 3 cents. We can bring it to 2 cents per kilowatt hour based on the calculations which is available in the literature and which we did ourselves. So, and based on the efficiency, that's a 20% stability of 20 years. Now, can we reach 20-year stability? This is still a big question mark, but these are the assumptions.
Exactly, and this also has been certified. The LCOE, levelized cost of electricity, has also been calculated by NREL.
Yeah.
So this is also in line with that. And by the way, China just announced that they are no more subsidizing the silicon industry. So please expect to rise in the price.
Prices, yeah.
Please expect the rise in the PV coming. And with this, I think if we have no any further question, I'd like to thank all my keynote speakers, which are excellent researchers by their own means in their field. We have almost 322 participants on the Zoom and many more on the YouTube online with streaming. And with this, we will take a short break and then we will come with some of the contributory talks of 5 minutes each. Is it, I'm correct, Professor Yusuf? Hello? Yeah, with this, I think our keynote speakers have finished all their talk. The session has been finished. Now is the time.
If you can give floor to participants to attendees to ask questions directly.
Okay, thank you very much. It's a very good. Yeah, some of them are feeling shy. I don't know. Please, these excellent researcher and professor have spared their time, so they are available for you. Please don't feel shy and come with your questions. So I leave you with in the hands, very good hand with Professor Naziruddin, Professor Mathur, Professor Bassini. Please come with your question and directly ask. I am the middleman, so the middleman is going away. Please directly ask to them.
Professor Nazir, it's good to see you after a long time.
Thank you. Thank you. Yes. Because of this virus, I was not moving and not attending many conferences.
Yeah, the EPFL colleagues, they hide, they appear only in Nature and Science, that's it. So we have to find them somewhere. Okay, but I don't want to take away any time for the questions. I think there is one. I think people are writing more in chat. This is, I think.
Yeah. Side by side, there are some of them. So I transfer it to you already, but cobalt oxide. Now coming back.
Professor,
yeah.
Professor Dieter, you can activate your mic to give your question.
Actually, my question has been answered already. I wrote it down and it was read as the first question, but it was concerning the thermodynamic stability of the different phases and how this is really connected to the stability of the compounds, because stability, of course, is a kinetic, whereas the stability is some thermodynamic property.
Yeah.
We have another one. Yeah, how the solvent and temperature can affect on preparing a spinel cobalt oxide by sol-gel methods. The influence of the solvent and temperature for a spinel cobalt oxide.
Right, so I think the chemistry on your side, because cobaltite, which is 30304, is sitting in a thermodynamic sink. So when you take the mixture of cobalt, or just start with cobalt acetate, and you reduce it in an alcohol, for example, ethyl alcohol or isopropyl alcohol, you do get cobaltite. That is the spinel phase. So it's pretty straightforward. And I think the best is to either use a solvothermal method because you directly get crystalline material.
Thank you.
Oryomi Abagan, you can allow to talk. Please activate your mic. Oryomi Abagan. Lushimi Tarek. Lushimi Tarek. You are allowed to talk?
No, he already asked. We answered his queries. PV system. There's a one from Emmanuel, Dr. Emmanuel, I think he's asking about Professor Bassini.
Hello, everyone.
Yeah, please.
Hello, everyone.
Yes, go ahead. Tarek,
How
yes.
do you technology in PV system?
So this, I think Professor Naziruddin has already answered you that the cost of silicon is very cheap today, 20 cents per watt per peak. But in the pipeline, there are new materials are coming. We are developing. He gave an excellent talk today, an overview about new materials, which also give you less than 20 cents watt per peak for energy generation. And we didn't understand clearly, are you talking about PV system means integrators, power converters, power energy, but we are talking about the materials point of view. Okay. Okay. Yeah, thank you very much also for Naziruddin for giving this talk about methyl ammonium. We know that the change phases at 85 degrees from monoclinic to triclinic. And for this, we are already collaborating and we are more than happy with Dario Bassini. And indeed, the results are very good. We are working on FAPI with him. And I think.
Excuse me.
Yeah, please.
How to create a new system photovoltaic?
For the new photovoltaic system, you need a new semiconductors. And the semiconductors should absorb light. And the aim should be to absorb light as much as possible, Generally, most of the semiconductor absorb visible part of the spectrum. So if you can develop a material which can absorb visible as well as a near infrared region, you can push the performance. Silicon absorb mostly the NIR region, near infrared region. So if you are a material scientist, if you are developing some material, please make a material which can absorb as much light as possible. So you can make a new PV system.
Also, I think we can add to that the fact that it's important that we have different technologies that can compete to be able to improve the overall efficiency, stability, and implementation. We don't know today what it is that we will need tomorrow, or the day after tomorrow, or the year after tomorrow. So we need to study this. It's our role as scientists to be able to provide as many solutions as possible to the future problems that we will have. So this is something that we owe to ourselves and to our society. So I think that this is very strong incentive for finding new materials.
Great.
Right, and I think maybe to add to that, understanding, and I think the two talks by you and Nazir have shown it, of the fundamental understanding of the crystal chemistry and the electronic behavior is so important. I mean, you look at the paper that Miyazaki published for the first time, nobody thought that this hybrid perovskite will take this turn. So this simultaneous development of a lot of new science and technology, I think there is no other example where you had these growth which are orthogonal normally. You have materials, then they reach some kind of maturity. But now looking at Nazir's talk this morning, you are already at par with silicon. So I can understand that this is the way to go, taking the materials and developing a deeper understanding, both in terms of science and engineering, and thinking of integration. This is something. And I think maybe with this, I would like to ask, since I have Nazir here, a question. You mentioned in your talk in the beginning that one of the challenging issues is stability. But towards the end, you have shown us a lot of ways of interfacial and all. But I think in terms of, we know that the anions are not that mobile than the cations. So how do you see that? And if we can, with tin perovskite also giving very good efficiencies, do you see that that is going to be material for devices?
Yeah, thank you for asking this question. So actually, I did not show a lot of data where we are trying to understand. That's the reason, one of the reasons why I asked why ionic liquid is stabilizing. So we have developed this polymerizable ionic liquids, fluorinated ionic liquids. So they coordinate to the lead and then form. So they have a dual function. They grow the crystallinity of the perovskite composition, and eventually they leave around the grains to make it connectivity between the grains. And this fluorinated ionic liquids, we have the XPS data showing that they are forming a shell on top of perovskite grains. And that way you can enhance significantly the stability of the perovskites by using functionalized ionic liquid. This is one of the topics which we are extensively working. I did not show because I just showed the recent high efficiency data. But in fact, we do have a high efficiency and stability using this functionalized ionic liquids.
Yeah, thank you very much.
Thanks.
Any further questions, queries, comments? More than welcome. We still have a couple of minutes because 11:30 we have a contributory talk. Some of the contributory talks will start.
If
there is a question for Professor Basani, there's a question. It says that with regard to the findings of yours, you observed, why was it that your finding did not get the same result?
So I was reading that question. I was trying to understand which are the same results. So perhaps they're referring to the work by the group of Kahin that when I compared it to our own. So for memory, they found a diffusion coefficient that was 200,000 times slower or faster, sorry, than ours. And we attribute that to the fact that they didn't take into account that you have dislocations and high diffusivity pathways inside macroscopic crystals. So if you have a crystal, it has a certain size and it has a certain surface area. So you're going to model the diffusion with respect to the surface area. But if the crystal has lots of holes and dislocations and defects through which protons can diffuse or other ions can diffuse, it actually has a much higher surface area than what you're actually modeling. And so for that, you are not taking the right surface area into account. So we think that it's due to the fact that they didn't take into account the presence of high diffusivity pathways, which are present in large crystals, less so in nanoscopic crystal, because a nanoscopic size crystal usually won't have any defects. It will just have a grain boundary. I hope that answers the question, but otherwise, please feel free to write it again.
Yeah. Thank you very much. We have another one for Professor Sanjay. What's your opinion on titanium dioxide nanotube decorated with cobalt oxide as a photoanode for water splitting? From Arwa.
Yeah, thanks. I think this is an interesting point because obviously the material, if it's changing the morphology and form, it changes property, this we know. And I think this is the same with titanium oxide. And nanotubes, where you do need some doping, it's mostly nitrogen dope, and it increases the absorption. I think Shahzada just mentioned we need material which can harvest maximum amount of photon energy or the solar energy that we have. So I think that is a good way of electronically and structurally modifying what material which is abundant, titanium oxide. And this was probably the important message in my talk, that we can keep on developing new materials, but we have to see on what scale they are available, how we can modify. At the end of the day, they have to be produced in large amount in the industrial sector. You don't have these sophisticated, and that's why you see then drop in efficiency when you go from 1 square centimeter to a module size. So it is intrinsic to the scale up. And I think that's why this TRL thing, that technology readiness level, we have to really see that your competence or materials competence should reflect or translate into the maturity that industry is needed. And titanium oxide, which is now doped with nitrogen or carbon, is a well-known product. The company in Japan has been marketing this for a long time, the carbon-doped titanium oxide with high conductivity. So this is a very good material, but once again, it's a white pigment, so it doesn't absorb in the visible light. And this is what people are trying to do. So it might be, at the end, a combination of materials. So yeah, this is a short answer to a question which can go for a long time. Actually, it's a discussion point.
Yeah, thank you very much. Thank you very much. I think you very rightly answered it. And Arwa I think is very brave. Has come up with a number of questions. Thank you again to Arwa also. Just look very, he or she, I don't know, look very enthusiastic. Right? With this, I think is 11:30. I like to close this session, and I'm again very thankful to all my speakers who, in spite of their busy schedule, take their time out. I know Naziruddin has a talk at 9 o'clock. He managed 9:30 here. Sanjay Mathur also has a talk in Frankfurt, German meeting, 9 o'clock, 9:30 he managed here. Tariba Seni also busy guy with chairing many committee at the French Science Circle. So with this, I think I like to close this session, and I'm thankful to all of you. And it's time for a contributory talk, and I hand the floor to the organizers. Thank you very much.
I invite all keynote speakers to stay with us to follow the students' PhD presentations.
Okay. If they are available, I will also request them to be there for it. If they are available. Yeah.
Excuse me, for the authors of the papers, I invite him to rename the name of the pseudonym of Zoom, and add at the end the paper ID to facilitate their identification.
Okay.
Please add the paper ID near your name.
Okay. So it's the time for Pedro Lineker, and he is going to talk about experimental investigation on the influence of the diameter on the thermophones for application in hybrid PV and thermal system. Pedro Lineker is from Brazil. No, the presenter is by Romeo Micoas, the Federal University of Technology, Brazil. Romeo? Yes. No sound.
For application in a hybrid Lineker Machado. I'm here to present the study entitled Experimental Investigation on the Influence of the Diameter on Thermosiphons for Application in a Hybrid Photovoltaic Thermal System, here at the 9th International Renewable and Sustainable Energy Conference. I'm from Brazil. Our university is located in Ponta Grossa, Paraná, which is a state in southern Brazil. Paraná is famous for the Iguaçu Falls, and its capital is Curitiba. UTFPR has 13 campuses around the state. Ours is in Ponta Grossa, a city which is 2 hours away from the capital. So here's a brief introduction. Currently there is a new world order in terms of energy. Self-sufficiency in energy generation is sought, together with a diversification of the energy matrix, using alternative energy sources capable of supplying the energy demand in the countries in case of a shortage of fossil sources. One of the alternative energy sources is the sun, which can be used to generate clean electricity from photovoltaic panels. Although it has a high potential, solar energy is underused, since the maximum efficiency of these photovoltaic panels is about 20%. The efficiency of photovoltaic panel can vary during the year due to different levels of solar radiation, as well as with temperature, since an increase of 1 Celsius degrees in relation to the optimal operational temperature can generate losses of approximately 0.5% in efficiency. As a possible solution for temperature control of photovoltaic panels, several tests are being conducted with heat pipes and thermosiphons. Thermosiphons are passive heat transfer devices that operate in a two-phase cycle resulting from the vaporization and condensation of a working fluid. They are composed of a hollow evacuated metal casing filled with a working fluid. Thermosiphons have 3 sections with distinct functions in their operation: the evaporator, adiabatic section, and condenser. The lower region, called the evaporator, have the function of absorbing heat from a hot source, causing the vaporization of the working fluid, and the condenser has the function to dissipate that heat to another cold source, condensating the working fluid vapor. In the adiabatic section, there is no heat exchange with the environment. Regarding photovoltaic panels, thermosiphons can be used in a photovoltaic thermal system, in which the evaporator region of the thermosiphons is positioned in contact with the back of the photovoltaic panels in order to absorb heat, while the condenser is inserted in a manifold where water flows inside, absorbing the heat from the thermosiphons. Thus, aiming at the development of a photovoltaic thermal system, this paper aims to conduct an experimental investigation about a geometric parameter in the thermal performance of thermosiphons, in this case the diameter of their sections. The thermosiphons were made in a copper alloy, and the evaporator size was made in regard of a commercial Resun 60 watts photovoltaic panel. 3 different thermosiphons were made, one with all section with an outer diameter of 9.52 mm, another with outer diameter of 12.7 mm, and the final one combining both diameters, 9.52 at the evaporator and adiabatic section, and 12.7 at the condenser. A copper connection was made to join the 2 sections that have different diameters. Here is the experimental apparatus, and it consists in a power supply, a data acquisition system, a portable microcomputer, an ultra-thermostatic bath, and a variable area flow meter. For the experimental test, a chromium-nickel alloy resistive tape was wound over the entire evaporator and connected to the power supply, using test LEDs with alligator clips. In that way, we were able to simulate the evaporator heating due to the Joule effect. To simulate a manifold, the condenser was inserted into a 60 mm diameter PVCT that was connected from flexible silicone hoses and connections through the ultra-thermostatic bath, allowing the cooling of the condenser from the water flowing on its surface. The evaluation of thermal performance of the devices was made through the thermal resistance, that considers the ratio between the difference between evaporator and condenser temperature and the heat load applied. It can be seen that for all thermal loads applied, thermosiphon B showed the lowest thermal resistance values among the devices tested. This occurs because the device presented the lowest temperature difference between evaporator and condenser sections, which shows that this thermosiphon was able to transfer heat more efficiently between its 2 extremes. After finding out that thermosiphon B, the one with different diameters at its region, was the one with better thermal performance, a total of 4 thermosiphons with its characteristics were made and used to build a PVT, as we can see here in this figure. Now, as a continuation of the study, tests should be done with the PVT system, comparing it to a conventional photovoltaic panel, in order to evaluate panel temperature data, as well as electrical, thermal, and second law efficiencies. Here are our acknowledgements. Thank you all for the attention.
Thank you. So now the next speaker is Najwa, and he is going to talk about investigation of the structural properties of tin oxide cobalt doped by potassium, deuterium, and synthesis by co-precipitation method for photon conversion. Is Najwa Iraza?
Hello everyone and welcome to my presentation. First of all, I'd like to thank you all for being here today and for giving me this opportunity to present my work in the framework of the International Renewable Sustainable Energy Conference. Let's start by a brief introduction about myself. My name is Najwa Iraza and I just have my master's degree in materials and applications for photovoltaic energy. So it goes without saying that PV energy becomes today one of the most promising and ecological sources of renewable energy. In order to increase the efficiency of PV cells, several mechanisms can be interpreted. This work, which was my project's graduation, is part of the thematics. It relates to the investigation of the structural properties of SnO2 co-doped by potassium dysprosium and potassium samarium synthesized by the co-precipitation method for photon conversion. This presentation will take about 5 minutes, which is structured as follows. The diagram in front of you illustrates the objective. We plan to produce SnO2 powders, which will be characterized by specific methods for future use in PV cells. However, the limits of Cell-based performance of silicium are in part due to the poor overlap of the solar spectrum and the absorption spectrum of silicium. One of the keys to increase the yield is to convert part of the solar spectrum to adapt it to the width of the band gap of silicium. In this context, the use of impurities such as rare earth in a host matrix can give rise to luminescent materials covering the entire visible range. In this study, we will focus on samarium and dysprosium. So, in general, in SnO2 doped by dysprosium, the rare earth occupies the Sn4+ site. This substitution makes Sn as a fault center in the network by carrying one excess electron. To avoid the generation of vacancies, it is preferable to introduce an alkali metal with the lanthanide. In this case, the introduction of K+ ions was used as a charge compensator. The same principle for SnO2 doped by potassium and samarium. The diagram in the following figure illustrates the main preparation steps. The chosen method is co-precipitation. So, to determine the structure of the different phases formed during the thermal treatment, the use of the following characterization techniques remains the most frequent solution. The first one is Fourier transform infrared spectroscopy, which is a method of structural analysis. So the resulting IR spectrum shows the two period bands at 560 and 670 cm-1 associated with vibration extension of SNO and SNO-SN. The second one is X-ray diffraction. So as you can see, all doped powders show a slight shift in the position of the peaks with respect to the pure SNO2. This is particularly due to the low doping rates. The most intense peaks are the lines corresponding to the reticular planes 110, 101, and 211 of the tetragonal phase of the rutile type of SNO2. The table in front of you shows the latest parameters calculation using expert high school software and foolproof software, which were compatible with theoretical values. So to sum up what I've just said, SnO2 powders have been successfully synthesized by the co-precipitation method. It favors the small and uniform nanoparticle through a fast and homogeneous nucleation and crystallization. In order to better understand the study, the use of other techniques of characterization, such as UV visible and photoluminescence, remains the most frequent solution to be able to achieve a comparative study between SnO2 doped by potassium dysprosium and potassium samarium. I'm coming to the end of my presentation. I hope this has been informative and would like to thank you all for your attention. Hello everyone and welcome to my Hello everyone.
Professor Ping Wang will ensure the moderation of this session. The floor is yours, Professor Peng Wang. Please activate your mic.
Hello.
Professor Peng Wang. Meanwhile, we go to the next presentation of Mr. Jabour Manar, ID 100.
Hello everyone. In this presentation, we will present a topic of energetic and economic evaluation of mono and polycrystalline grid connected PV systems in the case of Ouarzazate, Morocco. So the aim of this study is to evaluate and compare the energetic and economic performances obtained using data from experimental measurements of mono and polycrystalline grid-connected PV systems and the simulation by the system advisor model software. The different results showed that the polycrystalline models gave the best performances compared to the monocrystalline models, with a performance ratio of 80% and a capacity factor of 21.9% and a low LCOE of $59 per megawatt hour. For the experimental devices, the two PV systems are installed at the Polydisciplinary Faculty of Warzazat with a power of 2 kilowatts, and each plant is composed of 8 PV models of 255 watts. The PV plants also consist of a meteorological station which monitors the ambient temperature, models temperature, as well as the solar irradiation and wind speed and direction. The Warzazat site is characterized by one of the highest sunshine levels in the world, as shown in this figure, the wholly global horizontal irradiation with a maximum value of more than 1000 watts per square meter. It's also characterized by a very high ambient temperature values in summer, which can reach above 43 degrees Celsius. And regarding to the PV models temperature, the present figure shows that these models can reach a cell temperature value between 60 to 77 degrees Celsius. These high values of temperature throughout the year is justified by the very high ambient temperature of this site, which have a large influence of the model temperature. Now, let's talk about the comparison of the performances of the two mono and polycrystalline PV systems. As illustrated in this figure, the results of the experimental measurements give a higher energy yield values than those simulated with SAM, with a highest value of above 1915 kilowatt-hour per kilowatt, obtained by polycrystalline models. Also, the results showed that the polycrystalline models bestowed higher performance ratio values than the monocrystalline models. The measured results give a performance ratio of more than 80%, while the simulated one gave a less value of 78%. The much higher capacity factor is obtained by the polycrystalline models and with the experimental measurements, which is about 21.9%. For the economic results, the comparison was based on the determination of levelized cost of energy that was based on the financial parameters of the consideration in Moroccan markets. And the simulation was carried out with the two different simulation software, SAM and PVSys. As shown in this following figure, the SAM software gave a low LCOE of $59 per megawatt hour with a polycrystalline models. As conclusion, the experimental measurements give more important performances than the simulation by SAM software, which underestimated them, and which can be justified by the uncertainty of the meteorological data drawn from the database of SAM software. Also, for the Warzazat site, the most optimal technology is the polycrystalline technology. And thank you for watching.
Thank you. We have any further questions? The talks there?
Yes, questions related to this part. The three presentations.
Okay. Otherwise, we can take a short break now and we meet up at 12.
I think there are some questions in Q&A.
Okay. Okay. Let me check Q&I. Oh, this is the same question being repeated. Yes. Okay. So these are the questions from the last talk, I think, about Julius. From literature, I read that monocrystalline perform better in tropic region than poly. It's true. The monocrystalline has a less defect, but and they perform better, but they are also costly. So the cost of the silicon also increases for the monocrystalline solar cells. And similarly, in our research and R&D endeavor, we also try to make the go towards more near and near to the monocrystalline things. And how to increase the possibility of new data. This we already have answered, I think, in the morning. Nazaruddin, Professor. Okay, there is a question from Dieter Meisner for about thermosiphon top. How useful are experiments in which the mounting of the module has to be much steeper than the optimal orientation?
Who should answer this question?
Sorry, can you repeat the question, please?
Yeah. How useful are experiments in which the mounting of the module has to be much steeper than the optimal orientation? How useful are your experiments?
So we think that the advantage of using thermosiphons for a PVT system is that at the same time as you reduce the panel's temperature and increase the electrical efficiency, we can increase the general first and second thermodynamics law efficiency due to the heating of water. So we've seen much studies that have been made that using this PVT system can increase in a lot the both efficiencies for the panels. And in that way, we can keep it at a lower temperature and increase both thermal and electrical efficiency.
Okay, we also have another question from Dieter. Concerning the comparison of single and multi-crystalline module, it looks like the real efficiency of the module were different despite the same rating. So the comparison really affect the properties of the crystallinity. To some degree, yes, the performance drops with time. But they do monocrystalline drops better, give you are more efficient and also again more costly. So if the cost is an issue, LCOE, then most of the solar cells are polycrystalline for validated deployment. Okay, so if there is no further presentation in this session, can I give floor back to the organizers?
Yes, there are three more presentations. I think Professor Dieter want to ask question.
I already read his questions. And
yes, okay.
But please let me add to the question concerning the thermosiphon. Of course, the thermosiphon needs a steep orientation. So when because of this you have to put the modules much straighter, much more upright than is optimum orientation, then of course you lose a lot of the power which you can produce even if you gain something by cooling. So I don't think this would be very useful.
Oh, we performed the tests with the thermosiphons at the optimal inclination of the panel, which was our city's latitude. And all the thermosiphons worked great, so we wouldn't change the orientation. We would still be able to use it at the optimal positioning.
But in your paper, you wrote it's 20% from the perpendicular orientation. So
no, 25 degrees from the horizontal.
Ah, then you made a mistake in your slides. Thank you.
Okay.
Thank you very much. Professor Shahzada, we go to the next.
Hello, everyone.
I think this time, Professor Saadada, I think it's time for a break. We will start the next session.
Yeah, at 12:30.
Yes.
Okay. Okay. It's a time for break, and we will be back at 12:30.
Okay.
Okay. Thank you. Naziruddin told me that Professor Naziruddin told me that he is not available because he has some examination, PhD thesis examination. So we have to look for a new chair for the next one.
You can also the share of the session.
No, the next session is Professor Naziruddin.
Yes,
and he just messaged me that he has an exam. Yeah, he is busy with another committee at 1 o'clock.
Who can do this session?
Okay, I will check with Professor Bassini and Dario Bassini. I will check with him if he's available.
Yes, I'm sorry.
Oh, you are there.
Yeah. We're having a laser being installed right now, so I had to go check that the installation was going okay. My apologies.
Okay, so can I make a small request to you, Professor?
Sure.
Can you chair the 12:30 session?
Pardon?
Can you chair the 12:30 next session?
I'm going to lunch with the person installing, so I don't know. Right now it's a little bit late. I don't know if we'll be back in time.
Okay, okay. Because Nazir just informed me that he has another meeting with the PhD committee, so he will be not able to be chair the session.
Yeah, I can take over as soon as we come back, but I think we're starting at 12:30. No.
Yes, 12:40.
12:40.
Okay,
that might be a little bit tight for me. My apologies.
Okay, yeah. So you please please continue with your lunch with your guest. And
no, it's okay. I was just finishing because.
Yeah, and I will check with him if he can do at least the first one, and then the rest two you can take.
Okay, that would be fine.
Thank you very much. So thank you very much for all the attendees, our keynote speakers. Again, we will take a short break, and we will be available at 12:30.
Okay, I'll be back as fast as possible.
Thank you very much.
Thank you. Bye.
Bye-bye.
Ahmed? Hello? Ahmed?
Yes, Nazir bhai.
अच्छा ठीक, आप ऑनलाइन आ गए ना?
Yes, जी मैं. This is not mine. I think Samrana is going to speak now.
ठीक है.
And the organizer, can you please allow her to share the screen? The organizer, yeah. The camera on.
Yes, it's done.
Yes, बढ़िया. So,
okay, good.
बढ़िया. Yes. Yeah. Now, Samrana, you can share the screen.
How much time she has now?
30 minutes. 30
minutes. 30 minutes slot. Okay.
Yes. Yeah, the keynotes, and then I know you are very busy. You have another committee at 1 o'clock. So.
Oh no, I will introduce her first, and then.
Yeah.
And 215 participants.
Yeah, they will join. I think in the morning it was 3:25.
Yeah.
They went on a break, and they will come rapidly.
Yeah, Yusuf, can I start introducing Dr. Samrana?
Yes.
Okay. I thank you, Dr. Yusuf, for giving me this opportunity to share this session. My name is Naziruddin. I'm working at EPFL. I have a great pleasure to introduce Dr. Samrana Kazemi. She has collaborated even with me in some publications, and she is a doctorate from Jamia Millia University, Delhi, New Delhi, and she got a prestigious award, IUPAC and UNESCO award fellowship to work in Prague on micromolecular chemistry, and she is expert in energy and storage applications and nanotechnology. She has published over 40 publications with H-index of 26. So it's a great pleasure to introduce Samrana, and on her topic today, she will be presenting on perovskite solar cells to this audience. Samrana, welcome to you, and give back the floor to you. Share with your screen, please.
Okay. Good afternoon, everybody, and thank you, Professor Nazir, for the nice introduction, and thank you all the organizing committee members, especially Yusuf and Professor Ahmed. So as my title of my talk indicates, the designing of molecular semiconductors for perovskite solar cells. So I'm going to talk today about the application of molecular semiconductor as whole transporter material for perovskite solar cells. But before starting and to showing my results on perovskite solar cells, I would like to give a brief introduction about the molecular semiconductors. So yes, so the molecular semiconductors basically a class of the organic semiconductors, and these are the term organic semiconductor basically is used to describe the organic materials which has the pi conjugation. So they can be either small molecules such as oligothiophene, oligoacenes, or it can be pi conjugated polymers such as PTAA or P.PSS, polythiophene, which is the state-of-the-art polymer for organic solar cells. So depending on the applications, we can design a variety of the pi conjugated materials, which can be either oligomers such as spirometad, which has been used for the perovskite solar cells. But before starting the field of perovskite solar cell, I would like to give more stress about these pi conjugated small molecules and the polymers, because they have extraordinary properties in terms of the optoelectronic devices, because they have been known since 1950s for different applications. And why they are so important? Because they offer the cost-effective solution processing methods which can be used to develop lightweight and flexible optoelectronic devices. And the main important properties of this material is that wide chemical functionality, so that you can tune their optoelectronic properties along the whole visible spectrum. As you can see, these different colors materials, they are the small molecule based pi conjugated materials, and depending on your requirement, they can be prepared in a different ways. So as you can see, there are different applications, but they are not limited to these applications. There are a variety of more applications where these pi conjugated materials can be used. For example, if you want to use them in organic solar cells where you have to absorb more light, so you need thiophene based chromophoric materials which can absorb more light and have high absorption coefficient. Similarly, for if you want to use them organic light emitting diodes, we need some more photo emitting materials which can be emit more light and have high photoluminescence. For field effect transistors, they should have high charge carrier mobility. And similarly, for the optical sensors application, these materials should have high electrical conductivity. So these are some applications where we can use these organic semiconductors. But as I said, that they are not limited to this application. There are more wide applications where these materials can be used. And recently, in perovskite solar cells, they have just used it recently as a charge transporting layer. Either they can be more hole transporting or they can be also electron transporting materials. So with that, I would like to also show some materials which has been developed in our group for different applications. As you can see that by changing either the core or the side arms, you could attain a variety of materials and which can have also changing in the optical properties. So we can be starting from the UV range, we can have absorption in visible range, and it can be extend to the NIR range. So just changing the side group, for example, this is the triaramine group, and when we change this by adding the methoxy group, the color of the material changes. Similarly, when we change with this thiamyl group with this more stable material, this thiazole, carbazole, which doesn't absorb the light, then the absorption can be shifted to the UV visible region. So with that, I would like to start now my main topic in perovskite solar cells. So the outline of my talk will be the perovskite solar cell. I would like to just a brief introduction of our solar cells, as it has been already elaborated by Professor Nazir talk, and then I will talk mainly about the whole transporting material, which are based on the organic small molecules. And I will show some of the results on the different core base, which has like triazotruxic base, phenothiazine base, tetraindole base, and the recently developed the fluorinated triaramide base 2.3 STMs. So with that, I again start with the perovskite. That what is the perovskite? Perovskite is the mineral which is composed of inorganic halide and the organic halide, where A is the for the photovoltaic application, X should be the halide ions, and B can be the lead or tin, but we are using more the lead in this perovskite, and for the A cation, it could be methyl ammonium, formyldinium, and cesium cation. So why perovskite is more showing that because of this extraordinary properties of perovskite, it makes unique applications in photovoltaic. So, and because of this tunable direct band gap, it has a tunable direct band gap, which can be further tailored by changing the B cation or the X halide anion. It has high charge carrier mobility. It has ambipolar charge transport behavior, which means that it can itself transport electron and holes, and it has long diffusion length of electron and holes. And high optoelectronic quality means that it can be used not only for the solar cells, but it can be used for light emitting diodes, photodetector, and laser applications. So as I'm going to show you more results about the perovskite solar cell in the NIP configuration. Therefore, I would like to just explain about this. So in NIP configuration, where we have the FTO, which is the transmitting conductor side, followed by the electron transporting layer, deposited the electron transporting, which is basically the blocking TiO2, and followed by mesoporous TiO2, and then we deposit here the perovskite of different compositions, followed by the whole transporting material, and then deposited the metal cathode. So as we see that this perovskite solar cells shows is a rising start in thin film emerging period technology, and just in less than a decade, it has reached up to 26% efficient, less than 26% efficiency. So the maximum efficiency to 25.6% is achieved just in less than a decade. So the reason why it has more potential, because it is also use the less material compared to the silicon technologies, and also it allows different deposition techniques such as spin coating, spray coating at the lab scale, and at the large scale we can use the slot die cutting, inkjet printing, and also it can be used for tandem solar cells. So we can make a wide gap perovskite solar cell using bromide perovskite solar cell, or it can be the low band gap perovskite, which can be made by using the iodide based perovskite. So although for any type of technology, there are always a triangle golden rule which has to be fulfilled before it comes to the market. So perovskite basically already fulfill the low cost and high efficiency, but the high stability is always remains an issue in case of perovskite. Although there are different this has been trying to solve, as we have seen already in the Professor Nazir talk, that by making the 2D and 3D perovskite, or making some other passivation molecules over the perovskite, it can improve the perovskite and the penetration of humidity into the perovskite, because perovskite is basically a salt, and it is very sensitive to the moisture and oxygen. So one of the reason of the perovskite instability is perovskite intrinsic instability of the perovskite itself. The other, as we know, that perovskite solar cell is made of the different layers. So this is not only the perovskite who contribute in the performance and the stability, but the other layers who also equally or more or less responsible for the performance and stability. The other thing which comes with the electron transporting layer, and we found that this TiO2 is basically is UV unstable, and we need some other material who is UV stable and which has higher electron mobility to replace this TiO2. And recently, I also in our group, and also as Professor Nazir has shown, that by replacing TiO2 by tin oxide, or by modification of this TiO2 by other layers, we can overcome also these problems. And then there is another thing also, that we need some moisture resistant encapsulation, which is also one of the research direction where people can contribute more, and this is very actually less directed research. So we need some actually also more encapsulating material which can encapsulate perovskite apart from the charge transporting layer. So today I'm going to talk about more about this materials for hole transporter, because you see this is the more important in an IP perovskite solar cell, because it's the top layer of the perovskite, and which affects also the stability of the perovskite layer. So with that, I would like to tell you about that for an ideal hole transporting layer, we should have some 4 golden laws. That, like, for example, it should be efficient, it should be stable, it should be low cost, and of course it should be dopant free, which is basically sometimes not possible. And we are still trying to get some dopant free materials. So as basic, the main role of the whole transporting layer is to extract hole and to transport to the metal contact. So so one of the main important requirements of the whole transport layer is that it should have the aligned energy level with respect to the perovskite. And it should make a nice film over the perovskite layer, so that it should have the full coverage. And then it should have also some the good interfacial contact with the perovskite layer. So if you want to achieve the doping-free HTM, then we should have also high hole mobility. And of course, to reduce the cost of the perovskite solar cell, we should have also reduce cost of the whole transport material. So we need to find some cheap synthesis which has the less purification method and less step for the synthesis. And for the stability, again, we should have also the morphologically and UV stable molecule, which can allow to cover the perovskite without degradation. So as we know that the state in the NiP perovskite solar cell, the spirometard, which is also a small molecule, is always been the state of the art STM, because basically it fulfill all the basic requirement of being whole transporting materials, except that is poor charge transport properties. It has poor, very low electrical conductivity and very low charge carryability because of its twisted structure. So to improve its electrical properties, we need to dope it by the different salts, such as lithium TFSI, and to add some additives to improve its morphology. So, but on the other hand, these salts are hygroscopic and tend to degrade the perovskite solar cells. Therefore, this is the challenge to find a new whole transporting materials, which is either dopant free, or we need to find some different doping agents, which are the hydrophobic dopants, and which can increase the stability as well as the performance of the solar cells. So we have been working in these directions, but today talk will be just talking about the whole transporting materials and how we can, by molecular engineering, how we can improve their optoelectronic properties. So here I showed you some of the most important building blocks for whole transport material, which has been used for perovskite solar cells and also for the other optoelectronic applications. As we can see that this is bifluorine is the building block of the spirometard, which is already achieved 25%, 5% efficiency. And recently, even with the highest efficiency which they achieved has been used, they have also used the spirometard as an STM. So we are still looking for the whole transporting materials which can completely replace the spirometard. But as I have shown you that the ideal material is it's never exists. So we have always some drawbacks in the materials which we synthesize and design. So the other molecule which I really like more is the trisotruxine based whole transport material, which has also achieved 19 to 20% efficiency even as a dopant-free whole transport materials. But the problem with this material is the yield. The yield is basically very low. So then you have again a little bit expensive whole transport material. Paraffin-based whole transport material play a very important role because they are also cost-effective and can reach also 20 to 21% efficiency. And then comes to the carbazole. Carbazole is also very cost-effective, and they are very thermally and morphologically stable building blocks. So by using them, we can make also cost-effective material, and the efficiency recently in our group also achieved 17 to 18%. And then it comes the triphenyllamine building block, which has basically, because of the presence of the nitrogen, which has electron-rich electron donor molecule, so the atom, so that's why they shows a higher electrical conductivity. So basically adding these molecules, these building blocks can improve the electrical properties in the materials for the whole transport material. And then it comes to the the phthalocyanine, which is also a very robust material, and we have been also working with this in collaboration with other collaborators. So we also achieved around 18% efficiency using the different type of phthalocyanine. So these are the basically few examples, not published by our labs and also by the other collaborators, and they are dopant-free STMs and have shown different performance using different building blocks. So basically this is based on the trisotruxine, this is the thiophene, the trialamine based, this is the TIPS pentacene, which has been used by our group, and this is another trisotruxine based molecule. So I mean to say that by using different cores and different side groups, there is a wide possibility to use them not only for the solar cells but also for the other applications. So with that, I would like to show you now some of the results, starting with the trisotruxine based STM. This is a very actually interesting and the important building block, which has basically this tri-indole units combined with the phenyl ring in the center. That's why it makes more planar molecule. And we thought of using this material because this material is basically not new, but it has been used before for the other optical electrical devices. And we have chosen this material because it has basically very aligned energy level with respect to the perovskite MAPVI3, and also it has considerable hole mobility, and it's thermally stable up to 340 degree. And the most important thing is that it's optically transparent, so it doesn't absorb any light in the visible region. So, but only the drawback of this material was that it was very less soluble in the non-polar solvent. That's why we could not use it by the solution process method. So we did this work in a collaboration with the Hank Bolling, and because they have the expertise in the vacuum deposition techniques, and we made the solar cells in inverted planar PIN junction, and where we deposit first deposit the STM over the FTO, and then perovskite, and then the N-type layers such as the PCPM or the C60. So what we did, we found that when we use just this, we called it TBDI. When we use this TBDI as a whole transport materials, we just got the 7% efficiency with the voltage 1. And here you can see this JV curves where you have just TBDI, and this shows the S-shaped curve, which means that there is some energetic hole barrier between the perovskite and the whole transport material. So to overcome this, we use an additional layer of the interfacial layer of the molybdenum tetroxide between the TBDI and the ITO. So after adding this MO3 interfacial layer along with the TBDI, we have reached 14%, almost 15% efficiency, and also improving the fill factor. So, so from the take-home message from here is that the proper energy alignment of the whole transport material is very important for the efficient whole extraction and the whole transport. Followed by this and inspired by this molecule, then what we did, we tried some synthesis of these materials, adding some molecules such as this hexaloxyphenyl and and alkyl chains to make it more soluble. And again, we found that this is different types of KBTI, these trisine-based molecules can deliver better efficiency with respect to the MAPVI3 perovskite solar cells. However, again, we found that the efficiency were very low, and without dopant, we got the 9% efficiency. But when we add some dopants, that it reaches the 10%. It means that there are some lack of the mobility, which can be improved after adding the dopants. But we were not satisfied with those results. Then what we did, we further did some more molecular engineering of these materials, and we add some more molecules on the periphery of this HMDI. And then what we found, and adding more phenyl hexaloxy molecule on this HMDI molecules, from the 8%, we could achieve almost 19% efficiency. So, with this, we can see that this molecule is almost having the same energy level like spirometad, by just changing periphery molecules over this triazotine base core. We could more levelize the energy levels and improve the whole extraction ability. So with this on, so this is another, this is the same example of this molecule, triazotine molecule. And here I would like to show that how by just molecular engineering of the molecule from the simple molecule based on triazotine, we can make more extended pi conjugation molecule, and also we can improve and extend the optical properties from the UV range to the more visible range. And also it can change, also modify the energy levels between the perovskite and the STM level. So with this inspiring with this trazodone molecule, we recently also found out that similar to the triindole based trizotrixene, there could be some other molecule which can be also interesting molecule for whole transporting as a whole transporting material for perovskite solar cell. And we found that based on the tetraindole units, which is connected to the cyclooctatetrene molecule, we found that this molecule is also can be suitable for because of the energy level we have calculated by the DFT calculations, and because of this moderate hole mobility, we need to dope these materials because in undoped form it has very low efficiency. So we thought we have it a planar molecule, but we found by the DFT calculation that it has non-planar satellite structure, and because of this, it has the twisted structure which shows non-planarity. Therefore, we need to dope it with the different salt, with the lithium salts and using TPP as an additive. And by using this molecule, what we found that when we use them as a dope, we called it TTI. And when we use it instead of a spirometers, we got efficiency around 15.8%. And by looking the PV parameter, we saw that the voltage was very low compared to the spiro, because also the current was low, but the fill factor was very high. So what we thought that it means that if we have the lower voltage, it means that there is some problem of the proper energy alignment. And with that, also, if you look the steady state photoluminescent efficiency, which tell about the whole extractions by the whole transient material to the perovskite, so we can see that black one is the photoluminescence of the pure perovskite, pristine perovskite, and upon depositing the SGM, the luminescence efficiency quenched or reduced with respect to the perovskite. So when we use the perovskite with spirometer, it shows higher photoluminescence quenching than the TTI. It means that it has less extraction than compared to the spirometer. It means there is a problem with the proper energy alignment, and what we did, we used this TTI as an interfacial layer between the perovskite and the spirometer. A very thin layer of the TTI is used as an interfacial layer just to overcome and to proper energy alignment. And we found that after adding this TTI between the MAPI and the spiro, we got higher voltage, and also the current is improved, and as well as the fill factor is improved. And the final efficiency what we achieved is was the higher than the spiro, and we got the 19% efficiency. So the reason of using this TTI as an in between the spiro, it was not only for just as we call it as a graded whole extractor, but also we found that probably it also improves and reduces the defect, because it could have also the nitrogen atoms can actually passivate with the vacancies in the perovskite solar cells. So to check this, that if it has some interaction with the perovskite surface, we did some extra electron spectroscopy of the pure perovskite and the TTI passivated perovskite film. XPS gives nice information about the surface interaction of the molecules. So we did for different elements, but here I just want to show about the lead and the iodine. So in the case of lead, for the pure perovskite, we have this position of this 4F lead, which is found at around 142 and 136. And when we deposit the TTI, this peak of the lead shifted towards the lower binding energy. So that the shifting of this peak towards lower binding energy basically indicates that we are decreasing lowering the oxidation state, because we have the electron donation of the NH group present in the TTI to the uncoordinated lead ion. Similar way, the iodine also shifted to the lower energy, so showing that the defects can be passivated by this TTI molecule. So also we did some device stability test that when the presence of just spiro, when we have the spiro, the device degraded very fast. But in the presence of TTI, the devices can go further, longer than the pure spiro. And also it improves also the hydrophobicity of the perovskite solar cell. So now another molecule recently we came through interesting molecules based on the phenothiazine pore. So this is basically the phenothiazine molecule, which is electron rich because of the presence of the sulfur and the nitrogen. And if we combine these electron rich molecules, because it is also cost effective and also electron rich. So if we combine these molecules with the arms, which has the carbazole molecule, we thought that it could be an interesting molecule from the point of view to improve the charge transfer properties and also the planarity. So through study of these materials, we have synthesized two molecules which has the same almost the same structure, except that instead of this molecule, it has the sulfur, and then just to adding here these two oxygen molecule, which we called it the sulfone. So basically now the sulfur is the electron donating, and then when we add this oxygen molecule, it's electron withdrawing. So just to see the effect of this electron donating and electron withdrawing group onto the optoelectrical properties and the photovoltaic properties, we also did some DFT calculation to calculate the HOMO energy level and also to calculate the dihedral angle. So the dihedral angle basically tell you about the planarity of the molecule. So the more lower angle means the more planarity, and then it means that we can have much better molecular stacking of the molecule, and it improves the charge transfer properties. So with this, we use them for first we did some optoelectrical measurements. We prepare some test films to measure the absorption, and the CV measurements were done to also calculate the homolume level to energy levels, and to see the thermal stability. We did the TGA, calculate the conductivity. We did some IV measurements, and also we calculated the electron hole mobility by CLC measurement. And we found that compared to the PTA, which has the sulfur group, compared to this group, the sulfone group has better intramolecular charge transfer properties, as it shows absorption in this 350 higher absorption in the visible region, and which could be also seen reflected by the its properties in the later in EQ measurements. And in the CV measurements, we can see that this usually always this electron withdrawing group always make a HOMO level makes more lower energy levels. That's why if you look here with the PTO has more higher oxidation potential compared to this the PTA base, and the low homolume experimentally calculated for the PTO was found by 5.62, while for the PTA base was 5.58, which is more upper than the PTO base. So basically PTO based energy level is more aligned with respect to the perovskite, which we have been used in this type of solar cell. And similarly, the conductivity of this material was found higher than this PTA base because of the molecular packing. And as well as the mobility was also higher in this electron withdrawing geo-based molecule. So then we incorporated these materials in the NIP based perovskite solar cells, where the devices shows a nice efficiency and also less hysteresis. So in case of the PTA, we found the efficiency reached to 17. While in case of PTO based, the electron withdrawing sulfone group based efficiency reached around 17.8, which are higher than the PTA based one. And in terms of the cost, we also calculated the cost of these materials, which comes around 32 euro per grams, which is quite compared to the Spiro, which has the very high cost around 400 euro per gram. This cost is really very low. So also we have done some device kinetics just to see that how they have the whole extraction efficiency. We did steady-state luminescence, and we found that compared to the prior perovskite, this PTA and PTO base shows reducing efficiency. And also we did some dark JV measurements, which is actually a nice indicator of the efficiency of solar cell, which can tell you about the lower value of the reverse saturation current, which can be calculated by this formula. So the lower value of the reverse saturation current is an indicator of increasing the voltage and reducing the charge recombinations. So in case of PTO, we found the lower voltage, lower reverse saturation current than the PTA based one. Further, the long-term stability measurements were also done for these measurements, and we found that for when we age these devices for humidity measurements, then these materials has the higher stability up to 1000 hours. And when we heated them under moisture, and when we continuously heating at 85 degrees centigrade, they could sustain up to 50 hours. Both of the material can sustain, but the maximum stability was found in case of the PTO based materials. And also we did under different and stress conditions of these materials, and the comparison was done with respect to the spirometers. And we found that the PTO based whole transfer material, PTO based solar cells have the higher stability under moisture and light than the spiro-based devices. And now recently, we were very motivated with the article published in the Science, where they have shown the spirometer, which was functionalized by the fluorinated side groups. And they have developed this spirometer by adding this fluoro group at ortho and meta positions, because of the fluorine, the benefits of fluorine group that they have. They can lower the homo level, and also they can increase the hydrophobicity of the materials and also the molecular packing. But again, the spirometer is again very expensive materials itself. So, but we got this idea, and we synthesized the molecule in our group, which is very simple and very cost easy to make, and achieving the high yields. And we have used a very simple triaramine based molecule, the core, because it improves the electrical conductivity. And then we just use this fluorinated molecule on the side group of this triaramine. And to comparison, we also synthesized this orthomethoxy based triaramine STM, just to compare and to see the effect of the fluorine atoms on the optoelectrical properties and also the PV performance. So as I told you, that the fluorine groups basically improves the hydrophobicity, and also it lowers the HOMO levels. So as we can see here, that in case of fluorine based STM, we had the 4.9 electron volts, while in case of FO, in case of without fluorine, we have little bit higher energy level. And the main important thing and to notice here is that the material which we use is a very thin layer of the material, so that we use also very low materials. And the good and the extraordinary property of this material is that it has the better film forming properties than this orthomethoxy. And also by using a very thin layer of the FOME, we have achieved almost a similar efficiency than Spiro. So we used first we did the optoelectrical measurements and the thermal properties. As we can see that the absorption of these two materials shown basically in the around the 337 nanometer for the FOMO, while for the OME it shifts to the red. But the reason why it shifted to the blue shifting in case of FOMO is because of that it has the electron withdrawing properties because of the presence of the fluorine, and it has also the little bit wide band gap than the orthomethoxy based one. and the conductivity of the FOMO and the mobility of this FOMA is higher than the OME-based SGM. So then also we saw the effect of the film forming properties on the photovoltaic performance. We found that when we deposit this FOMA, it makes a very uniform full coverage over the perovskite, while in case of OME-based, it is basically crystallized over the surface. That's why it makes a non-uniform coverage over the perovskite. And by making the device with the mixed perovskite solar cells, we found that it has the efficiency can be the voltage is improved, and also it shows almost the similar AQE like the spirometad. And in terms of the device kinetics, we also see the whole extraction ability, which can be seen that with the respect to the FOMO, the spirometad has the the OMO based has shown the lower extraction than the FOMO. So also just
sorry to interrupt, but we need to start concluding because
okay. So just I'm just almost concluding it. So just to see also that this fluorinated STM interacts with the perovskite. We also did some XPS interaction, and we found similarly like the other STM, we found that there is some interaction taking place, and the lead-based core spectrum of shifting peaks towards the lower binding energy, which is confirming the interaction with this. And the most important thing, which I would like to show, that the hydrophobicity, in case of this FOMO, we have the higher hydrophobicity than the spirometad and or based on the OME based. With that, I would like to conclude my talk, and I just want to tell you about this materials which we have been used. That probably that is dopant-free STMs, and if you want to achieve high mobility, we have to have the planarity and more molecular packing in the material itself, and to facilitate fast charge transport, we should have also proper energy level. And probably this fluorinated arms with TPA core really emerge as an efficient and cost-effective dopant-free STM. And with further optimization and device engineering, I think we could achieve more higher efficiency in the future. With that, I would like to conclude. We'd like to thank to all the collaborators and all the group members of my team. Thank you all for listening.
Thank you very much, Dr. Kazim, for a very nice lecture. We have time for one or two very quick questions because we are considerably behind schedule already. We have one on the chat, but I don't know if this is really, but maybe you can help us answer it. It comes from Mr. Loshami Tariq, influence of crystallography and crystallochemistry of materials on the yield of PV systems. I'm not sure if you really discussed the crystallinity, but do you have any thoughts on the influence of the crystallinity on the yield of the PV systems?
Sorry, I couldn't get the question completely.
If you have any thoughts on the influence of crystallinity on the yield of the PV, of the yield of the system, PV system.
They need to be ordered.
Yeah, of course, the crystallinity. Yes, the thing is, we need crystallinity to improve the charge mobility. But on the other hand, if we have the crystalline, completely crystalline STM, then it's difficult to cover the surface of the perovskite. That's why, as I showed in the last STM one, that this orthomethoxy-based STM are more crystalline than the fluorinated one. That is why it was difficult to cover the whole surface. So we need some crystallinity, but if it's completely crystalline, then it's difficult to get a uniform coverage.
Okay. Thank you very much. I'm afraid that's all the time we have. So if you can stop sharing your screen, we'll move on to the next speaker. So in the meantime,
please allow me to share my screen. Oh, yes. Thank you very much.
I don't think it's me that does that because there you go. If you haven't guessed, I'm taking over the chairing of this session. My name is Dario Bassani from Bordeaux, and I'm very, very pleased to introduce our next speaker, which is Professor Shahzada Ahmed. who is originally from India, but did his PhD in the Polymer Institute for Polymer Research. He was then able to secure a very selective Humboldt Fellowship to work in the Max Planck Institute, and then has, after some other travels, is now a full professor, IRSEC professor at the Center for Nanosciences in the Basque Country. So he's going to be giving us a talk on the engineering of perovskites for maximum electricity harvesting, and we're very pleased to listen to his lecture. Please, whenever you're ready.
Thank you very much for Professor Basseni for your very kind introduction. Thank you, organizers, for assembling such a fantastic talk on the topics. And tomorrow also, I believe, a very good talks coming from the speakers on the battery. So I will follow up on our talk on the perovskite solar cells. And today, Professor Naziruddin has given an excellent overview of that. So this saved a lot of my efforts also. So I'm very thankful to him also. As suggested, my name is Shahzada Ahmed. We work on perovskite solar cells. And we are also being funded by European Research Councils, the Premier League in the research. The outline of my talk will give you a flavor of thin film PV and what we work on perovskite as a light harvester and what's the future outlook. But I personally believe that any emerging solar cell, either doesn't matter as a perovskite, organic, dye-sensitized solar cell, is educating us. This technology is poised to educate, inspire, and connecting people like we are doing today, connecting with you like-minded people. One of my job is to ignite your minds to pursue this area for your further research and developments. I want to bring to your attention this the papers published last year by more than 11,200 signatories. It was basically the main author was Ripple, Wolf, Newsom, and Bonanza, and they say it's a climate emergency. It is a climate emergency. It's now it's now time to act. We cannot delay much. We cannot delay much because our world population is increasing as a 15% every 10 years, and by 2030 we will be almost 8 billion from the current 6.2 billions. And then our power consumption from 15 to 16 terawatt will go to 30 terawatt. Where are the energy? Where are the source of the energy? And if we will burn more carbon, we will emit more CO2. You see, the CO2 level is increasing. Right now, the CO2 level is, we are contributing to 850. We are contributing 870 gigawatt to our atmosphere. Business as usual is completely not acceptable. We cannot go it this way. Otherwise, believe me, we will have a next catastrophe like currently we are facing. So we need to capture our CO2 emission. We need to capture our CO2 emission, and for this, we need battery of new technology. We need a battery of technology. And we have to look for a source which is cheap and effective to generate electricity. Ideally, this can be one of the options, but unfortunately, it's not possible. So let's move about the sky scenario of the cell, which is a British company, which just last year is published a very good sky scenario. And we signed a Paris Agreement in 2016. It's almost 5 years, and we still have not fulfilled all the conditions, and we are far away from that one. Today, almost 6% to 8% of our electricity is coming from the PV, but by 2070, by 2050, 1/3 of the electricity will come from the PV, and PV. And then hydrogen is also a main vector, and it will be, the European Union is debating as a main vector for the energy carrier, and most of the trucks will run on the hydrogen. And equally, electric vehicles are like new battery storage. Tomorrow we will have a very good talks coming, are more important to store the battery. And by doing so, Europe are going in 2050 carbon neutral. Some country will want before 2040. But we believe that if we will follow our guideline, we will care more how much we burn rather than how much we earn. Our planet will be a beautiful place to live. By 2070, we will be a carbon neutral planet to live. If you look at this graph about the generation of electricity from, I took it from International Renewable Energy Agency. So in most of the part of the world, if you see the gray area here, renewables are much more cheaper than burning fossil fuels. If you look at the PV has come down drastically from 200 watt per peak in 1960 to almost 20 watt per peak today. So the gray area is from the is of burning fossil fuels. Similarly, it has come down. It's going down and down every time. CSP, which is also a technology, but this is more engineering to us, and it requires a lot of engineering. And the price has come down, but it still doesn't compete to the PV, but good for the country which is blessed with the sun, like Morocco. We have installed, my last company, has installed many CSP power plants in Israel. In south of Spain, we have a CSP power plant. Wind is also a cheapest source of electricity. Wind is also a cheapest source of electricity. You can see the LCOE, levelized cost of electricity, has gone down. Similarly, offshore wind and onshore wind, onshore wind is more cheaper because we don't have to transmit. So believe me, fossil fuels are much more costly than burning, than going from renewable energy. This is the graph. I think European Union, other map paper, making this. If we have to make a complete transition, and we have to look for the new material, as in the morning, Professor Sanjay Mathur has commented about a range of new materials and how we can use them. Professor Nazaruddin has also talked about it. Photovoltaics is a new type of photovoltaics is working for the last decades on dye and perovskite solar cells. So we look at materials, and these materials are an integral part of new technologies. So for energy harvesting, we look for photovoltaics, and most of the European space is also occupied by building, almost 30%. So BIPV is also one of the main things they are looking for. So you can harvest your windows electricity. CSP, some part of the world, they are successful. Wind power, batteries beyond lithium. Lithium is currently a very good thing, but the value chain, supply chain is not optimal. They have to be from Chile, they have to go back to China, then they back to Korea, and then come back again to Europe. So we have to look for a new battery which can be locally produced. Batteries beyond lithium, supercaps, fuel cells, hydrogen generation, and CO2 captures. So these are some of the milestones which need to be fulfilled. And here the aim is to find a source for energy conversion for a PV, which consume less material, which has the flexibility and aesthetic benefit. Levelized cost of electricity also should be lower, and it should show 25+ year of lifetime, which is currently only possible with silicon. So most of the new emerging solar cells are in the R&D stage in the laboratory, and silicon is the king of the market because this guy has a level of 25+ years of 25 years of 20 years of lifetime. But we need a new technology, and we need to take the risk to go to the market and make the technology more strong. So that we have to think beyond silicons, and now IoT is also increasing. So if the new solar cells are not very effective, they can also find more application in Internet of Things, a small area, as a self-powered sensor, because we are using much more and more and more of a sensor. Minimize the supply chain. The solar cell should be locally produced, so it will create jobs, and they should not be dependent on one material. And the cost should be less than 20 cent watt per phase. We have to look for this one, which can also harmonize with the greenhouses to make vegetables. If I have to divide the PV scenario, I will divide into 3 sections. I told you the silicon was first invented in Bell Lab in 1960. We call them H1. H1 is also cash cow, generating all the industries. If you go them, you will make money for them. So it is the H1 is the first generation of them. Similarly, 3.5. The 3.5 is also very, very efficient solar cell, but they are costly and they cannot compete today with the cost of the silicon which is giving. Then in the early 80s, it comes thin-film solar cell. Thin-film solar cell like CIGS, copper, indium, gallium selenide. Then you have the lower energy. Indium is costly. If you will replace indium with the zinc, you have a castrides. So CIGS is 25% efficient, but castrides is almost 12.6%. So lower efficiency is difficult. Then in the last 2 decades or 25 years, many other new vectors come into the market, like dye-sensitized solar cells, the oldest one. Then organic solar cells, which is also very good, giving 20% efficiency today. And perovskite solar cell, which is giving you 25% of technology. It's the new technology we call embryonic technology. It is the laboratory, a whole community is working to make them more efficient. And we believe that some of them, like quantum dot solar cells, one of them will go to the market in the coming days. One of the advantage of these type of solar cells is the emerging solar cells, they absorb in the visible part of the spectrum. And silicon absorb in the near NIR part of the spectrum. So this is also good to make a tandem devices. By doing so, you can absorb visible part in the emerging solar cells, infrared part in the CI, in the silicon solar cell, and you can increase the performance. And silicon with perovskite at 30% has been shown by half more than Oxford people. But for me, it is also a double-edged sword because today silicon is very, very not only efficient, but also a strong 25-year lifetime, and perovskite is not. So this is a technology. And this is I'm sharing with you the graph of an NREL chart, which shows that how you will see the rocket. The rocket is rising in the red colors. In just a decade, it has increased now 25.5%. While the almost other technologies are flat. And organic solar cell in recent years, last 3-4 years, it's shown a very good jump, and now 18.2% is certified, and while 19%, 20% has been reported in the lab. This is also a very, very efficient technology. And if you look with the graph of the silicon, it's almost flat. They have no development in the current, there was no development in the efficiency in the last 20 years, while the cost has been cut down. And this is the crossover. We have a very, for a technology, you need high efficiency, low cost, but you also need a stability. This is the missing link between our R&D, and we need to solve it. Currently, perovskite is facing some challenges. The challenges are phase transformation, like methyl ammonium tetraiodide. It changes its phase. Halide segregation, mixed perovskite give you the maximum efficiency, but now we learn that it also have a halide segregation. Ion migration, because ionic radii of iodine is low, so it's also migrate. Crystal size expansion, when we put them under a stress condition, light and heat, the crystal size expand or skews. And mixed phase also halide also suffer from low band gap, high band gap diamond, because sometimes they have a phase. This is the cross-section cartoon of a perovskite solar cell. Just to give you perovskite the light harvest, it absorbs light and then it generates electron and hole pair, and which then travel to the respective electrons. With the presence of a p-type and n-type contact, they are being collected. And just to tell you about the thickness of the silicon solar cell is 200 micron. Give you 25.6%. Perovskite is 300 to 500 nanometer, give you same efficiency. So the active thickness of the device is less than a micron. You cannot see from your naked eye. This is again, we always talk also about the market saturity and market penetration, which are the technologies to go that. So silicon has reached the market saturations, is everywhere being installed, but we need 100 times more silicon or any PV technology in order to achieve carbon neutrality. But if you look at the last one, emerging topic, biosensitized solar cells, this is also good for a small area applications like sensing here. Perovskite is almost ready, but we have to solve the problem before we can make an entry to the market. Organic polymers. CIGS is a very efficient technology, but due to the cost, it cannot compete with the silicon and similar castorides. The cadmium telluride is an efficient, also low cost, but there are not enough tellurium is available on our planet, and only one company, First Solar, is making cadmium telluride. So this is the perovskite is now the solar cell technology, which can be produced mass production, because we are not dependent on a one material. We are avoiding the monopoly of the materials. We are material independent. You can select any other type of diverse type of charge selection, p-type and n-type. Just we have listened talk of different type of p-types. We can choose on that one. And this. So by today, as I said, today we are having 5% electricity from PV. By 2070, it will be 1/3 of the electricity will come from PV, and this will not go in one shot. It will go in a phase-by-phase manner, because we need to either install the capacity of the silicon production or make entry room for the new technology. So silicon is a fantastic product. I don't want to touch it. We were looking for a new thin film market, which has a lower LCOE, levelized cost of electricity, like cadmium telluride here. Is the lowest. By the way, silicon levelized cost electricity is not the lowest. Cadmium telluride has the lowest cost of electricity. And then if you will calculate, like this morning also Nazaruddin has given a talk. So if NREL has also calculated, is it less than 20 cents watt per peak here? And why it happened? Because I told you we use very low material uses. Thickness of the material is low, and we use low cost processing. We don't very energy intensive process. Silicon is 99.9999959 purity, and to achieve this 59 purity, you have to heat them at 1400 degrees centigrade. It's an energy intensive process, and we don't require them because we are our semiconductor perovskite is much more tolerant, so you can achieve similar lifetime. And another term we use is energy payback time, how much energy you will consume in production, and what's the energy payback time. So energy payback time is also lowest for the emerging technology like OPV and this. I passed this one that perovskite is a semiconductor. We are not only good for solar cells, but you have many other applications like light emission, radiation, X-ray converter, quantum devices. We are also working on neuromorphic devices. So, and the challenges is to avoid any dopant. We used to use passivation structure because perovskite is a very polar material, and engineering the conformation. So some of you, which is new to the PV field, I just want to introduce you this graph that I always talk about efficiency, what this is. So efficiency is what this call it. So the short circuit current you achieve at the VOC, in open circuit voltage, and this is where the maximum power point is here. It's called fill factor. So if you multiply all these factors, the short circuit current into VOC into fill factor at once, and you will get the efficiency. And your good solar cells should show a zero current at the dark. So there's no recombination. If there's a current is not zero, it means there are inherent recombinations phenomenon is going on. This is a loss for us. Similarly, the good solar cells, we will say they should be efficient in charge separation and extraction of a carrier with both N-type and P-type layer. What we don't want is recombination. We don't want electron and hole to recombine because there's a thermal loss for us and it drops the efficiency. And we always try to minimize the contact resistance. So if you look at this graph with the full arrow is the desirable process, what we want. The dotted arrow is undesirable process, which we don't want, and we want to avoid it by means of doing many different things. So for this, we do VOC is the open circuit potential. We will optimize it. We can minimize, we can increase it by minimizing the undesirable process. For this, we do passivation approach. We do charge selective contact, rational and band alignment, grain size, and orientation of the molecule, which we recently published a very good paper from Daria Passetti, professor, and we have parallel and perpendicular orientation of the molecule we found, which was used as an interface layer. This is my lab is working in a holistic manner in a different type of all the full value chain of the perovskite, developing N-type perovskite layer, sorry, N-type charge selective layer, P-type charge selective layer, passivation approach, new dopants, organic semiconductors, and different stat defects. When we worked in 2012, was first of all, we started to work, we were working on methyl ammonium, but now we know that it's not stable, it changes its phase. Also, crystal size very smaller. So by working up in almost 10 decades with many composition engineering, etc., now our crystal size are larger. We do solvent annealing approach here to make break the crystal so that it can be larger. Now, and there's another group we don't work on, but there's another school of thoughts which also do evaporation. This is also a very good technique. You can evaporate your perovskite by sublimation. And one good thing is that I like about evaporation is you can precisely control the thickness, because then your device will be more and more reproducible because you have a quartz crystal macrovalence in your evaporation and the device will be more reproducible. So all these components you can, with all these perovskite, methyl ammonium, triple cations, only cesium or tin, you can come, this is the microstructure, and you'll see the grains are smaller in the evaporation of the perovskite than what we do in solution process perovskite. Now coming back to the today of the stability, which is the topic, the hot topic which everybody is talking about. Methyl ammonium is, we know that it's it changes its fate at 80 degrees from beta phase to alpha phase, the monoclinic to triclinic at 75 degrees C. Similarly, FAPI, we know that it's converted to alpha phase very fast, it's dark color, it became yellow very fast, so it means it's a photo inactive phase, it doesn't work out. A couple of years back, people completely inorganic perovskite, they were very excited because this is an inorganic crystal, much more stable, organic cation free, but this also has a phase separation problems, and this is an issue with that one. So coming to, and most of the efficient perovskites which has been reported are mixed perovskite. Mixed perovskite means they have a methyl ammonium, they have a formaldinium, they have an iodine, and they have a bromine. So 2 cation and 2 anion, or 3 cations sometimes. So, and what happens with time, they have a halide segregation. So if you do Kelvin force microscopy, if you put under the microscope, you will see they have, this is the ideal condition in the dark, but when you shine a light of the solar cell has to work with the light, there's a halide segregation, they make friendship. All the iodine will go to each other and say, hello, I am iodine, hello, I am iodine, and they will sit together. The bromide will say, hello, I am bromidine, I am bromide, I will sit together. So they will make a friendship, and they will segregate, iodine will segregate. In a ghetto, bromide will segregate in a ghetto. This is not good for us because the band gap variation. This is the high band gap domain and low band gap. Then coming to also mixed perovskite is iodine and bromide, the migration, the energy of different ionic radii is different. So the migration will be different. Iodine will be migrated, so bromide will migrate, and they will be not typically four places. So this is a wonderful paper published by Joachim Mein and one last year on the light, they segregate here. And all this by doing, what they did is the tolerance factor is not the same. And tolerance factor is what we measurement, is our measurement of the quality, how they are behaving. So tolerance factor near to 1 is a much more stable phase of the perovskite. This is my friend Ming Wang published last year. Similarly, what we started to work on formaldinium, pure formaldinium FAPBI3. Since last year, we are working on that one, and our work is going slow due to the current ongoing situation. And we just making a fully processable powder. So it's also very good for our physicists trained. They can just take this powder here and make it a spin coat. So we are making an, and because if we will make it two precursor making, sometimes we have an unreacted lead which can impede your performance here. So we took it here fully powder processable, resynthesized FAPBI powder. And then we also added cesium to make them more stable. But apart from being stable, we also find that if you add cesium, we are able to lowering the annealing temperature to almost half, to just 80 degrees. And the devices and the crystals you can see is much more sharper than the pure heaping in the FAPI, because FAPI demands heating 150 degrees centigrade to convert to the crystalline phase, while methyl ammonium is sufficient to 100 degrees. But by adding cesium, we just thought that 80 degrees is sufficient to do that. It's very easy. It's not very difficult to make this powder processable, fully processable. So we can just do them and process it, and then we can spin coat it. And you can see if we do that, this is normal FAPI. What we is achieved from two precursor methods, and while this is what our powder processable, they give you more reproducible results. They give you higher performance here, and the device showed also less hysteresis here. Similarly, very excited, Haris was all excited with this one. So he said, okay, we are making yellow phase. Why cannot we make a delta phase, a black color powder, which is more efficient? So then Haris synthesized the delta phase powder. And we found this is much more stable. So we preheat the powder also at 80 degrees centigrade or 100 degrees centigrade, then a spin coat. So we look at this, this is our powder with FAPI. Sorry, this is the precursor method. Mixing two components, formaldinium and lead iodide, and 100 hours it became yellow. Yellow is only the organic, yellow is only the lead iodide, it's not photoactive. The delta FAPI is good, but when we make an alpha FAPI, we deposit it was even stable with the moisture exposure. Similarly, we give thermal treatment, you can see the black color is these stones there. There was no change in the absorption, so we were not able to shift the absorption to any for a good and the bad. So there was no shift in absorption because the material was the same, only the processing condition was different. The devices gave performance better than the previous one, and there were no hysteresis, the main thing. But the good thing was the Auerbach energy. Auerbach energy decreases, you see. The Auerbach energy is decreasing. The Auerbach energy is decreasing means ordering, we are increasing the ordering in the crystal. And if we will increase the ordering in the crystal, the VOC will increase, the voltage deficit will be less. And then you can see the blue curve, the voltage deficit, sorry, the voltage is decreasing. Auerbach energy will decrease, the voltage will decrease. And also we calculated microstrain from this equation, Williamson-Hall equations, the strain energy, the strain energy decreases. So crystal became more, they can be a more stress shock absorber. And by measuring at maximum power points for a short duration of a time, this shows the uniformity is the correct here. Then the aim was to increase it more stable further. I think then we also treated them in ionic liquid, as in the morning commented about it. That's formaldinium, the fluorinated molecules, ionic liquid as well, like a Teflon. So they repel water, and we did them, and you can see this is the 85. The devices were stable than the previous one. The devices give you higher stability. And this is the JV curve, it's similar almost. This is the IQE, how many photon is converting into electron, and the integrated current should match. So this is the good solar cell, both the integrated from JSC and the EQE should match. You can see the 24, 25 milliampere. But the crystals are more ordered. You can say this is a strain FAPB3, it's a strain relaxed because we have seen that they are able to take more. Bearable, like a shock absorber. They are, by putting ionic liquid, they become more like a shock absorber, and the Auerbach energy further decreases. And then high quality perovskite and structurally perfect. I'll leave you with this picture without saying anything, and you just say this, enjoy the video. The main problem is the moment you put perovskite in water, they dissolve in a second. This is something we are working on now. Your FAPI, our FAPI, alpha FAPI, which we prepare the powder editing method, it took some time, but by adding an additive, we are able to, this is the water. By adding some additive, we can delay, or we are retarding to a longer duration of time the conversion. This is a very preliminary result we are working on. I hope we will be able to make something better out of it, and the device can be also should be more efficient. In the coming months, we will be working on that. Okay, so I run. The chairman has appeared, so I will run. So, okay, the video. Okay, I require 5-10 minutes more, please excuse me. And then the good thing is that, yeah, I will try to be 5. Sorry. The interface is the device, the famous word from the Nobel laureate Herbert Kromer, and I give you a flavor of how we are working on 2D materials. We have also worked on many molecular material as a passivator, but now we're working on 2D materials other than graphene as a band alignment, because by doing so band alignment, we are also minimizing the voltage deficit. The devices are more stable. Perovskite is a highly polar material, highly polar. We need passivators or any type of interfacial modification to make them more stable. So we place a MOS2 layer 2D here. Our voltage deficit was minimized because with the band alignment, you can see here, we were able to match it. And the voltage increased to almost 200 millivolt here. This is a cross-sectional diagram of the devices. And we use PTA as a very thin layer of 30 to 40 nanometers here. But the good thing was there is no dopant used in PTA. So the numbers you will see, maybe they look like a lower, but not is one of the best number because there is no dopant being used here. And this is a sub-electrical parameter why it happens. So built-in potential was higher. That's why the VOC was higher. And the good thing was the device were much more stable than with placement of an interfacial layer of 2D MOS2. Similarly, this was also published a couple of months back. With we learned from one thing, MOS2, so we moved to WS2 here, and we use the WF2 as an interfacial layer. The voltage increases here. The same story in the devices are also more stable, and also became the cover of the journal here. And the good thing was that the built-in potential increases because the band alignment is more better, and the W2D 1T reach 2D WS2 interfacial layer saturate the voltage at very low current, and the attempt to step frequency is low, and the device very well. A follow-up talk is on 2D material will be given by Dr. Peng Huang, so I skip all this. This is another thing we are working with a friend with Dr. Nawaz Tahir on the carbon nitride, another type of 2D material. So we did two type of, he provided us two type of carbon nitride, solvothermal and solid state. You can see the color it changes. They have two different, they have a synthesized both by two different techniques, solvothermal, so their surface areas differ. And then we use them as a P-type material, as a P-type material for our solar cells. They didn't work, so we use nickel oxides, an inorganic whole transport material. Just now you had a very good talk on organic semiconductors. So we use a nickel oxide as a P-type material, and we coated this carbon nitride on top of this one. And this is, you can see here with the carbon nitride, the nickel oxide, I said, carbon nitride, perovskite, PCBM, the inverted configuration we made it. And this is our device with nickel oxides. One of the boost efficiency of nickel oxide, I think is 17%, almost 18.5. Then we moved to both thermal C3 and 4 and C3 and 4 from solvothermal and solid state. We almost reached to 18.25% here. There was no change in the absorption because these guys don't absorb anything. By placing it carbon nitride, the interfacial resistance was lower, and you can see the resistance to recombination is also here. Graph here. We're also collaborating with a good friend in Turkey, Azgul, Professor Azgul, and their team is very good in machine data-driven approach. So this is what we are doing it. We are assembling, we make 400 to 300 devices. We provide them data and we validating our results. We fit them in a different models, the k nearest problem, k nearest neighbor, decision tree, random forest, gain boundaries. And if you will see the black and empty, full and empty circles, you will find that they are correct. They are very coinciding to each other. So this also in the future, it will save time to make a fully fabricated devices. So it will save time and cost to fabricate a fully fabricated devices. I skip this because the chairman is waiting. This is more about if you are learning to want to understanding, we can use some concept of like light management concept.
You still have 2 minutes, huh?
Okay, that's fine. So this is the idea to give the new people that like silicon light management concept is being used. So we can also increase the time capture for the light management, and by doing so, we can increase the wavelength of the light, and the devices can give you higher current, higher voltage. So if you are doing so, you need a change in the refractive index. So we took TiO2 and SiO2 because the refractive index variation is very high. TiO2 is 1.4, silicon is 1.7. And by doing so, I think you said that you will increase the wavelength of the light, and you can increase this the performance of the solar cell. This is being applied for the silicon solar cells. We are also more interested in the understanding, like Professor Dario gave a fantastic talk of the unraveling the fact, quantifying the mechanisms. So we are already collaborating with him, but also with other people with femtosecond ultrafast spectroscopy. And we publish papers here. We also do Kelvin probe force microscopy with our colleague at Max Planck, Jürgen Burt and Rüdiger Berger. So we are cross-section diagram, we cut them, we do Kelvin probe for the voltage deficit. So at the nanoscale level, this is the laser off, you shine the laser, you have a change in the potential. So these pixels, these are nanoscale. So they also, you can see the shine the laser, you have a change in the voltage. And this is what exactly the VOC is when you light a shine. Again, it's my favorite phrase, I think, and now I like it, but emission anywhere is threat to everyone, and we have to find a carbon neutral technology. And just to finish, let you finish, silicon is a very good product. We are very happy with it. We want 100 times more silicon deployment to be a carbon neutral, but we need also more new technology like thin film, and some of them are ready to take off. Perovskite is a blockbuster in terms of efficiency. By doing interfacial engineering, we can minimize the defect strategy, we can enhance the performance, we can make them more stable. Many molecular modulators have been published, and we are also using 2D materials. The future is methyl ammonium and bromide-free perovskite are potentially attractive because there's no phase segregations. In this context, we are working on a pre-synthesized perovskite powder because it reduces defect and performance, improved performance. This also, I have shown you that lowers the Auerbach energy, and Auerbach energy lowering minimize the crystal disordering, and then we have a increase in the voltage. There are some issues like 25 years lifetime with the silicon, price competition, but we are doing research and we are very happy with it. But I hope that the people who are listening here, many young generations and young minds will come with an excellent approach to solve the correct problem. We are more than happy to accept. And with this, I think I like to my funding engagement, European Research Council, European Spanish Ministry of Science and Innovations. And with this, I'd like to stop here. I will be more than happy to take your questions. And sorry for one last piece of information. If you are attending this conference, like Professor Yusuf said to me, you are more than welcome to contribute to our journal, Emergent Material of Campus. Please mention our name there, and we'll be more than happy to handle your scientific papers. Thank you very much.
Fantastic. Thank you very much, Professor Ahmad. It was a wonderful talk, and I think we all particularly appreciated, at least I saw in the comments, the overview that you gave us at the beginning on the place of solar power and where electricity is going. I think it would have been great to have that even as the first opening talk, because it really helps place the importance of the science that we're looking at. Does anybody have any questions? We have one in the question and A, which again from Mr. Louachi Tariq, which I'm not sure if I tried to read and understand the influence of the atomic scale at the level of the components of the atom and the bonds between these components on the performance of PV systems. I think he's asking about the actual structure, the influence of the structure, material structure on the performance.
Yeah, thank you, Mr. Tariq. This is atomic scale is more currently is with computational approach. It's very difficult to go that very near to that one. Computation like DFT or Monte Carlo simulation, that one. But there are some microscopy techniques you can also see, but we have not seen the degraded device under a microscope. But you can see that. But what we learned from our knowledge, like we were very excited with mixed perovskite, it is the most efficient perovskite also, but we know that the phase segregation occurs. And they're not uniform, and just form the high band gap and low band gap domains there. Did I answer your question? Otherwise, you're more than welcome to write to me or rephrase the question, please.
Yeah. And then another question that appeared from Mrs. Fatima Ziarai. If the results that are experimentally done, would it be possible to do the same theoretical studies using ab initio calculations?
Absolutely, absolutely. We always look for both the support and validate. Our approach is to validate our data with or cross-verify with both of them. Ab initio Monte Carlo is MD is absolutely fine. Many people are doing. I know in Morocco also some people are doing. We have been collaborating with them, but not Monte Carlo. So this will be, of course, real helpful because you know where to go, the simulative, the computational guy, and then we try to validate them, but almost is not possible every time. Almost 10 times or 20% times we are successful in validating those results in the labs. But the good thing is that our simulative friend know where to go. Mm-hmm. So this will be absolutely necessary and is a paramount.
And then I also have a question regarding the surface modifiers. We saw in the preceding talk by Dr. Kazim that they can reduce charge carrier recombination. I was wondering if this was due to reducing the surface density of traps or if it was due to surface recrystallization.
Dr. Kazim,
I think it's because of reducing the surface traps, because we do some electrical measurements and we found that there are some traps which can be passivated by these surface modifiers.
Okay, thank you, Dr. Kazim. And your thoughts on this, Professor Ahmad? Yeah. I think you have your microphone muted.
Muted, yeah, sorry for that. Yeah, I think Dr. Kazim talk was a focus on the p-type semiconductors. And as I commented about, perovskite is a light harvesters. It generates electron and hole pairs. While the hole pair are the minority carriers, okay, you need an efficient, another p-type layer to extract the charge efficiently and travel them back to the electrode. So she focused, it was not about passivators. She talked a lot and gave the clues about the molecular semiconductors as a p-type layer. But again, if you want to talk about passivators, I commented in the morning, very good talks and results here. Perovskite is a highly polar. You have also found with very good technique you have developed. PMRS is a highly polar molecule, highly polar, and also the crystal size is very high, is very rough. So passivators is very necessary in order to minimize the defect.
Okay, great.
So now I think is the passivator everybody is using as now a universal approach.
Sure, I think so, yeah. Well, thank you very much once again. So I think without much more ado, we're going to move on to our last speaker of this first afternoon session. We've had quite good discussions, so we're eating into the discussion time. We'll have to probably shorten that if we want to keep the panel discussion afterwards on time. But it's with great pleasure that I will introduce our next speaker. Before that, I will ask Professor Ahmad to please stop sharing his screen. And well, thank you very much. And so our next speaker is Dr. Peng Huang. Dr. Huang received his PhD from the Beijing Institute of Technology, and then has been doing a postdoctoral work in the IRSEC' Institute for Nanomaterials, I believe in the group of Dr. Ahmad and Dr. Kazim. So it's he will be presenting a talk on the 2D transitions in chalcogenide perovskite solar cells. And with that, we're all looking forward to your talk, Dr. Huang. Thank you.
Okay, and thanks for the invitation from this conference. Also, thanks for the introduction by the professor and the Mazen. And I'm Peng Huang, and my presentation title is the 2D team this as interfacial material for the perovskite solar cells. And the most of work I finished is in the Suzhou University, and now I'm in the Marie Curie Finland and in the business material. So I will introduce my work is following the 3 parts. So for the perovskite and the advantage also the development is very fast, and we can see perovskite is the third generation and the forerunner and devices, and the perovskite can improve the efficiency from 3.9 to 25.5% efficiency with the last decade, but the rest three generation solar cells, and the import is very less, and the efficiency is less than 20. And the fast development because of the perovskite structure. Also they have, and because of the structure, they can lead to very nuclear and the semiconductivity properties. And the perovskite structure, and they're made up by the ABX3, and we can change different A set and B set and X set to tune the best and the semiconductive properties. And for the perovskite, first the perovskite with the excellent absorption, and they have very high absorption and coefficient. And for the perovskite, and they just need 100 nanometer can absorb most of the light. But for the silicon solar cells, and the thickness of the active layer should be 100 microliter also, and the band gap can easily tunable, and the white is and the band gap and the tuner range is very high, and we can reach to 1.4. Also we can reach to 2.2, and the high band gap we can use for the thin solar cells, or for the semi-transparent solar cells also. And after perovskite and absorb the light, they will produce an electron and a holes. And the perovskite and they have a very low expansion binding energy. Also they have some like ambipolar carrier transport characterization. They can very easily to separate the photo generated holes and electrons and to transport it to the electron and to produce the current. And also, and for the perovskite, they is very easily to deposit. They can use the very common and the spin coating, very common methods such as the spin coating and the spray coating and the Dr. Bray and the snot dia coating or drop casting can prepare. And for example, and our group use the spin coating and spin coating the perovskite solution on top of the titanium oxide and the heating and with the low temperature, and we can produce the mirror-like perovskite. But the problem for this perovskite, and the problem is about the stability. You can see, and for the perovskite, they is quite sensitive to the moisture, and also for the pure Fa perovskite, they have some like unstable phases also, and the perovskite they have some is sensitive to the UV light. And the perovskite solar cells, and they will use some and the transport layer to transport the electron or holes. But for the p-dot pieces, and they will degrade the perovskites. Some are showing in the figures. And we focus on trying to solve the stability problem from the interface, and the NIP devices and the PNA devices is the most common devices to get the high efficiency devices for the perovskite. And for the NIP devices, and the most common used ATM is the titanium oxide and the tin oxide. Titanium oxide, we can get the highest efficiency also with the low cost. But titanium oxide needs the 500 degree to heating. Also, this material is UV light sensitive. And the tin oxide and also can get the high efficiency, but is also we can use the low temperature to process. But sometimes that will show some hysteresis. And for the PNA devices and the p-dot PSS is the most common and the whole transport material and for the solar cells. And they can use the low temperature to solution. And the process also is very common and the reception. Everyone can use it. But for this material is a little expensive. Also is aesthetic. And also this material can absorb the water and to degrade the devices. So most of people just want to modify or replace the conventional and bottom transport layer with the 2D TMDs. And actually, and for the third generation solar cells, and most of 2D materials such as graphene or 2D TMDs has been applied into the devices, and this 2D material can play as ETM or HTM, also can be as actives for the active layer. Also for the reduce the graphite oxide, they can be used the transparent and the conductive electrode. And for me, I will focus on the 2D TMDs. And what is the 2D TMDs? 2D TMDs is composed of the MX2. M is the transition metal, and X is the sulfide, and the Se and Te. And for this material, and it's very popular material after graphene. And this material also can be used for the energy storage, also for the PV system, also for can be used for the catalyst. For the semiconductor 2D TMDs, we can divide it into N-type and P-type. For the titanium sulfide is MOS2 is the typical N-type and P-type and 2D TMDs. And also this material have with the high mobility and high conductivity, and the most important, they can be used for the solution processability. And how to prepare 2D TMDs, and they have a top-down method or bottom-up method to prepare, because for the perovskite and for the preparation of the perovskite and other process can be used for the solution process. So we can choose the good and the preparation method to prepare and 2D TMD solution. And before I start and this project, only 2 people reported about 2D TMDs as how transporting material or how transporting interface material for the perovskite. And the first one, and they use the CVD method to prepare and the MOS2 and the WS2, and they prepare the devices, and the efficiency is less than 10%. And the second paper is insert MOS2 and between the perovskite and the spiral, and they can improve the stability, but the efficiency will decrease a little. And but for if they just use MOS2 as HTM, and the efficiency is less than 5. So, and we focus on how to prepare high efficiency and the perovskite with the 2D TMDs. I use very simple and affordable method. And for the 2D TMDs and the solution ink, and also we can use very common and the deposit method to prepare. And we use the spin coating and we use the spin coating to prepare the 2D TMD film. Also, we use the spin coating to prepare and the perovskite. And the down part, we just show the process how to make the perovskite. First, we were spin coating the 2D TMD solution. Later, we use the anti-solvent or two-step method to prepare the perovskite. And we're heating. After that, we spin coating and the PCBM as the electron transporting layer, and later we deposit the silver to finish the devices. And we use the lithium interactor method to prepare and the single layer or field layer and MOS2 or WS2. We use XRD and we use FM or we use the TM to measure and to characterization these samples, and we get MOS2 and WS2 is around 400 nanometer. The thickness is 400 nanometer, and after that we use and we check the and we check the structure of wave front after reaction they produce different phase, and we call it is the 2H and the 1T phase, and the ice prepare and the 2D material is 1T rich phases is contain more than 15% of 1T phases, and after heating at 200 degrees, and the 2D phases will change to the 1T phases will change to the 2H phases. We call it is the 2 and the 1T pool phases. First, before making first we check which phases is favorable for the devices, and we use different 2D teams material with different thing with the different phase, and we front and 1T rich material can get the higher efficiency compared to the 1T pool and the devices, and we also use the PL measurement to check it, and it's showing and the 1T rich material and with the higher quenching for the perovskite. So 1T rich TMDs is favorable for the high efficiency perovskite, and later we optimize the devices, and we compare it with the reference and the P.PSS as the reference, and we apply the MOS2 and the WS2 to get the near to and the 14 and 15% efficiency, and the more important and the efficiency will improve a lot, and this device and this efficiency is the highest efficiency used the 2D TMDs as whole transport material. Also, the devices can we use the same and the method to prepare the 2D titanium sulfide, and we also use the measurement to prove we get the field layer titanium sulfide, and this material is the thickness is 4 nanometer. It means 3 layers, and later we introduce the 2D titanium sulfide as electron transporter layer for the devices, and we also use the UVO treatment for the titanium sulfide to optimize the efficiency, and we can optimize the efficiency to near to 19% efficiency, and also the steady output can have 17% efficiency. Also, the devices show the good reproducibility. The most important is for the devices, and the stability will improve a lot. Why the devices use the UVO treatment can improve a lot, and we use XPS or SCM, EDX, and KPFM to check it, and after introduce UVO treatment for this field, and the oxygen can occupy the sulfur defect, and the sulfur defect because of the very and the sulfur defect produced because of the very strong interactor, and we use the XPS to check it, and we can stack that to prove and the oxygen process also, and after introduce and the UVO to treatment, and this thing is the most part is the titanium sulfide. Also use the KPF to shoot, and they can decrease the work function from 1.8 to 1.6, and which can decrease the gap for the conduction band of the perovskite. So that's the reason why can improve the efficiency. And also we compare with the other report and the metal compound ATMs, and because if some transport material and most of the metal oxide transport material should be heating some like the 500 degree or to heating, but it's not good for prepare some flexible solar cells, and we compare to this result. And for the room temperature processed metal compound ATMs, and they have two common methods to prepare. The first one is the spattery, and the second one is the solution processed. And for my result, and we can use the solution processed method to prepare near to 19% efficiency with this steam. Later, and we introduce the 2D TMDs. 2D TMDs, and as the modifier for the titanium for the tin oxide, we use the conductivity and the FM to check it, and the surface and the conductivity will improve a lot. Also, we use the SCLC to check the trapped density and for the mobility. And after introduce the titanium sulfide, and the trap density will decrease and the mobility will increase. Later, we prepare the devices and prepare the devices, and for the reference with the tin oxide, we can get efficiency is less than 20, but after introduce titanium sulfide, and the efficiency can reach to the highest efficiency can reach to near to 20. And also, we can the current, and we can prove by the ECOE results. Also, the devices share to good reproducibility. And also, we can use the different electron measurement and the PO measurement to check and the reason why is the increase the efficiency. And we can use the impedance to see, and after introduce the titanium sulfide, and the recombination resistance will increase. And for the PO measurement, and after introduce this material, and the electron and transporting ability is the increase. Also we use the capacitance and the voltage, and after introduce this material, and the capacitance will decrease. It means after that they will lead to the low hysteresis. And the conclusion, and for this, and we check the history for the 2D material for the as a transport material for the perovskite, and most of the result is the basis on the graphene, or such as graphene and oxide, or reduce the graphene oxide. And the first, and we use the titanium and the MOS2 and the WS2 as a whole transport material to get to near to 15% efficiency. And later we use the 2D titanium sulfide as a whole as the electron transport material to get to near to 19% efficiency. Also, the devices shall improve the stability. And later we use the 2D TMDs as and modify. Also, we compare to we compare the result with the rest reported results, and we use the titanium sulfide, and to modify the tin oxide, we can get to near to 22% efficiency. And also and this result can help us to develop new 2D TMDs and material, and also we can see can 2D TMD is the possible realize and the perovskite and to improve the efficiency and for the modules or some like that. And the third part is the encouragement, and because most of work is co-supervised by the Professor Ido and Professor Yunfang Li. And but according to my experience, and even we can get the highest efficiency, but for this 2D TMDs, and they have shown some problems, such as the thickness sensitive also is very poor forming ability. So after that, I will cooperate with Samrana and Shahzada to continue to optimize the 2D TMDs and for the Perovskite. And thanks for your attention.
Thank you very much, Dr. Huang, for a very interesting and very fascinating talk on these layers. The talk is open for questions and discussions. We have a little bit of time. And in fact, now that I see the schedule, I see that we actually have still 7 minutes to be able to go into the discussions. So I think we can ask questions to any one of our speakers this morning. So please feel free. I don't see anything on the Q&A that appeared. So while people think about their questions, I was wondering, do you have any evidence that there's any tin or the titanium can exchange with the lead, or that the sulfur binds with the lead? Are there any interfacial interactions between the tin and the sulfides with the perovskite material?
And this should be, and for my paper, and the last is the 2D TMDs as a modify, and we also use this one to, and we also use the XPS to check the possible interact with perovskite, and this should be have some is how to say, and the 2D teams, if instead to the and the tin oxide and the perovskite 2D teams is like a glue to interact with the tin oxide and also with the perovskite. And also they have some, because they have lot of paper report is sulfide, this element, they can as a passivator for the defects of the perovskite. So they should be have some work. But for the 2D material as a transporting material, because for this work, and we just started, so we did check the possible interact, but the interact with the perovskite should be possible.
Okay, interesting. Yeah, I think it's fascinating the way that the add layers influence the properties. I think that they actually change the bulk properties as well. We have one question from Mr. and Mrs. Amini Benamur, you and our panelists, how to compare the 2D and the TM and the modified one. So I think you're talking about the perovskite structures. How can we compare the different perovskite structures between them? And this is an open question for all of our panelists, so feel free to join in the discussion.
Sorry, it's because for the 2D TMDs, because it's the 2D and 2D material, also some, how to say, and some like the dimension, and this material is like a paper, so like a normal paper, so it's difficult to covering the subject. So for example, is ITO subject or FTO is not very easy to cover very well. So it's mean if 2D material as a single layer for transporting, maybe is not very uniform. So the efficiency is not high. Also for and about this part, the research is the did report not of a paper. So, but if we combine with the traditional titanium oxide or tin oxide, we can use the advantage of the 2D TMDs to improve the efficiency.
I guess what we would like to have is 2D material that was organized vertically, a little bit like the block copolymers. But it could be interesting if there was some way of using selective deposition to obtain vertically organize the 2D perovskites. That would be like in laminal structure that would be vertically aligned. That would be really ideal. because then we would have
yeah,
conductivity.
sure.
Yeah. All right, thank you. Professor Ahmed, I see that we're approaching the discussion time. Would you like to take back control of your session?
Yeah, thank you.
Perfect.
Thank you.
It was a pleasure to.
Thank you very much for acting as a chair.
To the discussion now.
Yeah, thank you very much for taking the chair and handling effectively on the time. Thank you, Peng, for your great talk. We are open to your questions. Further questions? Any more queries to the speakers? And since 2:30, we have a contributory talk from 2:30.
Okay. We start PhD students' presentations.
Presentations. Okay. So thank you, everyone, all the speakers, I think, and thank you, the chair also. We will move to the next session. And the first speaker is Safia Darisi. And Safia is going to talk about synthesis and characterization of copper, iron, cobalt, tin, sulfate thin film prepared by prepared. Safia?
1 minute, please.
Yeah.
I think Mohammed Yusuf Msous, no? البروغرام في لاباج ديال الوركشوب دوزيام بارتي. ماشي دوكيمون
No, this was it was Safia. Safia Darisi.
The presentation now is Mohammed Yusuf Msous.
Okay, in the program it is Safia Darisi.
You have the old version of the program. See the new version.
Okay.
It's okay.
Okay, whatever you want. Okay.
I have the honor to present to you our work entitled Structural and Optical Property of Cerium and Neodymium dioxide nanopowders prepared by co-precipitation method. Summary of my presentation. I will start with an introduction which briefly explains the problem of solar cell and set one of the solutions to this problem, which is the photon conversion. Then I will describe the synthesis method used to prepare our samples of cerium and neodymium conductor titanium dioxide and the results of some characterization techniques before concluding. The company uses the renewable energy source in solar energy. Photovoltaic or PV system is used to convert solar sunlight energy to electrical energy. The basic component of PV system is known solar cell, but there is a problem. The spectral incoherence due to the emission of sunlight and the absorption of silicon-based solar cells, for example, cause solar energy losses, leading to low photovoltaic efficiency. In other words, low energy photons are not used efficiently, and the majority of high energy photons are dissipated. Recent studies have suggested that doped rare earth ion can contribute to solve this problem. Thanks to this spectral modification characteristic using the process of up and down conversion to cover the unused blue part of solar spectrum, we can use a layer of down converter at the front of the solar cell, and for the red part, we can use an up converter layer at the rear of solar cell. The up conversion is a process in which the sequential absorption of two or more photons leads to the emission of light at shorter wavelength than the excitation wavelength. One of the materials more extensively studied for this purpose have been lanthanide or rare earth system. Due to suitability of their discrete energy levels for photon conversion inside a wide variety of host material. Our work focuses on the case of down conversion process. Our method consists of the introduction of the rare earth couple, cerium and neodymium into the titanium dioxide structure for photonic conversion. After excitation for the cerium synthesizer via ultraviolet light, energy transfer to the neodymium activators occurs and resulted in the emission of the infrared light. For atom oxide, we use titanium dioxide as a precursor to which we add titanium and
ريكلاماسيون اليوتيوب تقول لي راه انت ريكلامي انك عندك لك صورتها
chloride and neodymium nitride. The reactions are produced in basic medium thanks to the addition of sodium hydroxide. The obtained powders are calcined at 450 degrees and characterized by different techniques. For the structural propriety, X-ray diffraction was performed. It confirms the formation of all samples in anatase phase of titanium dioxide. Also, the crystalline size phase were calculated by using both Williamson-Hall and Tobias-Schneider formulas. It showed that they are in nanoscales. The Fourier transform infrared spectroscopy indicates also the presence of the stretching vibration of TEO band. For morphological and elemental analysis were performed by scanning electron microscopy coupled to energy dispersive X-ray spectroscopy. The crystalline size measured were around 65 nanometer. And the band and the doping element are detected. Optical properties were observed by UV visible spectrum photometer by recording the transmittance and the absorption. The calculated band gap by the value of the calculated band gap by Tox formula is shown that is decreased with doping. In conclusion, we can say that prior studies suggest that light absorption inefficiency in solar cell can be addressed using up and down conversion. In this study, we show that we are able to succeed in doping titanium dioxide with rare earth ion as part of down conversion process. For the future study, we must conduct the photoluminescence analysis, then make the satisfied inputting technique, for example. And thank you for your attention.
The next presentation is Abdelkader Al-Kisani, from University of Marrakesh, Morocco. Paper ID 141.
Hello. In this presentation, I will present my work on integrated copper and sulfide in films of solar cells. Preparing that laboratory material of faculty of science media Marrakesh, we show spotlight. Firstly, I will start from a match of work. Secondly, I will present section concept definition of CFTS and CFTS solar cells. After that, I will present the part of research and finally I will end with conclusion. The solar cells of second generation commercialized are based of absorber but those observers suffer some limitations such as the toxicity of cadmium and selenium, non-abundance of antium and gallium, and the high cost of materials.
अच्छा टॉप दिया उसने मतलब नवीन प्रोसेसर नहीं है मतलब अच्छा कोई मटेरियल तो करवा सकते हैं हाँ ऑफ कोर्स
survive object of this work. Firstly, I will present the part of experimental section concerned to synthesis of CFTS in solar cells by soldier speculative technique. The precursors used to prepare the soldier solution were copper chloride, iron chloride, tin chloride, and urea. Solvent is solution of methoxyethanol and deionized water. The solution was stirred on hot plates at 50 degrees C for 20 minutes. The bronze solder solution was formed. After that, pink water was used to deposit the CFTS in film on clean soda glass and on fluoride oxide glass substrate. Then the obtained film was dried in air at 200 degrees C for 20 minutes to remove the residual organic materials. After that, the synthesized film was analyzed at 400 degrees C for 40 minutes in nitrogen atmosphere using tubular measures. Subsequently, the synthesized film were analyzed by X-ray diffraction, Raman spectroscopy, scanning electron microscopy, energy dispersive X-ray spectroscopy, and UV near infrared. Secondly, I will present the part of experimental section concerned preparation of CFTS-based solar cells. The structure of the device is firstly 80 nanometers thick of intrinsic zinc oxide film has been deposited by solder method on the clean fluorine tin oxide substrate. Then 50 nanometers thick of cadmium sulfide in film was deposited by solder method. After that, the copper iron tin sulfide in film was deposited on the top of cadmium sulfide film. Finally, opaque contact of Oreo was deposited on the surface of copper iron tin sulfide in film by water coating. The fabricated solar cell has been characterized by solar simulatory. For resultant distributions, X-ray diffraction analysis confirmed the formation of CFTS tetragonal star in structure according to standard resonance curve. constant and crystal size have been calculated. Lattice constants are in good agreement with the standard value from the reference card. The crystal size is found to be 60 nanometers. Also, Raman spectroscopy compared the formation of stunning self-test films. For morphology and pigmental composition analysis, the surface morphology of prepared self-test film has uniform and compact. The binary dispersive spectroscopy compared the presence of copper, sulfide elements and with stability. Also, the optical characterization has been performed. It's shown from this figure the transmittance is less than 25% in the visible region, and the fundamental observation gauge has been clearly observed at 824 nanometers. In addition, the band gap of the prepared film is about 1.5 electron volts. The analysis of fabricated solar cells showing photovoltaic activity with efficiency of 4.7%, open circuit voltage of 0.8 volts, and the fire factor of 50%. Finally, the conclusions of our work are copper iron sulfide absorbing film was successfully deposited by a partial solvent method without humidation process. The analysis further indicates that the first starting polycrystalline structure has been formed with the uniform and compact surface. The best is by the source showing a high competitive voltage of 0.8 volts and conversion efficiency of 4.7%. Thank you for your attention.
The next presentation, Badr Akharkhash from University Mohammed V in Rabat, Morocco. ID 56.
Hello everyone, and thank you for giving me the opportunity to present this work entitled First Principles DFT Investigation of the Electronic and Optical Properties of Glow-Doped Rutile Titanium Dioxide for application in photovoltaic panels, coatings, and self-cleaning. My name is Badr Akharkhash, a research associate in the Semiconductors Physics and Solar Energy Research Team, directed by the Professor Abdel Fattah Baghdadi. This presentation is structured as follows. First, I will briefly speak about the principles of metal oxide photocatalysts. Then I will move on to DFT simulation details and results, and finally a conclusion. So let's start with the principles. Oxide-based photocatalysts are essentially semiconductors. So when a photon with adequate energy is absorbed by the semiconductor, it generates electron-hole pair with redox power, which decrease in the intensity of the highest charge purity energy level appears just above the valence band maximum, which reduces the band gap of the system. To examine the origin of these electronic structure changes in the chlor-doped titanium dioxide, we have calculated the density of states. As you can see in this figure, we have also calculated the projected density of states in order to explore in more detail these results. These figures clearly reveal that the main contributions to the valence band and conduction band are attributed to the O2p and titanium 3D orbitals. Concerning the gap states rise, we found that it is mainly attributed to the O2p and chlor 3p orbitals. We have also calculated the electron localization function, which is a wave function derived property, allowing us to determine regions where electrons are localized close to atomic centers. These plots clearly show that chlor and oxygen have the highest charge density due to strong bending forces from these atomic nuclei, of course, which this is understandable given their electronegativities. We have also performed Bader charge analysis, and the results qualitatively confirm the cationic oxidation states of the chlor atom substituting for the titanium atoms in titanium dioxide. We now move on to the optical properties and the complex dielectric function. From these figures, we note an overall agreement between all principal features in the dielectric components for both pure and chlor-doped systems, along with a slight decrease in the intensity of the spectra in the doped system. Additional optical properties were also calculated on the basis of the complex dielectric function, namely the absorption coefficient, transmittance, and reflectance. It is clear from these figures that the incorporation of chlor into titanium dioxide lattice at a titanium site induces the increasing of the absorption coefficient in the visible light region, which reflects higher photoresponse for visible light, and as a result, an enhancement of the photocatalytic activity of titanium dioxide. But we found also a significant decrease of the transmittance and an increase of the reflectance in the visible spectral range, which might be detrimental for its application as a self-cleaning transparent surface. In summary, we have performed bulk density calculations on pure and chlor-doped systems. We found an axially octahedron structure in the doped system due to the gentler effects. Found also a rise of occupied gap states attributed to the O2p and chlor 3p orbitals, which reduces the band gap of the system and enhances the photocatalytic activity of the oxide. But we found an increase of the reflectance and an important decrease of the transmittance in the visible compared with pure titanium dioxide. And thank you for your kind attention.
The next presentation is of Mohammed Jamal Smiley from University of Blida, Algeria, ID6.
Hi and welcome to everyone. I am Smiley Mohammed Jamal and I will present our work entitled Comparative Study between a Single Junction and One Intermediate Band Solar Cell. Presentation plan. Introduction, theoretical model of a conventional solar cell, theoretical model of an intermediate band solar cell, simulation and result, and finally conclusion and the perspectives. Introduction. Solar cells constitute an important and promising clean energy technology. The solar conversion efficiency is, however, small. One way to improve it is to insert an intermediate band between valence and conduction bands, making what is called the intermediate band solar cell. We propose in this work comparative study of the efficiency between two solar cells, conventional cell and intermediate band solar cell with one intermediate band using detailed balance model. conventional solar cell model. This is the diagram of a conventional solar cell. And this is a list of our assumptions that we have used in our calculations. The number of charge carriers is equal to the number of incident photons minus the number of emitted photons. The current of the solar cell is given by this equation, where N stands for emitted photon flux, X the concentration factor, Fsun is a geometrical constant, and the mu is a chemical potential. Intermediate band solar cell model. This is the diagram of an intermediate band solar cell. We have inserted intermediate band in our band gap. We have the same list of assumptions like in the previous one, but we add to it that no carrier are extracted from the intermediate band. So the current entering the cell is equal to the current exciting from the cell. G1 equals G2. The current of the cell is given by this equation. And the maximum efficiency is given by this equation. Simulation results. First, the simulation results for a conventional cell. For T equals 300 Kelvin. For different concentration factors, X equals 1, no concentration. Light is not concentrated. X equals 100 and X was 1 over Fsun. This is for the fully concentrated light. This is for T equals 400 and different concentrations of light. Here are the simulation results for an intermediate band solar cell. First, for T equals 300 K, we have relatively a flat efficiency versus energy gap. This is for 400 K. The results are shown here. The efficiency improvement is also summarized in this table. Conclusion and perspectives. In this work, a comparative study between two different solar cell structures is established in terms of efficiency. The obtained results showed that an intermediate band solar cell can largely surpass a conventional cell. Inserting intermediate band will enable us to use a greater range of band gaps, because the efficiency in an intermediate band solar cell does not drop off as quickly as in the case of a conventional cell. Perspectives. As a perspective, we aim to study an intermediate band solar cell with two intermediate bands in order to establish a comparison with the present work. Thank you for your attention.
I think now the time for discussion. The moderator. Professor Sazeda.
Yes.
Okay, for the moderation of the session.
There is no any further questions. And in the note, it's also in the Q&A. Yeah, most of the question asked has been answered. So I think it's if we don't have any further things, we can close the session.
Okay. Do you have a question to authors?
Not at this moment. Yeah, there is a, I didn't, okay, there is a one. I don't know. I still don't understand the difference between a single junction and one IBSC in terms of what exactly. Can you please specify the difference between a single junction and one IBSC? Intermediate band solar cell. What is the difference between single junction and intermediate band solar cell?
The concerned author?
What is the difference between the single junction and intermediate band solar cell?
For which people?
I think the last speaker is the last one, Nasir Said.
He's not there.
Okay. Okay, if we don't have any further queries, I think we can close the session, right?
Okay, thank you very much. Thank you very much, Professor.
Yeah, thank you to all.
Thank you to speakers.
Yeah.
If there are question from the audience before closing this session.
Also, if they are thinking, they can listen to the talk and they can come also tomorrow. Tomorrow, I think Dr. Kazim is chairing the session, and we have very good talks tomorrow on organic solar cells.
Okay.
And perovskite solar cells, and very excellent talks from China and Denmark. So please, they can also ask questions tomorrow. They have an opportunity to take it.
Okay. Thank you very much, and I hope to see you tomorrow for the third part of session 2 of workshop 2.
Yes.
You have, I think, we start the next session of the conference.
It's 12:40. It's 12:45. Yeah, it's 12:25.
Yeah.
No, there are some issues because the first talk is 12:40. So we will see you as 12:30 tomorrow. Okay.
350 at 350.
No, 12:40.
We talk about we have a work tutorial. We have.
Oh, right now. Okay, sorry.
Now, just
okay.
After the break.
Okay, so I will. Okay, so thank you very much. So I will take a leave, and you continue this workshop. Okay. Okay. Thank you very much, Professor Shahzada. Thank you. It's a pleasure. Bye. Hope to see you soon. See you soon. Bye. Bye. Bye.
Hello, Professor Saifur Rahman, how are you doing?
I'm fine, thank you. How are you?
Fine, thank you. Thank you so much for your support and your continued support, actually, for all the initiatives we're developing here as part of the board. Thank you, really.
No, I'm happy to be with you.
Yeah,
so
and also congratulations for your election as the IEEE President-elect for 2022. So we didn't have the chance to, to congratulate you face to face or live. Yeah,
that's true. That's true. I'm glad that it worked out the way it did. So now I can spend more time talking to people like you, not campaigning for the election.
Okay, yeah, thank you. Hi, Professor Vivrani. Hello.
Thank you. Hello, everyone.
How are you?
Hi.
Yeah.
Hi. I'm so happy to see you here again.
Thank you.
Thank you.
It's a little bit cold here. Let me put my, hold on a second.
Okay.
Hi, Professor Hassan.
Hi, thank you. How are you?
Fine.
In Virginia, pretty cold here. Temperature now is 0 degrees centigrade outside.
Wow. Winter already there, I guess. That already started.
Winter is here.
Yeah. Okay.
So Hassan, where are you now, Hassan?
And now I'm in Kurdistan.
Kyrgyzstan. Doing
yes,
what?
yes. West part of Iran.
Oh.
Right now I'm in the University of Kurdistan. Sanandaj. Yeah, the city is Sanandaj.
I gave a talk there a few months ago.
Yeah. I was in Japan at that time.
I know that, right? That's what I'm asking you. Okay. Good. So how is it going so far? Mohammed, the conference started this morning, your time, right?
Actually, it started a couple of days ago with some tutorials, but the official launch was organized this morning. So we had a very interesting speech by the Minister of Energy Transition and Sustainable Development here in Morocco. Probably I'll share with you later on the video just to have an idea about what's happened this morning. We also had your remarks and also the other participants in the panel in the opening ceremony.
Okay, that's very nice.
Okay.
This session is also recorded on YouTube live.
It's broadcasted also on YouTube Live. Yes, that's true. Yeah. So we have already more than 200 participants in this session, by the way. So according to the, probably you can also see the number of participants. But through the YouTube channels, probably we have more because the session is also broadcast on YouTube channel.
That's very nice. I'm happy you're doing this.
Okay. We still have about 6 minutes to go.
Right.
Yeah. And what about the suggestion you made during your opening remark about organizing the IEEE flagship conference here in Africa? That would be a good thing probably to discuss later on, because I know that you've organized one of the editions in China. That's yeah. Okay.
Yeah, this is called in IEEE Sustainable Power Energy Conference, ISPEC.
Yeah.
So we should, because of the global warming, climate change, decarbonization, a lot of issues we as engineers can provide discussion platform for.
Okay. Interesting. We are soliciting you for many talks here in Morocco. Saifur, I guess you have another talk in the IEEE Advanced Humanitarian Technologies taking place within the next, let's say, few days. There is another invitation here.
In India this morning at 6:30 my time.
Wow.
One in Qatar tomorrow morning, Qatar.
Okay. So where are you now? Where are you now? You're in Virginia, you said. You're in Virginia, right?
Virginia, yes.
Virginia, yeah.
Timing is good. You are GMT +1, I'm GMT -5, so 6.
Yeah.
We are friends, same time. What is
you can start by presenting Professor Saf.
Yes, okay. Okay, good. Okay, so let's start. Okay. Well, good morning, good afternoon, good evening, ladies and gentlemen. It's a real pleasure to invite you to this session on smart grid. So we have our first keynote speaker, Professor Saifur Rahman. Professor Saifur Rahman is the founding director of the Advanced Research Institute at Virginia Tech, USA, where he is the Joseph Loring Professor of Electrical and Computer Engineering. He also directs the Center for Energy and the Global Environment. He is a life fellow of the IEEE and an IEEE Millennium winner. By the way, I have also to mention that he is the IEEE President-elect for 2022. He's just been elected to this position. He was the president of the IEEE Power and Energy Society for 2018 and 2019. He was the founding editor-in-chief of the IEEE Electrification magazine and the IEEE Transactions on Sustainable Energy. He has published over 140 journal papers and has made over 400 conference and invited presentations. In 2006, he served on the IEEE Board of Directors as the Vice President for Publications. He is a distinguished lecturer for the IEEE Power and Energy Society and has lectured on renewable energy, energy efficiency, smart grid, energy internet, blockchain, IoT sensor integration, etc. in over 30 countries. He is the founder of BM Controls, LLC, a Virginia, USA-based software company providing building energy management solutions. He served as the chair of the US National Science Foundation Advisory Committee for International Science and Engineering from 2010 to 2013. He has conducted several energy efficiency, blockchain, and sensor integration projects for Duke Energy, Tokyo Electric Power Company, the US National Science Foundation, the US Department of Defense, the US Department of Energy, and the state of Virginia. So without further ado, I leave the floor to Professor Saifur Rahman.
Thank you. Thank you, Mohammed. Let me share my screen. Give me a second.
Yeah.
You have to give me permission to share now.
Yes, I think Yusuf is... Okay, I think now you can share your screen. Yeah.
Okay, I'll try now. Okay, it's coming up.
Okay.
Make it full screen. Give me a second.
Yeah.
Okay, I can see Mohammed, full screen is showing now?
Yes, yes, please go ahead, yeah.
Thank you very much, everybody. Appreciate your attention and good afternoon to my friends in North Africa, Africa, and other parts of the world. So I am speaking on the role of smart grid for integrating renewables into the grid. The big issue now, but variable resource for energy, solar, wind, all of these are creating challenges for us. There's a 9th International Renewable and Sustainable Energy Conference. I have spoken at this conference before some time back. Happy to be back to share what I think is a challenge and how you solve this. Now, when you talk about smart grid, first question comes up, what is a smart grid? What does smart mean? So this is not done. You cannot say, I have built a smart grid. It's never finished. It's always something you can do better. So I say it is a concept with many elements where monitoring and control of transmission, generation, distribution, and end use allow efficient delivery of electricity. Efficient, that means reliable as well. That's the target. Now, when you say the word grid, this is a grid. The word grid means network. If you want to focus on the electric power grid, which this picture shows, it is very smart already. It has a lot of technology, a lot of electronics built in. So we don't need to worry about making this grid smart. What we worry about making the distribution system smart so that we as end use customers can get electricity in an efficient, reliable way. That is the target now. So what are we trying to do? The motivation is we want to make the grid smarter, safer, reliable, and more cost effective using sensors, comm technologies, and distributed computing. So sensing, communication, and distributed computing. Those are the elements. You notice here, I put the word cost effective in red. That means it is not cheap, it is cost effective. Smart grid is very expensive, but it can do more things for you so that the cost is justified. Having said that, for common people, I use this picture to explain the difference between a normal grid and a smart grid. On the left-hand side, normal phone. Objective is to make a phone call. That's it, phone call. Rotary dial, the quality of voice, very good, very high quality voice, better than your iPhone. On the right-hand side, iPhone costs today about $1,200 on the right-hand side. The black phone costs $12, 1, 2. So 12 and 1,200. Why should you spend 100 times more money if you want to make a phone call? Use the old one. If you want to only transfer electricity from power plant to your home, you don't need all this fancy stuff. You don't need it. It's okay. It's going on for 130 years now. Why do you need a smart grid? Because like this phone, it does WhatsApp, it does Facebook, it does camera, it is a clock, it is a timer, it is a place you can do emails. All those are extra stuff, not part of the phone call. Similarly, electric power grid, the fundamental job is power, we know that. But smart grid can do more things for you. Automated meter reading, automated controlling of load, automated disconnect of switches. All that can be done in a smart grid without having to add other features like we have today. So smart grid is a comprehensive tool to do many things related to supply of electricity, pricing of electricity, controlling electricity usage during peak hours. All of that can be done using smart grid. That is why you spend so much money. Now, so what is the beginning and end points of a smart grid? It starts at the power plant, transmission line, distribution line, local commercial buildings, your home, end use appliance. I say the smart grid starts at the generator, ends at the refrigerator, all the way. That means if your power company can scan your demand every 5 seconds, they can tell what you are running in your building. Refrigerator, hair dryer, toaster, oven, light, fan, air conditioner, they can tell. So this is the difference between a normal grid and a smart grid. Now, what are the building blocks of the smart grid? What you have to make the grid smart? On the top is technology. Of course, we have the technology like smart meters, smart switches, they have to be there. These are already available globally, no problem. Second is standards. We have to make sure that technology built by many companies follow same globally accepted standards. Example, many companies build and sell smart meters, many companies all over the world, Europe, Asia, North America, and so on and so forth. If a power company in your case, this is Morocco, wants to buy smart meters, they have a choice of companies from China to Switzerland buy. But they have to make sure some came from China, some came from Swiss companies, some US, some whatever English, they must work together. We have built standards which the manufacturers follow to manufacture their smart equipment. It's done. Next is rates and regulations. I briefly said this before. You want to make your system more efficient. That means you don't have to burn gas or oil for an hour on a 24-hour day to store the peak load. Expensive generation. If somehow by structuring the pricing so that in the peak hours, the cost is very high, they will discourage consumer to use electricity more than normal. That way you don't have to worry about extreme peak load on a very hot summer day or very cold winter day. Those rates and regulations are happening now in many countries, but smart grid makes it possible for the rates regulations to be implemented. What do I mean? Smart grid, in our case, smart meter, can send a signal to the building operator that from 3 p.m. to 6 p.m. hot summer day, price will be double. It can be, all can be automated. The price doubles, the building engineer can pre-program his building so that some lights can be dimmed without affecting the functionality. Some air conditioner temperature can go up by a couple of degrees. Some big fans can be turned off and on, so that the demand is distributed. All that is possible by a smart grid and smart communication working together. That's happening slowly, not as much as I would like. Now, at the end, the bottom is the fundamental consumer awareness and education. If the public, not just engineers, do not know the benefit of cheaper rate during off-peak hours and high price during on-peak hours, then they don't care. So we have to make sure we develop enough educational programs so that common public will know the benefit of smart grid and willing to pay the extra money, I said, to pay the cost of putting the system together, they can benefit down the road. Those are the issues we have to keep in mind as we build this smart grid. Now, how is the grid changing? The top third of the page is the before smart grid, and the bottom half is the after smart grid. The top part is common. We see this power station, step-up transformer, long-distance transmission line, step-down transformer, reduce the voltage down to local level, and your local feeder circuit. This is happening for 137 years now, no problem. What is new, if you follow the lower half of my screen, we have a solar panel, we have a storage battery, we have electric vehicle, we have wind turbines, all the new stuff. Still we have large power stations. These large power stations will stay at least next 25, 30 years. They'll stay, but not new ones may not be built as many as we have built in the past. Point is, this is the changing look of the power network. We have to work with this. That's why we need smart grid to make things work. Now, this is my vision for the future. Smart grid will not happen overnight, will not. It will evolve into something smart over some time period. What do I mean by this? I call it intelligent, interconnected microgrids. I'm showing you here 1, 2, 3, 4 microgrids. They're interconnected and they're intelligent. What do we mean by this? Take a city of Rabat or Casablanca, for example. You have a city, it is a system. The city can be broken up into local neighborhoods. One smart microgrid could be a neighborhood. It may be that neighborhood is the business district, central CBD, central business district. They want to get more reliable power and willing to pay more. So let's focus on that part of the city, not the whole Moroccan power grid at the same time. They can have solar, they can have electric vehicle, but more importantly, you see the top picture, I have a modem in the middle. Modem means we are communicating over the internet among all buildings. This is important. So in a smart grid, power supply and communication technology have to work together. That's one. On the right-hand side, another microgrid, it has a battery storage built in. Fine. The one in the middle is a bigger microgrid, which is connected to wind turbines on the left and conventional power plant on the right using long-distance transmission lines. So that middle microgrid can supply power to a smaller microgrid when the smaller microgrid is not able to serve all the load from local generation. Maybe solar is not as strong. They'll buy power from the bigger microgrid. The one at the bottom, another microgrid has a lot of battery storage for whatever reason. So that would be a evening time supply to the top microgrid, which is mainly solar. This is my vision. This will take time, but it will not happen over time. overnight to get this all done. Point is, for people doing research, you have this issue of small microgrid, a lot of solar. How do you manage it? How much storage do you need? How much demand flexibility you have from the consumers? All have to be done into one place, and you can do some research focusing on that. I can talk more during Q&A if I have time. In summary, we have to merge power flow with information flow to make the smart grid work. This is a picture of power infrastructure, power station, step-up transformer, long-distance transmission line, local distribution, and so on. It's done. On the lower left-hand side, rooftop solar PV, battery storage. In the middle, an industrial complex with cogeneration, meaning they produce steam and also electricity. On the right-hand side could be another data center, maybe. The data center has fuel cell, flywheels. All that is happening today, power system-wise. Now, we have to superimpose this power infrastructure with information infrastructure. This is new. Here you see the red lines pointing up, down, left, and right. That means you must provide two-way communication between the source and the load. So the smart grid allows the homeowner or building owner to send signal to the power company for something they want to do at that point in time. That's the combination. Now, that was the discussion on a smart grid. Let's talk about renewables, the other half of my talk. We have wind, onshore, offshore, rooftop solar, electric vehicle, all that is happening and coming to our industry very soon. We have talked about renewable sources, distributed generation. Wind and solar are free, but they are not there all the time. They're intermittent. Hydro is not intermittent as much, but it is not possible to build hydro anywhere. You can put a rooftop solar anywhere, but not a hydro plant anywhere. Even though resource is free in all these three cases, they're not always usable. Like hydro is not possible downtown, wind is not possible downtown because it's not so windy. Those are the challenges. I'll show you how we meet those challenges going forward. Now, start with wind power. I'll show you the intermittency and variability of wind over time. I'm showing you data from northwestern US, Bonneville Power Administration, real data for 4 seasons. This is wintertime, January, typical load shape, the blue line, dual peak, typically because of the heating load, morning heating and evening heating load, 2 peaks. The red line shows the wind power output, average day in the month of January. See, the wind output is low and early in the morning, slowly picks up by midday, 1 o'clock, 2 o'clock, it is the highest and then begins to drop. Typical day in January. At the same time, the same day in January has a dual peak. Point is here, your peak for wind is about 2 p.m., but the peak for solar power is 7 a.m. and 7 p.m. They don't match. So that's the challenge. That is in winter. Let's look at springtime, April. Same power company, Bonneville Power, and typical day in April. Again, we got dual peak because some heating load still going on in April. Wind power was high in early morning hours, demand was low. When the wind is low in the about 7 p.m., demand is high. Doesn't match. Let's look at summertime, different. Summertime load is very flat, wide peak because of air conditioning load in the US. Most states are like this. There's your blue line, got it. Wind output is red lines. Again, during peak hour, 5 p.m., wind is the lowest. That's the challenge. Finally, fall, autumn. Better in the sense of matching the wind power output and the electrical power demand. Power demand is high again. By October time frame, heating load has come back, so you get dual peak back again. So first peak in the morning happens about 7 o'clock. Wind is pretty good. Wind was high all day from midnight till about 3 p.m. We caught one peak. The second peak happens at 7 p.m. Wind is low. So we got one peak covered, but not both. This is the challenge. You can say you can do storage. You can do storage, yes, but storage is not cheap, pretty expensive. Okay, now another example of short-term variation. That's daily variation. Short-term means this is data from Texas. I see in this picture is a wind farm, 150 megawatt capacity wind farm, many wind turbines there. So at 5 in the morning, the wind output was about 135 megawatts from that wind farm. Fine. In a minute, that dropped to 43 megawatt, 135 to 43. Then it slowly picked up and all that. Point is, if you depend solely on wind turbines, like a field of this type, you'll have serious issue at 6 in the morning because load cannot be served, unless load was very low at the time. That's a possibility. That's one case. Another case, in longer term, this is 10-minute variation, the same wind farm, different day, of course, in Texas. So at 6 o'clock in the morning, the output from wind turbines dropped from 142 about 25 megawatts, 10 minutes. Stays low, then picks up again by 2 hours, picks up. That means you cannot depend solely on the wind power for power supply. Now, that was wind. Let's look at solar. That's my building where I work in Virginia. Rooftop solar, clear sunny day. I'm getting a lot of wind, a lot of solar power from this panel. No problem. I also have in Virginia clear winter days, clear. Look at this, it's clear, sky is blue. Winter, it snowed the night before. Because of snow, even though it's sunny, I get zero output because the panel is covered in snow. That's a challenge, what we do with this. That's variation day. This is my data from this system I just showed you. Small system, 6 kilowatt. So for most of the day on a clear sunny week, I get 80% or more output. Very nice. If I go to another week, which is partly cloudy, I get about 50%. So how you run your building using solar only? Cannot. Fine. Other problem is this. I can have short-term, even though sunny day, some clouds come in and go. So for short time, maybe a minute or two, the supply goes down. You can see way at about midday, it has gone down by 50%. And then it went back up. My point is, this is the smart grid application. I would be able, because of smart building control, to change the building load for short time period to match the supply shortage. When the demand, when the supply is, like you see, about 1800 watt in this case, for a 2-minute time period, I can dim some lights for 2 minutes, or raise the temperature in the air conditioner, or turn a big fan off for 2 minutes. You will notice it. That is the smartness. I'm now able to match the load with variation in supply. That's a smart grid combination, because smart grid can be used to control temperature, ventilation, operation, and so on and so forth. I'll give you an example in a few minutes. This is a day where it's a cloudy day and clouds moving in and out. In this case, you cannot do control enough. You turn the lights off for 10 minutes, not acceptable. So in this case, you need some battery backup to carry through the difficult cloudy day. Now, that's my case. This is Saudi Arabia, King Abdulaziz University of Science and Technology, KAUST in Jeddah. This is a 2 megawatt rooftop solar. This was taken, this picture is new, very nice. But over time, this is what happens. Because of the dust and the moisture, if you do not wash these panels, you lose 30% or more output. So my point is, if you depend on solar, even if it's sunny, but it is not fully available. Those are the smart grid issues we need to talk about. Data from Riyadh, Saudi Arabia. They have a lot of sandstorms, dust storms. Typically in September, clear skies, you get 100 kilowatt system, 100 kilowatt, 80, 95 kilowatt every day, no problem. When the dust comes in July, output is half. So July is hot, it's sunny, but because of dust storms, output is low. So what do? Those are the challenges we have to discuss and give results for managing the system. What they have done in Saudi Arabia, they have found a way to wash these solar panels. To wash, you need electricity and water. That's another challenge. But we have to realize the variability and make sure we can keep doing this using smart grid. Now, coming back to solutions now, we talked about storage battery already. These are 2 megawatt batteries for power company applications. Below that, on the lower left-hand side, I have pumped storage hydro plant. What's a pumped storage hydro plant? During off-peak hours, nights and weekends, you can pump water using these big tubes, 6 tubes you see here in the picture, to upper reservoir. The storage, right? Pump storage. Store the water. When the peak happens during midday, hot summer day, let the water come down. And you get electricity output. Use power, off-peak hour, use a pump to pump the water. Same machine will work as a generator during peak hours to bring the water down from the upper reservoir and run your generators. The cycle time is about 3 to 4 hours. Battery cycle time is second or so, meaning if charging the battery, discharge time comes within a second, it can flip. But pump storage takes 4 hours to flip because all that water was going up has to stop and slowly come back down. Takes time. In between is the compressed air energy storage project. This is an example where you take off-peak power from wind turbine, let's say, use a motor, compress the air, and push it in an underground salt cavern. Salt cavern means it's sealed, there's no leakage. It stays there. During peak hours, you let the compressed air come out and go straight to the turbines of the system and run it. Why that is important? Any gas turbine requires compressed air. How does it work? Before the turbine starts, you turn the motor compressor on to compress the air and hold it. Then when the time comes to run the generator, you fire that compressed air and you get a turbine operation. In our case, we are not using electricity during peak hours to compress the air. Air has been compressed before and it's sitting for us to be used. This is the difference between a normal gas turbine operation and a compressed air gas turbine operation. So, coming to solutions. Now we are playing with demand, right? I said I will dim some lights, change the temperature setting, turn some fans off. So demand response is a customer action to control load to meet a certain target. Again, see, my target was I need to reduce my load so that when the sunshine is off for 2 minutes, I'm not in the dark. So that's the question. Question is, how long can you do that? You can do for 2-3 minutes, not for 2-3 hours. Then you need battery support. Those are the issues we need to talk about. So this is the summary. We get a changing paradigm. Historically, we said demand-driven supply, right? I know the demand next week, next month, next year, next 10 years. Based on those forecasts, I build power stations, I schedule power plants to meet the demand. Let's say going on for 100 years or so, demand-driven supply. Now, the supply is unknown, unsure, intermittent. Sunshine is sunny now. After 10 minutes, we don't know. Because of the supply is now flexible, our demand has to adjust to the changing supply environment. I call it supply-driven demand. That is not possible unless you have a smart way to control your demand for a short period of time and run your storage as needed. All that stuff is built in the smart grid ecosystem where we have all the control sensor built in. This is what I call smart grid ecosystem. The core of the ecosystem is the smart grid, which can send signals to buildings, to offices, to factories to change their load for short time periods to match the variable supply. So this is it. Smart grid ecosystem starts with smart buildings, the yellow circle at the bottom. If you can read on the right-hand side, what is a smart building? Intelligent building. It has intelligent building automation system. What do you mean by intelligent building automation? That means your building automation we have in many buildings today, they're not intelligent, meaning they turn the AC on and off, change the temperature by preset schedules. It's okay. To make them intelligent means they must interact with the supply variability. So when the supply is variable, demand has to be adjusted to meet the supply changing style. If you don't do that, you'll get blackouts. The smart building. University is a campus. University may have many smart buildings and result in a smart campus. City of Casablanca, Morocco has many campuses. I know for sure, I've been there. So if all the smart campuses are in the network, you can build a smart city where you can play with the variability of the sunshine, the wind power, and maybe some storage without creating blackouts, brownouts, and the like. Finally, many smart cities in a country can be interconnected under a smart grid. Now you know the difference. Smart grid has many things: smart building, smart campus, smart city, all that built in. You cannot have a smart grid overnight. All these things have to work. Smart city, smart building, all of that put together will give you the environment for a smart grid. Okay, so that's it. I'm done. If you have any questions, comments, I'm in.
Thank you so much, Professor Saifur Rahman, for the insightful.
So, I am done. Thank you, Mohammed. Anytime I can talk more, or this is it.
Okay. Thank you so much, Saifur. So we have some questions. I can pick some of them from the Q&A box here. So there is Dawda Abur Rahim is asking what is the good protocol or communication protocol for smart grid.
Okay, there are many protocols from the my case. How does the smart meter in my house get controlled by the power company? From my house, the information goes back and forth to a data concentrator using microwave mesh network built by the power company, beginning few kilohertz. From the network controller, which is aggregator, the signal goes to the power substation that is going over GPRS, your cell phone network, mobile phone network. From the power station, substation to the power control goes over the power company's own fiber optic line. So fiber optic, GPRS, and microwave. You can also use LoRa technology, LoRa, longer distance, from your home to the substation. In the building, we use mostly Wi-Fi and some Bluetooth inside the building. Bluetooth, Wi-Fi, microwave, GPRS, fiber optic, internet.
Thank you. If you have any question, please post your questions on Q&A box. So there is another question from Ahmed Hamashi, who said, I'm wondering what are chances of having blackout for smart grid, and most importantly, without big production facilities?
You know, this is exactly the case we are pushing very hard. You have 2 points. One is chance of blackout, and facilities, what would be the result? Because we are now using many distributed facilities, a failure of one big generator would not matter to me. I have 1,000 generators. So I may lose one house, but not the whole city at one point of time. But problem is, we have to make sure all the small things are interconnected so they can help each other out in time of demand. And that's why communication is very important. And that means now for the power company to send power from the power station to my house, we don't care about communication. It's power in a line, the side. Now the line is there, in Virginia, we have this all the time. The storm comes in, wind will drop the distribution line, I lose power for a few hours. If I have some local generation, local storage, I am safer before.
Okay, thank you. Another question from Dauda was asking why there are not hydrogen system in the smart grid system that you presented. So can
yes, I did not talk about hydrogen simply because hydrogen is not available yet. It will take a long time because of two reasons. It's very expensive to make hydrogen, very expensive. If you do from water electrolysis, very expensive. Other problem is the hydrogen it burns by itself. It's not like air, it burns. So you have to be very careful in transporting hydrogen from place one to a place A to place B. So all the infrastructure is not there yet. That is why I did not include hydrogen, but it is a good source of storage. If you have free or low cost electricity at night, make hydrogen and somehow have to ship it to the place you're using. It is at least 10 years away.
Okay, any other question? So probably a few minutes, couple of minutes. Well, okay, otherwise I can also ask a question. Say for, you know, that IEEE Standard Association is working on different standards in the framework of smart grid. How do you think those standards could, you know, contribute to the development of the technology, also accelerate the adoption of the technology worldwide?
IEEE Standard 1547, good example, designed for interconnecting solar panels, storage in the distribution system. That standard is being followed globally right now. That is very useful tool to have. So that's happening. But as the technology changes, there are more storage on the list of options now. They have to modify 1547 to have storage as part of this control algorithm. So that will evolve over time.
Probably we can, since we don't have the next speaker, so probably we can just use his time probably for more questions. If you allow it, of course, Saifur.
No problem. I have one on it. I can see on screen a question. Does rainfall affect energy output of solar panels, even though they can serve as washing? You're right. It does affect solar panel output because solar panel output depends on sun intensity. Rain means cloudy, right? Obviously. Intensity goes down, output goes down. But at the same time, the rainfall will wash the solar panel. If dirty, it would be clean. I showed example on my rooftop solar a few slides back. I built that in 2013, 8 years ago, never washed it, never. Sunshine, rooftop rainfall and snow cleans it for me. Never wash it. Unlike Saudi Arabia, they wash it every month.
Okay, thank you. There's another question in the post there. In case of low wind energy generation and no energy storage system, could the smart grid respond to load demand? As you say, it can control the supply to reach the load.
Well, smart grid has no internal storage, no internal. It's a communication technology, managing things. So in low wind generation and no storage, can the smart grid respond to load demand? It can. I do this work myself, building automation. When no low wind and low solar means supply is limited. What I'll do, in a very smart way, I'll look at my building demand profile. How much from lighting, how much for air conditioning, how much for ventilation fan. I can control them in a very smart way over a few minutes of time span, and you will not feel it. If you came to my lab, I can show you, I can dim the light in my lab to 80%, from 100% to 80%, you cannot tell the difference, If I dim from 100 to 80, 20% dimming, I can save 12% electricity without doing any headache for you. Okay. Similarly, I can raise the temperature in my building by 2 degrees centigrade, you'll feel the difference. By that, I save 10% energy. That's the smartness of smart grid, smart building. I showed you at 4 levels: smart building, smart campus, smart city, smart grid. So yes, answer is yes, can be done, but you have to have computer program, protocols, communication to achieve this end goal.
Okay, there's another question from another participant who said that in terms of concept, why there is confusion between smart metering and smart grid. People tend to reduce smart grid to advanced metering infrastructure. What to do to raise awareness about real concepts?
Well, a smart meter is a one equipment, that's it. Meter measures the energy flow and gives you electric bill. They don't give it. You measure the kilowatt hour consumption, electric bill based on this. That's normal meter. Smart meter has 2 things. One, it can be read remotely by the power company. They don't come to your home to read the number. But equally important, they can control the voltage at your house. They can control the frequency. They can control the supply of power if the price is high or low. That's smart meter. Many people confuse smart meter with smart grid. Smart meter is one small part of the smart grid. Smart grid starts at the smart meter, goes all the way to the power station, communication, power supply, control of voltage, power frequency, power factor, all that is done, can be done using a smart grid infrastructure.
Ori, maybe pick a last question from the audience. So there is one which asks, what are the advantages of smart grids over the approach that involves incorporating the stochastic aspects of renewable energy sources at plant design stage?
Well, smart grid gives you the tool to do what you just said, stochastic aspect of renewable energy. 2 ways. One is, if the renewable energy is changing its intensity, you can bring in enough storage, number 1, and enough load control simultaneously so that the variable supply can be equal to variable load. This is new. Before, load is fixed, a load is here, supply will meet the load. Supply is guaranteed, kind of guaranteed. Now it's not guaranteed. It's just said intermittency. So I'm smartly controlling the intensity of my light, temperature setting, some battery storage to match that supply variability with the demand flexibility.
Okay, thank you so much, Saifur, for the insightful talk and for answering most of the questions asked by the audience. There are some attendees asking to have your email address, so probably I take for your permission first to share your email address for future. Yeah, so that we will share the presentation. Also, probably can we share your presentation later on?
Yes, no problem. No problem.
So we'll share the Professor Saifur's presentation and also email address. Once again, thank you so much, Saifur, and keep in touch. Take care.
Thank you. Will do. Well, take care. Nice. Enjoyed the talk. Thank you very much.
Okay. Thank you.
Bye-bye. Bye-bye. Take care.
So let's move now to the next speaker. So we have with us Professor Hassan Bivrani. I'm not sure if I'm pronouncing correctly your name, Professor Hassan.
Yeah, exactly.
Hassan Bivrani received a PhD degree in electrical engineering from Osaka University, Japan in 2004. He is a full professor at the program and the program leader of Micro Smart Grids Research Center at the University of Kurdistan, Iran. Over the years, he has worked with Osaka University, Kumamoto University, Japan, Queensland University of Technology, Australia, Kyushu Institute of Technology in Japan, Central Lille, France, and Technical University of Berlin, Germany. Currently, he is a visiting professor at the Osaka University and experienced research fellow of AVH Foundation. He is the author of six international books, 15 book chapters, and more than 300 journal conference papers. He's been the guest editor of 4 volumes of Elsevier Energy Procedia and Energy Reports journals. His current research interests include smart grid operation, and control, power system stability, microgrid dynamics and control, and intelligent, robust control applications in power electric industry. So without further ado, I leave the floor to Professor Bevorani.
Thank you very much, Mohammed, for your nice introduction. And hello, everyone. And I would like also to thank Saif for his nice starting presentation. I would like to express everyone warm greeting from Kurdistan, University of Kurdistan. Let me to share my presentation file.
Okay.
So now I hope you can see the slides.
Yes.
Today I would like to talk about the virtual dynamic shaping in renewable integrated power grid. It means how we can shape the dynamics of a power grid in the presence of renewable integrated renewable energy sources and distributed generators. So for this purpose, we are focusing on a key elements, that is grid connected converters. At the beginning, I would like to have an introduction on a modern power grid or smart grid, and then I will focus on a grid connected converter and its capability to have a flexible grid dynamic shaping in a power system or power grid. Then I will show you some results of an experimental study with other partners in this research work. And finally, I will give you some applications that recently we have done. By the way, Saif make it easy for me to compare a smart grid or a modern power grid with a conventional power grid. So I will skip and just talk some sentences, some short sentences about this issue. As Saif mentioned, in a conventional power grid, we have one direction power flow from the power station that they are mostly a bulk power station and thermal type in one side to a demand side in another side. So, and between them, we have transmission companies, transmission lines and distribution companies. But today, we are in face of a new power grid structure, which is completely different in both sides, demand side and the generation side. Today's, in a modern power grid, we cannot see a clear border between generation and demand. And not only for data, we have the bidirectional way, but also for generation, we have the same structure. And in addition, we have a more complex system because of a high diversity in both generation and demand side. Fortunately, due to advances in computation and control and electronics, we can monitor and we have access to all points of a smart grid. So that's a big difference. Surely, this kind of system makes new characteristics and challenge as well. Some of characteristics are mentioned here. So the size and diversity, as I mentioned, is increased. So the system is more complex than the past. And we have a high rate of uncertainty in this system due to integration of more energy sources and demand options and more functionality in the system. And furthermore, we have intermittent or variable power, mostly produced by the renewable energy sources. So it makes some problems for stability and keeping the performance in a power grid. And furthermore, the total inertia and damping property in the system is going to decrease because of replacing bulk power plants by the distributed generators using the interfaced power electronic system, such as grid connected converter. So it's also make a stability challenge in our system. So today, I would like to discuss how we can respond to this challenge, the last one, specifically the last one, by the grid connected converters. Grid connected converters, I mentioned that makes some challenge because it makes the distance between the rotating mass in some small digits like the wind turbine and the grid, but in another way, they make some new possibilities for improving the system dynamics. How we can do it? Before talking about it, let me to say that time scales of the stability phenomenon and the control also is changed. At the past, just we have a time scale from milliseconds to seconds and minutes, but nowadays it's extended to take a wider time scale to microseconds and less by having high-speed switching converters in the system. So from thermodynamic phenomena to wave phenomena, it is a wide range of time scale, and it gives some new possibility in the control point of view. And furthermore, in a stability perspective, also we have a revolution. In addition to angle, frequency, and voltage stability, as well as resonance stability, mostly due to electromagnetic phenomena. So in the previous power system structure, these stability issues mostly are influenced by the power system, by the bulk power generators. But nowadays, also some of these stabilities are associated with the converter that they are integrated in the power grid. So let me to focus on the grid connected converter. Everyone knows that using a grid connected converter, we can be able to transfer a power from a primary source like solar power, like solar energy, like wind, like other energy, like water, and so on, and change it to an appropriate shape of power, active and reactive power, and connected to the grid. So this grid-connected converters needs a control system. And today, I am going to talk about this control system and its capability and possibility for shaping the dynamic of a grid to have a more flexible, smart grid in future. Totally, we have two types of grid-connected converter, a grid following and grid forming. In a grid following converter, the most important things for us is transferring the maximum power from the primary source to the grid for supply the load, local load or grid loads. So in this case, we don't have enough flexibility in control. Just we have two active and reactive power references for setting this system at the maximum power point tracking mode, as you can see here. But in this is an example for grid following converter. And as you can see here, we have a reference for reactive and active power. And these converters try to transfer the power appropriately to a power grid to supply the connected load or grid. So the control structure is simple, and we cannot do so much by using this structure. But in a grid-forming converter, the situation is different in control point of view. In addition to reference generator, to generating references for active and reactive power, we could be able also to control the voltage and frequency at the output of converter. And in addition, we will be able to create new dynamics and to emulate some desirable dynamics. So we can be able to shape the injected power, both active power and reactive power, from the primary source to the grid. So this kind of grid-connected converters not only can be used for supply the load, but also can be used for control purpose, for performance supporting, for regulating of voltage and frequency, for improving power quality, and many, many other requirements to have a more efficient, smart grid in the future. Here you can see an example for grid-forming converter. So you can see that the voltage references are produced by an oscillator based on a dynamic, a desirable dynamic considered for the voltage and reactive power. And in addition, we can be able to also follow some desirable dynamics for the frequency and active power as well. So that's why, in addition to active and reactive power reference, here we can be also to use different references for voltage and frequency or other requirement in the, at the output of this grid-connected converter. Here, I would like to tell you that in a general view, we could be able to affect the dynamics of the connected grid in two main perspectives: reactive power and voltage, as well as active power and frequency, QV and P omega or PF. So it's depend to us, and it's depend to our objective. Which one is more important for us? We can focus on it. For example, if our target is regulating the frequency or improving the inertia or developing a new structure for PF droop, so in this case, we should focus on this block and try to design a structure, a control structure for this block. Otherwise, for reactive power and voltage or other relevant issues, we should focus in this one. So we have two perspectives. Let me to talk about these two perspectives in more detail. For example, this is the voltage and reactive power perspective. As you can see here, the more important control box here in the control systems of a grid-connected converter is this box. In this box, we can be able to emulate and to create virtually any desirable dynamics that we need it to have a more efficient and a more flexible system, or to improve the performance in addition to the stability of system in voltage and reactive power point of view. Of course, in addition to that, we can also follow some basic control loops like PF droop for frequency and active power. So how we can be able to realize this main block? We have different strategies. And actually, I would like to say that we are free to create our desirable structure and our desirable mechanism, control mechanism. But there are two important structures for realizing this QV block nowadays in industry. The first one is voltage current based control structure, that we can realize it using this simple structure by having voltage controller, current controller. In addition to that, we can also build virtual impedance generator And maybe also for designing the control system, we need some frame transformation at the beginning and at the output. So this is one common way to realize this QE block. Another way is Q-based control scheme. In this case, we mainly focus to provide a Q reference, a desirable Q reference using this block. But in addition, also here we can have other necessary blocks like virtual impedance and QE droop that is necessary as well. So what about a second perspective, frequency and active power? This is one structure, one common structure that here, in addition to P droop, PF droop, we also can be able to emulate virtual inertia, to emulate damping property, and other requirements. Here, to improve the system performance, also we used an output impedance simulator by a virtual impedance loop. And also here we can be able to use voltage estimator, that in practice we need to use an estimator for voltage at the output of grid connected converter. So how we can realize the main block, this P droop inertia and damping block? How? This is one simple method, that by this block diagram and by realizing this block diagram, we can be able to have a simple droop, to have a damping characteristic, and to provide a visual inertia. So this is an example. Everyone can use another strategy and another mechanism. Based on that, what's more important for us in performance and stability point of view? And what characteristic is more important in the system or in our study system, our case study? So I would like to summarize this part. So by a grid connected converter, we can be able to shape the output injected active and reactive power in two different perspectives. The frequency and active power. As you can see, for example, we can be able to even emulate some well-known frequency and active power control systems in the conventional power grids, like load frequency control, secondary control, like PF droop, like swing equation. That's a very basic equation for showing the dynamics of frequency and active power and rate of change of frequency. And in addition, we can be able to use even the governor model, the conventional governor model, to be benefited by the some properties, some good properties of the bulk generators in a microgrid or in a small smart grid. In addition, we can be able to manage other function based on our desirable dynamics, based on our needs. Okay, and for this case, usually just we need to get some feedback from the frequency, change of frequency, and the active power. In other way, we can be able also to do the same things for voltage and reactive power. We can be able to emulate the function of automatic voltage regulation as we have it in conventional power system, or automatic reactive power controller, or QE droop, and any other desirable dynamics, voltage and Q dynamics. So let me to say that we can be able to evaluate the impacts of grid connected converters on the system dynamics easily. For example, this is the frequency response model of a conventional power system. This is governor dynamics. We usually use a simple order, first order dynamics for that, with a droop characteristic, as well as the turbine model. And at the other side, we have also the dynamics of rotating mass and the load by showing two parameters, damping characteristics and inertia, amount of inertia. So this is a well-known control structure for analyzing the frequency response of a system and for designing the control, the frequency controller, like the secondary frequency control or load frequency control. So how we could be able to study this conventional block diagram in the presence of grid-connected converter? It's easy. We can be able to consider the dynamic of a grid-connected converter by a first order transfer function for the inverter or converter and the gain for the droop. And then we can be able to find or to translate this dynamic to the sign dynamics as a conventional generator. So here we can be able to calculate damping property and inertia and droop characteristics that they can be emulated by a grid-connected converter. So now we just need to combine these two block diagrams together, and using this combined block diagram, we can be able to evaluate the impacts of grid-connected converter on the frequency and active power of a power system, of renewable integrated power system. Okay, and we recently have done this issue in our laboratories. So let me to show you some examples. This is a grid-connected converter with a control system in the frequency and active power perspective to provide and to improve this perspective. So by having a virtual inertia emulator here, and also using copying the dynamics of a governor, as well as virtual impedance controller. So this is this structure is known as a virtual synchron generators nowadays. But anyway, it's a control system for a grid-connected converter. We have done some experiment to show the impacts of this system on a connected grid, like a microgrid. So for this, in our laboratory, we try to build a setup, an experimental setup that you can see in this figure. It makes by 2 DGs, 5 kVA and 2.5 kVA here, and it's connected to the grid, and also it has a local load. So let me to show how we can be able to shape some dynamics of the connected grid. Here is a microgrid by these DGs, by these DGs that they are equipped with the grid connected converters with these structure for control system. First, let me to show the impacts of this virtual impedance control loop. So we can be able to build the virtual impedance in different way. Here in our experimental study, we try to emulate the virtual impedance finally in terms of two parts. First is a fixed part or constant part by this inductance property, and then a transient part by delta R and delta L. So it's easy to show that constant part is effective on the damping, improving the damping and transient power sharing in the microgrid, in this microgrid as a small grid. And transient part also shape the overcurrent of the system, overcurrent at the output of converters. So let me to show some experimental results. For example, here we try to change the load, to increase the load in a step 4, and you can see the output active power and reactive power, as well as the frequency and voltage at the output of 2 DGs that they are connected to the system. And here, in this time, in 3 seconds, we also changed the active power reference of generator 2. And you can see that by the constant part, we could be able to improve the damping. If you compare the second shape with this first one, you can see that oscillation is damped effectively, and also the power sharing is improved. And the red locus or Lucy graph also show the same result to us, because by increasing the impedance at the output of grid connected converter, we can be able to decrease the imaginary part of the eigenvalues. So it gives the same results for damping and transient load sharing between 2 DGs. And also for transient part, we can see that the output current to be limited effectively. And that's another shaping the dynamic of system of the grid connected converter by creating some new dynamics virtually. Here is the impedance, the virtual impedance at the system. And more, we can be able to also do the same, improve the quality of system by the Q group, as well as as well as the voltage estimator. We could be able to improve the reactive power sharing, because they are mostly influenced by these 2 blocks. So here you can see that without estimator and with estimator, we have different response. And by voltage estimator, we can be able to get quite better results. And also we can be able to access more oscillation damping by using virtual and governor model, by emulating these 2 parts, virtual inertia and governor model, as you can see in this block diagram. And by having this, we can be able to more smooth active and reactive power in the system. Actually here, of course, active power and frequency is our target. So you can see that the result is desirable in oscillation damping point of view. So recently, in the last few years, we have done some applications and some new research on this area with our Japanese partner in 3 universities, 3 different universities: Osaka University, Nagoya University, and recently Dosha University. And let me to show you just some application, each one in 1 slide. This is one application. I will try to conclude my speech in next few minutes, if it's possible. So here we have done a study on the dynamic impact evaluation in a big power system by the grid connected converters. So reference is given here, and you can get the results and more information about this study. We try to replace one of big generators by the distributed generators, by grid connected converters, grid following and grid forming. And using grid forming, you can see that the frequency response and active power response is quite improved. As well, we used the grid connected converter with creating virtual dynamics for enhancing the gas engine generator. And also by this technique, we could be able to get some desirable responses in the system. And maybe more interesting, we try to use the industrial fan, the load, the motor drive connected to this fan for supporting the frequency of a grid by properly and usefully driving the grid connected converter in the system by creating new virtual dynamics and merging it to the control system of overall system actually. And here in this application, we try to use intelligent technique to create virtual inertia in the system. So it's also another work. And also for big power system, we try to improve the energy storage system connected with under controlled grid connected converter for improving the frequency response and active power control in the system. And finally, we try to use the robust control technique for robust tuning of damping parameter in the control system of a grid connected converter. That it's the topic of a paper that just, it will be presented in a 5-minute short video in the next section. So let me to conclude my talk here. We hopefully can be able to any desirable dynamics by our smart inverter by implementing it in the control structure, in the control system of this inverter, and we can be able to shape active and reactive power injected to the system. You can find more details of all topics that discussed today in this new book, Grid Connected Converter, that will be published maybe in next month or next 2 or 3 months. So thank you very much for your attention. And I will be so happy to answer your question on this perspective. Thank you.
Thank you so much, Professor Hassan Varani, for this insightful talk. Probably we can pick a few questions from the audience. So start with one from Dauda Abdurrahim Moon, who asked, in the overall control scheme, you see that the control does not control the harmonic power. Which explanation can you give about that?
Yeah, thank you very much. It's I think it's a great question. I mentioned in one sentence that we can be able also to improve the power quality by using the control system of grid connected converters in grid forming structure. So, and we have done also some works and have published some papers recently. And in this book also, you can find a chapter about how we can be able to decrease the THD, the harmonics in the system. It's also, yes, it's possible by using that. So it's not just for improving the stability or improving the damping and so on. I think you can do anything. It's a very flexible structure. So as I mentioned in my conclusion slide, you can be able to shape it for your purpose as you want to do it. So, you know, because what's the reason? Because in usually active filters, in grid connected converters, how we can control the harmonics, how we can improve the power quality in a microgrids. The best way is through the control system that we are using in the for the inverter, for controlling the output of inverter, in addition to the normal ways or conventional ways by the active filters in the past few decades. So yes, my answer is positive, and we can be able to also control the harmonics and improve the power quality of the system.
Okay, Well, the audience can ask questions in the Q&A box. If you can have any question, please just post it in the Q&A box. Probably I can ask question if you allow me to do that, Professor Verwan. Yeah, well, you know that AI-based algorithms recently are, revolutionizing all kinds of disciplines. How do you see the impact of such, algorithms? Well, like deep learning or machine learning-based algorithms in the field of your research.
Yeah, thank you very much. It's also is a good question. Yes, as I mentioned, we can be able to follow any dynamics. So if you know that what dynamics we need to use, or if you know that what aspect we would like to improve in a power grid, so at that time we can be able to make an appropriate scheme. So for realizing this scheme, we can use intelligent techniques. We can use machine learning, or we can use other, for example, algorithms like GA, like neural network or fuzzy system, as you can see in one of application at the end of my presentation. So it's, I think in future, we can be able to see more application of machine learning in the control system of grid connected converters to shape the grid, the dynamics of our grid.
Okay. Any other question? Let me check just the box here. Okay. Probably I can also ask another question. Are you aware about any IEEE standards group developing any standard for the kind of problems you have mentioned or covered in your presentation? And
Yes,
what would be? Sorry.
Yeah, of course. I can understand. Yes, the first chapter of these grid connected converters is talking about the grid codes and relevant standard. It's very, very important, as Safa also mentioned about it, because we are going to add some new digits to the already existing power grid. So we need to follow some standards, and we need to match these elements together. So that's why in industrial point of view, we have to follow the existing grid codes and standards in different areas. For example, in communication areas, in microgrid areas, and in power electronic areas, as well as in power quality point of view. Yes, there are some standards now in all this area, and we have to follow them and consider them for designing our grid connected converter and its control system as well.
Okay. I don't know if there are any questions from the audience. Okay, probably I can continue with the last question from my side. We hear, I don't know if you had the chance to listen to the Minister of Energy Transition this morning in the opening ceremony. And well, we have several strategies related to renewable energies, and also some of them also addressing some of the applications that are related to smart grid. And what is the situation in Iran or Kurdistan? Because it's very important to know also what's happening in other parts of the world, learn from other experiences elsewhere.
Thank you for your question. Yes, this morning, yes, I had chance to listen her speech. It was a fantastic speech, and it was, of course, she showed the guidelines for smart grid and renewable energy. Maybe it's a general guideline for anywhere, not just for your country and Morocco. Anyway, in my country, the situation is a little bit different because you know that everybody know that we have a lot of oil and underground sources. So still it's cheap enough. So that's why still there is no big interest, national interest to replace the conventional power generators with renewable energy sources and with clean energy. But it's of course a target for for next 2 decades. Yeah, and assigned by our government, try to use and increase the using of renewable energy sources. But still, this is not a very serious problem for us.
Okay, thank you so much, Professor Birani, for once again for all the thoughts you shared with us in the amazing presentation and framework of the keynote talk. So now probably we can move to the other, I would say, the session of the following session, which is I think I would just go back to the program. So we have 4 talks scheduled in this session. Actually, they are 5-minute presentations from mainly PhD students. The first one is on robust optimal damping control design for grid forming converters. Will be presented again by Professor Hassan Birani, GRU, and Taji Katul. The next one is blockchain-based solar energy trading, which is presented by one of the authors in the list here, Ajinkya Brahmakar. Sorry for pronunciation, sorry. Sanket Patil, Patmesh Kulkarni, Melbov Parod, and Joshi. We have also the following presentation on technical considerations for legacy SCADA system, RTU replacement with an advanced gateway. We have the list of authors: Ammar Alidan, Muhammad Mir, Abdullah Sheikh, Luay Kudehi. And the last presentation in this first session of 5-minute presentation will be covering optimized energy management strategy for off-grid energy system. We have also a list of speakers: Muhammad Barara, Tariq Anijaydi, Sami Labte, Muhammad Uliagdi, Darvish Sharif Al-Alawi. Probably we can just start with the first video. I guess that we have here video recordings of 5 minutes of all the presentations for the ask.
Hello everyone. I am Hassan Birani from University of Kurdistan. I'm going to talk about our recent research work on robust optimal damping control design for grid forming converters. In this brief video, I will talk about grid forming converter design methodology and some experimental results. And finally, I will conclude my speech. Now, the power grid is in transition from the conventional topology to a new topology that we call it as a modern power grid. In a modern power grid, we have a bi-directional communication and transfer of power between generation and load. And we have numerous distributed generator and renewable energy sources with new type of loads like electric car. Moreover, we have distributed sensors in the system like phase and measurement unit, so we can be able to control and monitor this system fully. This new structure provides new characteristic and challenge. One of these challenges is reducing the inertia and damping. And today I will focus on damping using the grid connected converters that most of DG use these system as an interface with the primary source and the grid. This grid connected converters need to be controlled by a control system. And generally we have 2 types of grid connected converters: grid following and grid forming. Grid following converters are set at the maximum power point tracking, and they are working as current source converters, while grid forming converters are working on voltage source converters, and we can be able to control these converters flexibly, in a flexible way, and provide references not only for active and reactive power, but also for frequency and voltage and other characteristics. Here you can see a grid connected converter, and you can see the control system of grid forming converter. As you can see, we can be able to emulate dynamic characteristics through the control system. And this is an advantage of this converter. So not only we can be able to emulate the frequency and active power response, but also we can be able to emulate the reactive and voltage response characteristic as well. So here we are focused on the first perspective, active power and frequency response, by realizing a pitch loop inertia and damping. One way for realizing these characteristics are using swing equation that are in using conventional synchronous generator. And in our research, we try to use H-infinity control for tuning inertia and damping in an optimal and robust way. So in our design, we try to transfer robust damping control problem to an H-infinity static output feedback control problem for finding these two gains. And we built an experimental setup for this case study that you can see in the slide. And by changing the set point and the reference of power, active power of the generator, we can be able to damp the oscillation in the frequency and active power response. Thank you for being with me. Thank you so much.
Professor Saidi?
If you can just proceed with the next talk, because we have recordings, so you can proceed with all the 4 talks, if you can do that. And after that, we'll have discussions.
Good morning, everyone. I would thank you for giving us the opportunity to present our work titled Blockchain-Based Solar Energy Trading. Throughout this presentation, I will be following this outline, starting with introduction, which will cover the purpose and overview of our work. Then I would be briefing one by one the key terms related to our work: energy internet, blockchain, smart grid, implementation approach, the requirement analysis, and then finishing with the conclusion. Depletion of non-renewable energy resources is having an adverse effect on the planet. Therefore, various governments have begun enforcing use of renewable energy to meet the rising electricity demands. Due to environmental and resiliency benefits, distributed energy resources are a potential solution for meeting future electricity demand. The survey provides a concise review of smart grid, blockchain architecture, and their role in distributed energy trading. Solar energy has been the primary focus as the renewable energy resource for implementation purposes. Energy internet is a combination of electric power and internet technology, where energy flows from suppliers to customers like data packets do in the internet. The energy internet proves beneficial in terms of development of a new business model because of the flexibility introduced in power exchanges and lower energy cost, improved system reliability due to balancing of variable loads, increased energy efficiency and optimized energy management system due to reduction of power loss, faster information and communication, planning, and energy telemetry technologies. Blockchain is basically a distributed ledger which spans over a blockchain network. The more number of participants in this network, the blockchain network becomes more secure. Since the blockchain has a distributed structure and numerous levels of verification, the participation trust among the participants increases. Few examples of blockchain are Ethereum, Fabric, Corda, and Quorum. Smart grids are a network of producers and the consumers. Producers are the distributed sources of renewable power, whereas the consumers are the ones who would use the power from the smart grid. Producers add energy to the network by selling it in the market, whereas the consumers access it from the network by using it after buying from the virtual medium. Here is the comparison of traditional methods and the smart grid. In traditional models, we have a centralized structure. In smart grids, we have a decentralized structure, including the large-scale power plants as well as the small-sized power generators. Power source for the traditional models are mostly hydrocarbons. In smart grids, we fulfill our energy demand from the renewable energy. In traditional models, consumers buy power from energy companies, which is a one-directional transaction. In smart grid, it can be a multi-direction transaction, that is, among the providers and the consumers. In traditional models, the pricing is governed by the government or the power companies. In smart grids, every generator can set their price. The billing method in the traditional model is postpaid. In smart grids, we have a prepaid method. This is the representation of power monitoring in the smart grid. Smart meters help monitor transfer of electricity in the main grid. The availability of power in the energy markets can be monitored with this apparatus, which further affects the pricing mechanism. This is the overall representation of the smart grid. It includes the physical layer and the virtual layer. The networking and the structure of the grid connection can be done as per the uses and requirements. Grid connection and network comprise the physical aspects of the grid. Virtual layer contains the pricing mechanism and the interfaces. Energy markets need to moderate the trading process with localizing methods like the non-cooperative game theory models or the ECO trading algorithm. There are constraints to monitor sufficient supply of energy to balance the demand and supply in the market. The implementation approach comprises of the physical layer where the actual energy trade happens, the blockchain which secures the transaction, and the marketplace where the pricing mechanism works. These are the required components for implementing an energy trade setup. Survey about blockchain and how it can aid carry out transactions in the smart grid, enhancing the energy internet, has been carried out. Several smart grid structures and the respective constraints to be taken into consideration while implementing have been studied as well. Thank you.
Next presentation, please. Okay.
Good day. My name is Ammar Al-Aithan. I'm from Saudi Aramco, working under Power System Organization. I'm delighted to present to you in this conference an experience we went through and technical evaluation of RT replacement that we needed to do in Saudi Aramco for older power substations. Power substations are a critical infrastructure for the industrial facilities in Saudi Aramco and to all other industrial facilities. The condition of these substations and its components are periodically assessed to ensure reliability. Those RTU was deemed to be necessary to replace. Those equipment serve an important function of monitoring and control of the substation. The SCADA RTU is a very old system, or very old installation with old technology and limited functionalities and capabilities and already outdated. The replacement was driven by obsolescence management and the new industry trend to digitalize the power system network. To proceed with the replacement of the equipment, 7 technical aspects of the evaluation were done and addressed. First, compatibility, expandability, and scalability. The new system has to be matching to the changes expected or intended in the substation in the foreseeable future. The new equipment shall have seamless integration with the old infrastructure as well. Second item is control segregation. The new system shall provide the right segregation to allow local operations away from the arc flash danger zone and provide various level of segregation to satisfy facilities operation policies. In addition, the system shall be capable to limit the operation to only one source, to one control source or a master, to avoid any wrong operation, and shall provide required operational interlock that are normally used in power substation. The third item is system redundancy, which goes without saying. Both hardware and communication redundancy is a reliability requirement that should be provided by the new equipment or the new replacement system. Fourth item is time synchronization, which needs to be carefully selected to ensure compatibility with the other systems to interface with. Protocols such as PTP, IREC-B, NTP shall suit the end devices in the substation and shall interface seamlessly with the master station. The fifth item is cybersecurity. A real-time operating system is an optimal here, such as Linux, to avoid the frequent update required in substations. The new equipment shall also have a user authentication or preferably using the LDAP for communicating communication going outside the substation. VPN using LDAP, VPN and firewall are ideal choices. The sixth item is programmability. This is usually overlooked. The operation of the substation mandates lots of interlocked automated schemes such as auto-reclosing, lots of alarms and alarm grouping. These are based on specific conditions and calculations of various parameters in the substation. The last one is HMI, or human machine interface. It's a feature that facilitates many other functions in the control and monitoring and provide holistic as well as detailed view of the substation. This should be configured to consider operation policies in the facilities with different authority levels. After conducting the evaluation, considering the described aspect, advanced substation gateway devices were chosen as a replacement to the SCADA RTU to provide all the required functionalities with optimized design, meeting all the requirement. Replacement was seamless and integration with all existing systems was smooth. Additionally, the gateway provides the real-time data covering the field, which is a crucial digitalization enabler. With this, I conclude and thank you.
The next presentation.
Okay, the last one. Yeah. Can you go to the last one, please?
Good morning, ladies and gentlemen. My name is Sami Labtai. I am PhD student of the University of Picardie Jules Verne. Today, I will present to you my work entitled Optimized Energy Management Strategy for an Off-Grid Energy System. The outline is divided into 6 main parts. The main objective of our strategy is to optimize the operation of the renewable energy system and reduce any power deficit. The loads connected to our system are divided into 3 main types. The first one are the important ones, the second one are less important, and the third one will be used in case of any energy excess. In this figure, I present to you the renewable energy system. It is composed of two main energy sources, the PV panels and the battery, an inverter with the load management unit, and three types of loads. The most important ones are the refrigerator and the lamps. The less important are the fan and the TV, and a water pump will be used in case of energy excess. Our main objectives are provide sufficient energy to different loads, decrease energy deficient, and decrease the loss of power supply probability factor. Here we present to you the static model of the PV panels, the inverter, and the battery. There are four possible scenarios in the load management algorithm. If the PV generated power is less than the load power, then the load will be provided by the battery. However, if the battery state of charge is below its minimum level, then all loads will be disconnected. In case of power excess, the surplus will be transferred to the battery. However, if the battery state of charge is higher than its maximum level, the excess will be used to supply a water pump. In order to control different loads, the management strategy used the following inputs: the ambient temperature, the natural irradiance, the battery state of charge, and the PV generated energy in the previous time interval. The study system data were collected from a tropical country. In Figure 7, we present the monthly production of the PV panels, while in Figure 8, we present the load consumption. The simulation results were obtained via MATLAB software. The following table represents our system characteristic. The first table represents the system powers. The second one represents the PV panel parameters, and the last one represents the inverter parameters. In the following figures, we present a comparative study between two systems with and without load management strategy. In Figure 9, we present the load cutoff duration. We can see the system without load management in blue color and with load management in red color. The total cutoff duration of the system without load management is approximately 360 hours, while it's equal to 219 hours with energy management. The following figure represents the state of charge of the battery of both systems. This shows that the monthly average state of charge of the battery is highly improved using our management strategy. The last figure represents the monthly loss of power supply probability of the two systems. We can see that the reliability of the system is improved as the LPSP factor is decreased from 7% to 4%. In this work, we implemented a management strategy for an off-grid PV battery hybrid energy system. Our objectives were to control the different loads according to energy availability and reduce the lost power supply probability. The simulations were conducted using simulating MATLAB software, and they demonstrate the efficiency of the management strategy. The energy deficient of the system was reduced about 40%, and the reliability of the system is improved as the LPSP decreases from 7 to 4%. Thank you for your attention.
Okay, thank you so much to all the speakers. Probably we can pick now some of the questions that are asked from the audience. I don't know if we have any question for the speakers. Okay, I cannot see any question here in the Q&A box, but probably I can take the lead and ask one or two questions for the different speakers. I will start with the talk on blockchain-based solar energy trading. I didn't see any simulation result or any result. I would like to know what's the state of progress in this research work from the authors of this paper. I don't know if we have anybody from this paper here with us. Otherwise, probably we can ask the authors from Aramco. I know that Aramco is a big business in Saudi Arabia, oil business. So, and certainly smart grid is one of the key technologies that Aramco would probably certainly develop. I don't know what the the situation with respect to smart grid adoption within Aramco.
This is Ammar Al-Aithan. Thank you for allowing me to participate in this great conference. Of course, we are in Saudi Arabia, and in Saudi Aramco are adopting some of the key features of smart grid. We do have a couple of projects that we're implementing, such as smart metering, such as integration of renewables. For example, in Saudi Aramco, we have the largest car parking solar PV installation, 10.5 megawatt, that we did almost 10 years back. And we do have an organization and a plan, a master plan within the company to implement different initiatives of a smart grid based on need. The beauty of a smart grid is that you can customize it based on your need, based on your financial situation, and based on your different grid topology. Of course, on a larger scale, it's implemented in a company-wide by the utility and by different ministries within Saudi Arabia.
Okay, thank you so much, Ammar, for the answer. I have another question regarding the kind of maybe partnership or collaboration with university. I know that there is a very, I would say, notorious university nearby at Dhahran, the Dhahran University of Petroleum and Minerals. Do you have any partnership on the same research topic related to smart grid?
You mean King Fahd, the University of Petroleum and Minerals in Dhahran?
Yeah.
Okay, which yes, we do a lot of not necessarily research, but more of collaboration on studying and putting together a plan. Okay, that and just a plan as we go that suits the company. And also we do have a collaboration with KAUST, King Abdullah University, which is in the Western region. We do have an annual conference for Saudi Arabia Smart Grid, okay, which usually happens around December time, but for the COVID-19, mostly there is going to be another round of the same conference. What we do mostly in Saudi Aramco is aligned of what the Ministry of Industry and utility impose, because we are part of a grid. Okay, we own our distribution system for the large oil and gas facilities, but they are at looking at the whole picture, they are still a part of the grid.
Okay, thank you. Because there are also some, I would say, IEEE communities in Dhahran that's working on a very, I would say, similar conference, the IEEE Energy Conference that was probably launched initially and from the Dhahran, and then was organized in different parts of the world. And it was even officially adopted by IEEE during the last 10 years or so. I still remember Jafar Al-Ibrahim, Dabal, and many other colleagues from maybe from the Aramco that were also key to the development of this conference.
True. We participate. We as a large oil and gas company, and transforming to an energy company. We participate in these conferences, and you know that the area in the GCC is always thriving to go into these technical conferences, especially in oil and gas. And we look into energy, we look into smart grid, we look into different industry trends. Okay, to be able to, of course, look at our company and our country as a whole from economical perspective and from industrial technologies and revolutions, not to stay behind.
Okay, thank you so much, Ammar Aitan, for your reply and comments, and
you're more than welcome.
Keep also connected to IRSEC. We look forward to meeting you in person probably next edition, inshallah.
Inshallah.
Okay, so I think we still have a few minutes, so we can probably, if there is no other question from the any question from the audience, I have another question for the last paper. I've seen that you to optimize, you know, the energy management, or the energy management strategy you propose is based on some kind of prioritization of the load. You have 3 categories. So what about including, I would say, more complex, probably prioritizing models based on, I would say, AI algorithms? What would be the, you know, the impact on the on the strategy as a whole? So that's, I would say, a very interesting question. I know that you have probably simplified the problem in taking 3 categories, but what about probably just keeping the system as it is and trying to adapt, you know, the management strategy based on an intelligent algorithm based on the machine learning, for example? Have you tried this?
Thank you for having me, Professor. And I would like first to congratulate you on the success of the conference. As for your question, I believe yes, it would be preferable to use different type of loads. For example, we can use another type of loads that is not considered as important and less important and dumpy loads. We can include many classes in these loads. Also, we look forward to use many intelligent algorithms. Like if you look in the algorithm, we use different sensor data for the management, and also we use an approximate of the state of charge of the battery of the last day. We use also the energy of produced in the last day. So matter of fact, our perspective are to use intelligent algorithm like neural networks or LSTM-based networks to forecast the state of the charge of the battery, to forecast also the produced energy in the next day. I believe this will have a complex algorithm we can construct to validate or to compare with the simple algorithm.
Okay, thank you so much for the explanation you provided regarding this question. Wishing also to meet you in person next edition, inshallah. So we can just conclude this first session of the 5 minutes presentation and move to the last one, you know, today. So we have 4 papers in this session. Allow me just to present the 4 papers. The first one is smart grid cost optimization, comparing Billman and generic algorithm. That's presented by, I think the authors are Fatima Zahra Zahrawi, Hassan Din Shakir, Mehdi Tausi, Hamid Wadi. The next paper is on magnetic induction wireless power transfer in solar roads for electric vehicles, experimental case projects. The authors are Adil Shahat, Stephen Thomas, Austin Lawson, Mason Moore. The following paper is a hybrid wind PV DC microgrid experimental project. The authors are Adil Shahat, Samuel Foucault-Red, Deborah Cipro, and Antoine Cover. The next paper is applying deep learning model to predict smart grid stability. So by Abdul Wahid Salam, Abdul Aziz Al-Hibawi. And the last paper is Global Fuzzy Supervisor Control for Dual Input Single Output Boost Converter by Sameh Mahjoub, Harvey Sharif Alawi, Laurent Delaroche, Bruno Marik, and Nabil Derval. So probably you can just start by playing the recordings of the 5-minute presentations, and then we'll have.
I'm glad to present our work on grid cost optimization, comparing Bellman and genetic algorithms. I will start with an introduction, then I will present our microgrid model, then we will discuss the optimal management problematic, show simulation results, and end with a conclusion. The benefits and motivation behind using microgrids are many. We can cite, for example, the optimization of the energy bill, the reduction of transmission losses and greenhouse gas emissions, provide energy supply, and minimize dependence on the main grid. Hybrid system is a combination and integration of several energy sources to better use the local resources, smooth the production, reduce the amount of stored energy. It is essential to combine several sources in order to meet the needs and provide storage. The studied microgrid is grid connected. We can see in this figure that is composed of three distributed energy sources: wind turbine of 90 kilowatt peak, a gas turbine of rated power 30 kilowatt, lithium-ion battery as energy storage system of 500 kilowatt. The objective of the management algorithms are ensure uninterrupted power supply, optimize the use of renewable energy in the energy mix, minimize the energy bill and CO2 gas emissions, optimize the production on the market. The objective cost function is defined as the sum of battery, gas turbine, grid, and equivalent CO2 emission costs. In this work, the power produced by wind turbine is considered with no cost to maximize its use. To realize energy management, it is necessary to satisfy the power balance, satisfy all operational constraints on different time horizons, determine the electricity price of sale and purchase on the main grid. It varies during the day. At each moment, the power balance should be respected. To improve battery life, the state of charge should respect the two first constraints. Also, it is advisable to use the turbine above 50% of its rated power to increase efficiency and weaken emissions. To solve our problematic, we have used two different algorithms, Bellman and genetic algorithm. The advantages of Bellman algorithm are for example, minimize the costs when the network is built, robust to find the shortest path from one node to another with high efficiency and accuracy. Simple, it does not need complicated data structures for application. Genetic algorithm mimics the natural evolution of biological systems. It was chosen because they can solve difficult problems fast in a reliable way. They can be directly interfaced with existing simulation and models. They are easy to hybridize. They have inherent parallelism which helps fast conversions. We can see here the load power and wind generated power shapes of the studied day. After simulation, we obtain these powers optimal dispatching by Bellman optimization. And in slide 16, we can see the powers optimal dispatching by genetic algorithm. We compared both results. During the studied day, GA makes an economy of 6% in production cost comparing it to Bellman. Air pollution is also reduced by 10% due to the reduced use of gas turbine. As a conclusion, we can say that the integration of auxiliary sources ensures the clipping of the power withdrawn from the main grid during peak demand. Fluctuations in wind power are balanced by the power exchanged with the main grid and the batteries. Genetic algorithms lower the production cost and CO2 emission rates for the same tested day. The execution time in GA is also 4 times shorter. Thank you so much for your interest and attention.
We probably can move to the next recording.
Hello everybody. Today's paper about magnetic induction wireless power transfer in future solar routes for electric vehicle charging. We are proposing experimental investigations based on a small scale case study. My name is Adel Al-Shahat. I am a senior member of IEEE within School of Engineering and Technology, Purdue University. And my other team members from Georgia Southern University, Stephen Thomas, Austin Lawson, and Mason Moore. So, our presentation outlines includes abstract, project description, methodology, discussion of results, conclusion, and references. So what we are targeting with the increase of the electric vehicle now over the world, we need significant research to improve the charging of electric vehicle, to try to overcome the problems of cable for the plug-in charging, and also to improve the driving range, also improve the battery life and the efficiency of the operation at all. So one of the valid solutions, or was the potential solutions, is the dynamic wireless charging. So that's why for this paper we are trying to implement and investigate the dynamic wireless power transfer, which while charging it utilizing the solar panels, whilst charging for electric vehicles was simulated in this paper, modeled using ANSYS software for making analysis, and also we built small scale model, and then this created model can charge 12 volts batteries with a control of microcontrollers. We started with a complete background and literature review, or not complete, but I mean good background and literature review. And then for the project description, those are the components which we used, including portable or foldable module of PV panels, and also charge controllers, converter DC AC converters to switch from DC of the solar panel into AC, which you will need it to make the power transfer coils, which is the transmitter and receivers, and then transmit the power wirelessly between them. We used the team built a small scale rectifier using diodes and capacitors, and the details in the paper, and also we charged this small scale battery to show the validation of our design. Before showing you the complete constructions, we had some simulations under the methodology using the ANSYS software. We simulated the coils in ANSYS as shown in this figure, and we investigated the magnetic field intensity within separation of different distances to 100 millimeter so far, with different specifications and complete analysis for flux density. Also, we designed inverter with using the multi-sim and also resistor protection circuit, and we used the Arduino program to read the voltage after the rectifier to examine it is working by proper way. Finally, we built the complete setup, including the solar panel, inverter, rectifier, battery, and small-scale car, and we got various results obtained under different separation, vertical separation with inductive values, coupling coefficient, which is very important parameter to manage the process, and also under the horizontal separation, we got the coupling coefficient based on different distances, plus also the coupling coefficient values obtained from angular misalignments as shown in those tables. The conclusion: the results for both simulation and the physical model are useful in understanding the parameters that will lead to be successful and efficient wireless power charging for electric vehicle. Horizontal and vertical simultaneous tests show that what theory suggests for wireless power transfer. The closer the coil, of course, the higher the efficiency. However, we have promising results for this small scale. Of course, more investigations will be needed, and this is what we are building in the lab on bigger scale, especially to improve the performance of the physical model and make it more closer to the real life situation. Those are our list of references, and if you have any question, please reach me. Thank you so much.
Thank you. So let's move to the next paper.
Okay, hello everybody again. Due to the importance of the renewable energy systems, especially hybrid, wind, PV, DC microgrids, which is popular all over the world, the research team started to build this experimental project based on some simulation and then some real-life situations. The team includes myself, Adel El Shahad. I am within the School of Engineering and Technology, Purdue University. Samuel Fakhrid, Deborah Kilpo, and Anthony Capri from Georgia Southern University, ECE Department. The outline for this presentation of the paper is abstract methodology of the proposed system, system model and simulation, and then implementation, results, conclusion, and references. So, because of the importance of the DC system, DC microgrids, especially in recent years, most electric loads today also can use DC current. Therefore, it is reasonable to investigate using a DC to connect all of these DC sources and loads. However, high dependency on weather conditions, especially if we are using renewable energy sources like wind, like PV, and to overcome this weakness of the unpredictable nature of those clean power sources, different green energy sources and the power electronics converter need to be integrated with each other to try to enhance the overall performance for the system. This paper presented a battery storage hybrid standalone photovoltaic wind energy power supply systems. Based on the simulation results obtained from the MATLAB Simulink, it has been found that the overall hybrid system can work under variable weather and load conditions, and this system will be used to power a weather station, which could be in turn provide the necessary environmental conditions like temperature, wind speed, altitude, and so on to determine the trajectory of any rifle or handgun loads, as this is our practical application, which we build the real prototype with a real small-scale system for it. So the methodology of this proposed system is a typical DC microgrid requires this dump load, charge controller, lead-acid batteries, panel, PV panel, wind turbine, and also AC loads. And this is what we investigated here also in this paper. Under is the DC power control and the deep cycle battery and some DC loads like light, laptop, or telephone, and the configuration is shown here. Here we used under the system model and simulation, we used the MATLAB Simulink nature to build our systems, including the wind turbine Simulink model and also the Simulink for the battery and for photovoltaic, and we combined all of them under this block diagram, and we analyze the results with three-phase voltage from the wind, or the current from the wind, also the battery voltage and the state of charging, plus the battery controlling system under the Simulink nature. Then after that, we went to the implementation stage to help us in our application as shown in this figure, including the PV or solar power generator source, wind turbines, the load, converters, controllers here, and the screening or monitoring for the situation. And also here we can investigate from this experimental result the range at varying angles and range of the height for the target which we are using the gun to target it. And this, if we drag, this is no drags here from the result of this small scale system. As a conclusion, simple conclusion, as far as the project go, our hybrid wind PV DC microgrid has accomplished many key tasks through the data and the information we have provided in this literature. It has proven to be not just economical but also sustainable and environmentally friendly. It can be easily manufactured in mass quantities and is very safe to the public. We have also considered the cost of the implementation of developing countries and assured that the system we have provided is cost effective in comparison with current power providing methods. The safety of the environment and the users of our product have been our top priority throughout the entire production system. And this is our list of references, and this is thank you so much, and if you have any question, please reach me. Thank you so much.
Okay, thank you. So let's move to the next talk.
Hello, this is me, Abdul Wahid Salam, PhD student, Faculty of Science, Abdul Malik Al-Saadi University. I will present our work, which is entitled as Applying Deep Learning Model to Predict Smart Grid Stability. This work is organized as Introduction, Dataset Description, Deep Learning Proposed Model, Comparison Models, and Experiment and Results, Conclusion and Future Work, and finally Acknowledgement. Introduction. A smart grid is an advanced concept of power system which harmonize electricity and communication in system network. Predicting smart grid stability is a challenging work. In this work, we will introduce a deep learning model to predict the stability of the smart grid. Dataset. The dataset of this work is obtained from UCI repository, which consists of 10,000 records. It is related to grid stability simulation for 4 nodes, 1 for producer and 3 for consumers. It consists of 12 input, feature and label, which consider as a classification problem. Also, in this work, as the dataset is considered as imbalanced dataset, we consider 3 options for simulation of the data and compare our proposed model to others in the 3 different datasets. First one, it is in the base of the dataset, which consists of 6380 for unstable classification and 3620 for stable classification. And we divide them almost equally for 4 faults. Also, we reduce the number of features of unstable classification to be equal to stable classification in the almost 4 faults. And finally, we compare our proposed model to others in the oversampling dataset, which we here do to increase the number of instability classification to be equal to stable classification. Proposed model. This figure shows the proposed model structure, which consists of 9 hidden layers beside input and output. Actually, this structure is based on densely neural network, which every layer is connected to the previous layers. And the only difference between densely layer and our cyclisted structure is that we replace concatenation layer by summation layer. We compared many deep learning model and machine learning to our proposed model. We use here for comparison feed forward neural network, recurrent neural network, and gate recurrent neural and long short-term memory, logistic regression, gradient boosting, decision tree random forest support vector machine. We choose this model as used in the previous study. Result on the original dataset experiment, it is clear from the table here that proposed model gets the best accuracy comparing to its counterpart, and it achieves not almost all the matrix that used in this simulation: accuracy and precision and recall, F-score, and mean that originally getting from confusion matrix. On the other hand, we use the ensembling dataset experiment as we said before, and also our proposed model achieved the highest and the best accuracy comparing to the other models. In the last comparison, which is on the oversampling dataset, also proposed model achieved the best result comparing to its counterpart, and also we can see that the accuracy is increased comparing to the previous dataset, and this is because we know that deep learning depends on the data, and here we increase the number of samples, so we achieve the best. We achieved a higher accuracy comparing to others. Conclusion and future work. Predicting stability of a smart grid is an essential method. In this domain, we enhance the deep learning model. It achieves a highest accuracy comparing to its counterparts. We compare the proposed model to other model in dataset with difference situation, original dataset, undersampling, and oversampling dataset. For future work, we will implement our model to predict the stability with more factors that affect the grade. Thank you.
Thank you. So let's move to the last paper in this session.
Hello, my name is Samah Mahjoub. Today I will introduce my work, which is entitled Global Fuzzy Supervisor Control for a Dual Input Single Output Post Converter. In this work, I will start with a brief introduction, then the structure of the hybrid renewable energy system, followed by the double input single output post converter modeling, the control design and the power management, simulation results, and finally a conclusion. So, considering its demographic position, Tunisia has a favorable climatic condition for the development of renewable energies. As we see, the solar energy presents 19.4% and the wind energy presents 35%. In fact, the wind and PV energy becomes the major source in the global electrical energy in the world. Problematics are: generated power is dependent on the climatic condition, the integration of the renewable source, stability of the DC path are dependent on the performance of the power converter technology. Solutions are the use of an advanced power conversion system, the design of a smart control strategy for this kind of converters, and the use of storage devices. Our approach is to define a smart control strategy, the fuzzy supervisory control. Their objectives are control of the double input single output converter, maximize the utilization of renewable energy, improve the energy conversion in the system, and finally guarantee the protection of the system by maintaining the DC bus stability. For the structure of the hybrid renewable energy system, it is consisted of PV and wind systems, which are the principal source, the battery, and a resistive load. For the topology of the studied converter, it consists of two sources, voltage, two resistors, two inductors, two switches, and a resistive load. The electrical parameters of the double input single output converter are given as: the proposed converter has 4 operation modes. The first when the two switches are on, the second mode when the first switch is on and the second is off, the third mode when the first switch is off and the second is on, and finally when the two switches are off. This figure represents the control strategy of the system. So the aim of this proposed power supervision system is to conserve balance between the subsystems, such as the sources and the load. The whole system includes 3 loops. The external loops is for power management, followed by the voltage loop, which gives reference to the inner current control loops. The major feature of this strategy is to control power flow according to the optimal production of the sources. This supervisory controller offers a high flexibility in control to share the power among connected sources while protecting the entire system. The input signals of the fuzzy supervisory control is the source ratio, and the output signals are the scale factor. Fuzzy rules are planned using a Signo approach and are summarized in the following table. So, in order to assess the performance of the proposed supervisory control, the supervision strategy is applied to the proposed DC-DC converter, and a set of scenarios have been performed to validate the effectiveness of the fuzzy supervisory control. This figure represents the variation of input voltage and the load. This figure represents the simulation current waveforms under the control without supervision and under the supervision. So we can deduce from the two figures that the two input current have approximately the same value when the control is applied without supervision, but in the fuzzy supervisor control, the source that has more voltage contributes with more current. The two figures represent the output voltages. So the overshoots in the output voltage in the fuzzy supervisory control are decreased compared to the non-supervised controller. It seems clear that the output voltage of the double input single output converter will produce the reference value despite the various perturbations. The two figures represent the variation of duty cycles under the different control strategies. And finally, this figure represents the variation of the fuzzy outputs. So, simulation results reveal the efficiency of the adopted supervisor control strategy and prove its robustness by achieving the line and the load regulation under the different simulation conditions. Thank you for your attention.
Thank you again for all the speakers in this session. We can probably move now to the discussions. We have one question for the paper by Abdelwahid Salam. So the question is, what time have you measured the parameter, the electric parameter to the wind and PV solar? This question is asked by Dawda Abdurrahim.
Would you please repeat the question again?
Yeah, it's on the Q&A box. So you can just check it. Is what time have you measured the parameter, the electric parameter, to the wind and PV solar?
It's not related to my topic, I think.
But it was asked when you were presented. That's why I'm making the links with your presentation. But anyway, I think if anybody from the papers that were presented during this session can, just jump in and give any comment regarding this question. If you also probably if you can ask Mr. Dawda, if you can just be more specific, what paper are you targeting with your question? Well, probably I can ask just one question, waiting probably other questions to be proposed on the Q&A chat box. So regarding the paper that was, discussing magnetic induction wireless power transfer in solar roads for electric vehicles. I don't know if Dr. Adil Shahat is with us.
Hello?
Hello, yes.
My question is about hybrid wind PV DC microgrid. In his experimental, he showed that he do a measurement to test.
Okay. Okay, so you're talking about the second paper, third paper, yes, hybrid wind PV DC microgrid. Yeah, thank you so much. Yeah, I don't know if Dr. Adil Shahat is with us here to give a short answer to this question. Okay, so I think that there is nobody from this paper present with us in this session. I'm sorry, but anyway, probably we can just reach out to the author. You have probably seen we can also share the email address of the authors that are already available, I think, but you can just reach out to the author and ask him directly. Okay, thank you. Any other question? Okay, so I think it's thank you so much again for your attention. I would like to thank all the speakers in this session. Again, the keynote speakers, but also all the speakers of the different papers that were presented in the two sessions. And well, looking forward to meeting you tomorrow, also through the other sessions that are still, to come in this international conference. Thank you so much.
Thank you very much. See you tomorrow. Bye-bye.